building LLM applications. Have you ever wondered how machines generate realistic text, translate languages, or even create images from scratch? Well, you're about to discover how the magic happens. In this course, we will dive deep into the fascinating world of generative AI, specifically focusing on large language models. Now, as AI continues to shape industries, understanding how to build powerful AI models is a crucial skill. Whether you're an AI enthusiast or aiming to develop real world AI applications, this course will equip you with the knowledge and skills to build your own LLM applications, giving you an edge in today's AI driven world. Let's talk about what you will learn in this course. First, we will introduce you to the concept of text generation, focusing on LSTM, which is long short term memory, networks, and how they predict the next word in a sequence. You will learn about essential techniques like word embeddings, which enable machines to understand the relationships between the words, and engrams, which help in creating training data for language models. You learn about essential techniques like word embeddings, which enable machines to understand the relationship between the words. Then, we'll delve into the architecture of LSTM models, covering the key layers and how they work together to process sequences effectively. We'll also explore advanced topics like attention mechanisms and transformers, the driving force behind modern AI breakthroughs. You will see how these concepts enhance large language models' ability to process large amounts of data and generate meaningful context. Plus, you'll gain hands-on experience through practical demonstrations where we will build models from scratch and apply them to real-world data sets. Also, if you're interested in mastering the future of technology, then the professional certificate course in generative AI and machine learning is the perfect opportunity for you. This is offered in collaboration with the ENICET Academy IT Kanpur, and it's an 11-month live and interactive program providing you hands-on expertise in cutting-edge areas like generative AI, machine learning, and tools like ChatGPT, DALL-E 2, and Hugging Face. You will be gaining practical experience through 15+ projects, integrated labs, and live masterclasses delivered by esteemed IT Kanpur faculty. Alongside earning a prestigious certificate from IT Kanpur, you will receive official Microsoft badges for Azure AI courses and career support through Simplilearn's Job Assist program. So what are you waiting for? Hurry up and enroll now. You can find the course link below. Now, before we dive in, here's a quick quiz question for you to test your understanding. The question is, what does LSTM stand for? Your options are large sequence text modeling, long short-term memory, learning system task model. Drop your answers in the comment section below.
Today we get started with a very interesting case study, and we are going to look about LSTM for text generation. So this is how this case study is going to be. So today you can consider that you are learning the first step of generative AI. So let's get started. Getting started with this, you can just go through the problem statement that we have. So over here, the first one, text generation using the LSTM. So text generation is the task of predicting what word comes the next, given the words lies ahead of it. And it can be used as a chain of auto predict tasks. So this notebook, this notebook takes around 2 hours to execute. And that too, I'm saying, if you are using Google Collaboratory GPU, so text generation, right? So it can be thought of auto predict tasks, like the students open there, so many possible words are there. What words fits over here the best? So as far as the text generation is concerned, the text generation actually did start from the LSTM only, and that somewhere started in the year 1997, where we trained our model to predict the next word. But the very common problem in RNN was it was forgetting the older context. So now, to ensure that the context and all these things, then the thing which was done over here is they thought of doing the text pre-processing. And after that, somehow the performance was good. And if you recollect, can you tell me how many words can LSTM remember? How many previous words can LSTM remember? Right. 70 to 80, 70 to 75, that's correct. So this case study is so interesting. Auto generation is also called as the natural language modeling because training machines to perform text generation is an attempt to teach machines the mappings between words and how words in a particular language are related to each other. By learning which words appear after the sequence or after a significant volume of natural language, all encoded within the context vector, machines learn to replicate the human understanding. Like you are making him MAD, made, mad, and what are this text generation? Just giving you the applications. Or in Google, you're trying to search for it understands San Francisco weather, San Francisco Giants, valleys, states, universities, etc., etc. Then getting started. Now, this is where the most interesting part of this. And you know what? Though this is a case study on LSTM, do not under any circumstance think that we are repeating the same thing. I was say under any circumstances, I would like to tell you that we are not covering the same thing again. It's completely different. So unfortunately, I will not execute this. It takes a lot of time. See, what embedding is over here also once again. I will explain it. That's not a problem. Please have a look at this. The below code, this line of model.fit takes 1 hour to execute. I started this training at 6:47 a.m. and it ended at 7:38 a.m. And I said 1 hour, 6:47. Well, this is different. This is what is done using the freely available GPU with my A100 GPU, which is the paid version of it, paid version, which is 20 times faster than your T4 GPU. Still, it took this much. So one thing is for sure that if I run this notebook, then it's going to be really crazy. What I can do is parallelly, let me create a copy of this. Let's say copy, paste. I usually run this notebook on Colab only, but I am having a super fast computer. No? I'm using the Mac M3, which I just bought a month back. So I'm going to see this is my older one, which I'm not going to execute. And this is run, right, which I will execute. And the moment where it says that I am tired, I am executing, I'll take time. I'll show you the output in the earlier notebook. Did you all understand my approach? What am I going to do? And that too, I have always executed this notebook in Google Colab only. For the first time, I'm executing over here. So if there are any dependency errors or something coming, I will not rectify it right now because sometimes errors are solved in just half a minute. Sometimes it even takes 10-15 minutes. So in Colab, it will run for sure. Let's see. So first of all, we need the pandas for data processing and the CSV file handling. I need the operating system module to use the OS dependent functionality. I need the NumPy for linear algebra. I need TensorFlow to build the model. Over here, I need the embedding, which will turn positive integers into dense vector. This is different. Pay attention. Embedding does what? Numbers are converted into numbers only. Embedding is used for converting numbers only into numbers. LSTM, we understand, right? It is used. It is a type of RNN mainly useful for learning the long-term dependencies, and dense is nothing but the densely connected network, and the dropout, as we know, it's used for controlling the overfitting. Then you also see the sequential, which is kind of a placeholder for the model. So your entire thing goes inside this, and Adam is nothing but the optimizer. Then what is our dataset information? So import the medium article dataset. This dataset contains information about randomly chosen medium articles published in 2019 from 7 digital sources. Our assumption here is by exposing our model to natural language in a particular domain, it will see instances of which words usually occur in the sequence and therefore on the training. I have data from 5 different blocks. At least as a person from the data science domain, can I assume that you have heard about towards data science? Answer with yes or no. If anyone says no over here, our session, whenever it gets over, you go and skim through it. It's important that you are aware of it. It is nothing but a blog only, all related to data science. So you will like it. I mean, in the long run, it's good to know. Those of you who know it, that's really awesome. Have a habit of going through the blogs over there. Okay, you can see, right? Slash content slash. That's what I said. Every time I used to run this on the collab only. For the first time, I'm running it on the this thing. And where is my data set? Medium data.csv. And why don't I have it, or I have it? Just a second. Let me just Control C. Um, I have it. That's the data, right? Medium data. I'm going to load it and then we'll see it now what it is. Wait a minute. Before that, clear all outputs. Connecting to the Python environment. And we are done. We didn't run this, sorry. I hope there are no dependencies. See, so many imports, 6 seconds over. Done. Get the data set. Right, so ID, URL of the blog, title of the blog, subtitle, images, how many claps, responses the blogs received, reading time, publication, blog, and the date. I look at the rows and columns, which is quite obvious to understand. And I here understand that I have 10 different fields and 6,000 records. And then I say, I'm running this. Title. So I am only interested in the title. I am only interested in the title. So basically, the aim is I want the LSTM to go through a lot of titles again and again and again and again and again. And then at the end, I will be asking it that implementation of, and I say that, hey, predict the next two words. So it predicted for me RN and LSTM. I asked, hey, if I start with implementation of, predict the next four words. It predicted for me RN and LSTM and GRU. I asked it how to use and predict the next five words. So it predicted a time before medium learn. I asked it forecasting, predict the next seven words. It predicted future prices of cryptocurrency using historical data. I asked it data followed by three words, science recruitment. Deep learning is a predict one word, budget, and so on. So because I cleared the output, they are gone, but I had already pasted it down. So let me ask you, are you clear with the problem statement? What is the end goal that we are trying to achieve? Everyone, end goal is clear, right? So always keep in mind what we are going to obtain over here. This is going to be something, a very interesting case study for all of us. For the first time in our course, we are generating some data actually using the Python code. That's why this is an important case study. Okay. Data set information. And this is done. And this is done. And this is done. Let me take up the very first title. Title of one. So we know that this is the title of the second article. Right? That's the one, hands-on graph neural networks with PyTorch and PyTorch geometric. what am I saying? First of all, now here, right? In this title, if you ever look at some kind of web pages, you know, I'm saying over here in this title, now this is all text pre-processing, text pre-processing, something which we have not seen, but here in the data which is scrapped from the blogs, in such cases, you are likely to find this. So here, data of title dot apply lambda x dot replace this by space. So if you find this, so what is this? Well, the U prefix over here indicates that it is a Unicode string, just a special type of string. And this backslash XA0 is for non-breaking space, and this is for the regular space. So obviously you might have a question that what is a non-breaking space? Well, a non-breaking space is a space that will not break into a new line. For example, mm, let's say uh, when you are usually okay, let me know. It's a little difficult to convince you. So what am I going to do is I want to actually show you how I understand it. So I say, what is a non-breaking space? Generate two basic HTML code where in one code we are having a non-breaking space and in other we are not having a non-breaking space. Then I'll tell you what it means and I'll show it to you live so that you understand what I mean exactly by that. So what will we do over here? Yeah, I'm just copying this code. Now if you see ampersand NBSP is the non-breaking space. So what will it do? Now, if you see over here, example and text. Under any circumstance, even if the sentence gets completed, example on one line and text on other line will not happen. Let's first understand with this. So I come over here and I say without nbsp dot txt, I have the code. I'm saving it, close. With nbsp txt, I'll get that code. Now I'll show you. They are there. HTML. You have to convert it to HTML code and without NBSP. Now have a look at this. This is one thing without and with. It generated a bad code ideally. Okay, it's a bad code to be very honest. So I say, I'll do one thing. I can do one thing here. I will just say, now, yes, now you see, example and text. You see, they have gone on different lines. Understand this, huh? Example and text have gone on two different lines. Now, I'll copy the same sentence and in that with wala code, did you see? I'll just remove one word. So you see example and text are on the same line. I'll add one or two characters. Now, did you see over here? In spite of space being there, it came down. Whereas here, it printed this and then it break the word and it went to the new line. So where is that code available? Where without the NBSP, now if you look into the code, I have completed the code as it is, right? Whereas here, you see, I have added ampersand NBSP, which stands for non-breaking space, non-breaking space. So I am indirectly saying that, hey, between the last word, example, and text, under any conditions, they cannot go on different lines. You should not break that word. So these kind of spaces or these kind of codes will never ever be seen to visualize. So that is what I am cleaning over here. Did you all understand what are NBSP non-breaking spaces? Everyone? Right? Yes. Okay. So what are we doing is we are only processing the title column. And what is question by Chanda? Just to confirm, input has title and not the content. Yes, that's correct. So we are not looking into the content. We are only looking at the title. So, yeah. So I'm saying that if there are any non-breaking spaces, replace it by normal space. Done. In the same way, I say you also have something which is called as backslash 200. It is called as a hair space character, such a small space that it doesn't even look like a space. So these all things are used while you are coding using the HTML. So removing that is also advisable, and that is what I'm doing over here. So my data is free from the NBSPs and the hair space characters. Now, usually these two are the major problems. After that, things are good. Now I went into tokenizer. See, I am not following the same approach as we did in the previous case study. But essentially, we are doing the same thing. So this is also one of the approach. That is also one of the approach. So first of all, for doing the tokenizer, I am importing the tokenizer. So tokenizer will turn the string into list of integer indices. Tokenizer will convert the list of string into integer indices. So if I have a word like the cat sat on the mat, you see over here, every word is given a unique number. You can see the cat sat on, given the numbers 1, 2, 3, 4. And again, because the came, it gave 1 and mat is given the next number. So this is what is tokenizer doing. So over here, OOV, if you are giving OOV, then it will be added out of vocabulary. Yeah? OOV stands for out of vocabulary. So it will be added to the word index and will be used to replace out of vocabulary during the text calls. So if you consider, let's say an example where I'm saying cat sat on the mat. Now, in this case, there is a number 6, ideally it is 1 2 3 4 5, but there is a number 6 which came. So the index 6 is going to be out of vocabulary. So the purpose is to avoid the errors when the model is given a word which it has never seen. For example, in the training, it got to know a lot of words. For example, in English language also, all of you will be like, yes, I know English, I know English, I know English, I know English, I know English. Right? Everyone will say that, yes, Darshan, I know English. So if I say, if I am talking about a very unique and kind of unknown, let's say, English word, for example, so you are a person who has learned so much of English, but all of a sudden, so basically, quixotry. Quixotry is a word which you have never studied. Quixotry is a word which none of you has ever studied, but it is a valid word in English. You can Google about what is Quixotry and let me know what meaning you find for Quixotry. So if I would not have told you that it is a valid word, what is that word for you? You'll be like, Darshan, this is not even an English word. It is out of vocabulary for me. Correct or not? You will say it is out of vocabulary. So your brain is a model which has never seen that word in your 25 years of age, assuming that you all are 25. In the same way, in your training data set, let's say the model got a chance to see around 50,000 unique words. But in the testing data set, a new word came like quixotry, which it has never seen in the training data. Then the model will be very simple. It will throw an error, garbage in, garbage out. So this is OOV, which is used to take care of that. So let's say your model got a chance to look at many sentences. So the unique numbers that it has given so far goes from 1 to, let's say, 20,000. Till the time it is able to see for prediction one of the words, it's okay. But when a word comes which it has never seen, then comes a problem. That's exactly what I'm talking about. Right. Okay. So now I say tokenizer, go and fit. Fit on text is like update the internal vocabulary. So this method is going to create a vocabulary index. So if you are having a sentence like this, वर एकदम सेंटरला किचन मध्ये एकदम वर सेंटरला. So I was saying if you're having a sentence like the cat sat on the mat, so it will create a word dictionary. So it will be like the word index the is given 1, cat is given 2, and so on and so forth. So you can see over here, this is what is called as the word index dictionary, which goes on for every unique value. And 0 is reserved for padding. So they don't use 0. So lower integers means more frequent word. Often the first few integers are the stop words because they appear a lot. And then I'm printing the number of the unique stop words which I got over here. So I have got in my entire corpus total 8,237 unique words. So for all of a sudden, let's say a new word comes which it has never seen among this 8,237, then that will be assigned the out of vocabulary index. Let's understand with the help of an example. So I am taking the title. And inside that, now I say that I'm actually implementing it here, creating an object of OOV, fit on text, and I am adding +1 over here. So over here, we know that the length of tokenizer is going to give us this one, and the +1 is for the padding, right? So this particular thing is because the padding is done with zeros, and hence we are saying number of unique words +1. So what is the total number of words in the data set? That was somewhere around, we'll see that. This will give the total number of words in the data set. Then I have the word and its corresponding ID. This will be giving me the what is the OOV been indicated by and the ID of that word. Similarly, I have taken 3 words, ID of strong and consumption. Let's see. Now there are 8238 words. Consider the word ID. So OOV is given 1, 2 is given 2, though is 3, strong is 4, and so on. Can you show me the word index of OOV? 1, strong, it's 4, and is 8. Consumption is this, you can scroll and check it out. After that, now if you see, this was just conversion of the sentences, right? As you can see. Now the next is to convert sequences, text into sequences and generating numbers. So over here, converting text to sequences. Now, what is this? This is something very important. Pay attention because you are likely to get lost out over here. So it's easy. It's just that you need attention, right? Because these all are not something that we have done in our earlier case studies, and that is why that's important. So we say NLP models require sequential input data, and the input word or the token must be numerical. So here we are going to generate n-grams in order to train our model for the next word prediction. So let's say if I have a sentence like I am good, it will give unique numbers to each of these. I is 1, am is 2, good is 3. Then the output would be 1, 2, 3. Likewise, our titles will also be converted into sequences. Okay. Then, so this is already done, right? This is what I already explained you. This is done. Cat sat on the mat and all. Now coming on to this, what is this? Then we will make n-grams model for good prediction. Then we'll create n-grams model for a good prediction. Let's understand this. So first this happens. Then n-gram model is like it is going to convert a text sequence 1, 2, 3, 4, 5. I am a data scientist. Every word is given a number. And then I is 1, M is 2, O is 3, data is 4, and scientist is 5. So 1, 2, 3, 4, 5 is the coding. Then after that, we create an n-gram sequence. So what is n-gram sequence? N-gram is nothing but n-gram. Like for example, I'll quickly like to explain the most popular available English unigrams, bigrams, trigrams. Now look at this. It's pretty simple. Oh, my laptop is hungry. Let's look at bigrams. Yes, you can have. This is good. This is good. So here, what are the words which are bigrams? See, there are some words which make sense if and only if they appear as a pair. Like for example, me saying, good morning, good night, good evening. All of these words make sense when they are available as a pair. All the best, Chetan. So all the best makes sense when they are appearing as a trigram. And rest all words are unigrams. So this is the best example. Like sometimes good makes sense, sometimes very good makes sense, sometimes not very good makes sense. Because we understand not very good is completely different from very good. So that is what I'm talking about. So I say, let us take a data frame of 5 sample sentences and apply n-gram unigram model and bigram model and trigram model on it. Now look at this. You'll actually understand what is happening. What latest take has latest. I want to see the code for each of this. Now have a look at this. So first of all, I come over here and let's say I'm creating a notebook. I call it as ngram.ipynb. That's what you see. And I'm doing the necessary imports. Done. So that's my data frame, which is there. Okay, I'll also say set option. And yeah, this is the data frame that you see. Now, how does it work? Well, this is very interesting. Now, code we are not interested at the moment, but I definitely want to show you how this n-gram, bigram, trigram works. So have a look at this. When I print bigram, it is finding out from the sentences. So AI is came two times. Is that? Let's manually look at AI is here and AI is here. Congratulations. Okay. And rest all the combinations of two which it created is consisting of only one gram. So if I look at trigrams, everything is one. I say, can you modify the sample data set to ensure that there are good amount of bigram and trigram also seen? I just have to change this. So that's the only change. I come over here and you see this is the sentence. Now I'm saying bigram. You see over here, has come two times, deep learning has come two times. Is that so? Well, deep learning AI is, and that was, oh, not deep learning is, deep learning. Deep learning, yeah, that's correct. Deep learning has come two times. Let me look at trigrams as well. Let's say I'm myself repeating the sentence. Now you see, it says that in various industries is a trigram, three words are there. It came three times. Is that so? Let's check it out. So if I highlight in various industries, see it has come three times. So what is basically n-gram? So n-gram over here, if you look into the code, it asks us to look for the n-gram range. So if I'm giving the n-gram range over here as 1, so it will pass 1 comma 1. But if I'm giving the n-gram range as something else, maybe as 2 or 3, then the things completely change. So basically, it's for generating all double words. It's not that, okay, they are meaningful or not, but it will generate double words. Bigram and trigram will generate three words. And in the same way, unigram will generate single word. And this is the count of it. Did you all understand what is n-gram? Right? Yeah, I mean, from the sentences trying to generate as many double words or triple words, whatever we say. So that is what this has done over here. Great. That's nice. Really nice to know that it's understood. Now, this is where, again, I'm showing you an example. So right now I am, we are training our sequential text generation model, and what are we essentially doing over here is increasing the total number of training examples. So what am I doing? I'm increasing the total number of training examples where I said, if I have a sentence like I am a data scientist, right? So let's say I have a sentence like I am a data scientist. Then the first line over here is going to convert it into sentences. So tokens. So 1, 2, 3, 4, 5, that is the list of the tokens. Then after that, when I say the length of the token, there are total 5 unique tokens. That is what is written. So when I say for I in range of 1 to this, because token length itself is 5, it will go from 1 to 5. So what is n-gram going to do? N-gram is going to generate words like this. What did I say? Token list, this goes from 0 to I plus 1. So first time I is equal to 1. First time I is equal to 1. So when I is equal to 1, I say that you select 0, 1, 0, 2, 0, 3, 0, 4. So when I is equal to 1, it is going from index location 1, because 1 is the starting index, till this. It generates 1 comma 2, When I is equal to 2, later on it generates 1, 2, 3. When I is equal to 3, it generates 1, 2, 3, 4. When it is 4, it generates this. And all of these sequences which are getting generated, they are appended. So this becomes a list of lists. And then I'm printing the length of the sequence, whatever it be. And this is how it is. And this is the n-gram sequence. That is just for one sentence. Oh, yeah. N-gram sequence is nothing but a list of integers, which is a sequence of the n words. You can see over here, I'm doing it one more. And this time I'm doing it for all the words. As you can see, if I'm not doing this, but if I'm asking it to print how many input sentences are there, so all of these are printed. But if I don't do that, and if I say that just print the length of the input sequences, I'll cover it out this also 48,000. So basically, from how many sentences were there? Around 6,000. From 6,000 sentences, we have generated around 48,000 sentences. From 6,000 sentences, we have generated in this way around 48,300, 461 sentences. Example for n-gram. So if I have a sentence like I am a data scientist, and if I am considering generating unigram, then these are the words. If I say I want to generate bigram, then am a data scientist are the words. And trigrams are this, where you have three things at the same time. I am a data scientist. Then this is 4 gram. I'm a data scientist. And this is 5 gram. Now you see a single sentence can be converted into unigram, bigram, trigram, 4 gram, and 5 gram, which means from this single sentence, I can generate 5 different sentences, which means from that single sentence, I can generate 5 different sentences. And that is exactly what is n-gram sequence. So what do we basically do is we have the input sequence, which is a list of n-gram sequence. So how does that happen is when you have this, the first thing is what we do is we go for tokenizer. So obviously I am a data scientist gets converted like this. So my sentence currently is 1, comma 2, comma 3, 4, 5. And when I talk about n-gram sequence, now here you have these are the unigrams, these are the bigrams, and these are the trigrams, and these are the quadra, these are the penta. So basically, what did we do is we converted everything into numbers, and then we are creating various parts of numbers clubbed together in bigrams 2, in trigrams 3, and in 4 grams, 5 grams, 4 and 5 respectively. Is that clear to everyone? Huh? Those of you who are saying once again. And yes, of course, they have to be consecutive words, no? Can you say all the best in any order and people will understand it? No, of course, it has to be consecutive words only. Shailesh, non-consecutive word will make any sense? What is the problem statement? What is the problem statement, Shailesh? Raise your hand. Let me talk to you. So these all are very new things that you have not studied in NLP. And obviously, you are working on the chat GPT and all of the architectures and you don't know text pre-processing, then it becomes very difficult on the later stage as well. So understanding that is mandate. So I say, now, now that we understood this, I got 48,000 sentences. So essentially, I say we had initially something around 6,000. What was that? Titles. We converted them into sequence of words, and now we have total sequences 48,000. Right? So now we have 48,000 sequences. If you can also see the input sequences, how they look like. That's going to be crazy, but you can see that. See, numbers, purely numbers. This is a bigram, trigram. Did you see over here again, Shailesh? 5 followed by 676, 5, 676, 68. And then this is the 4 gram, 5 gram, 6 gram, and so on and so forth. That's how it is able to extract this. Okay. So order is important. Yes, I don't know whether to call it as an increasing subsequence, but I think you understood my point. So after this, I want to make all the titles the same length. Now, the problem is everything is not of the same length. Some are even of length 2, some are of length 5, some are of length 3, etc. So I would like to make everything of the same length. So what am I doing over here is I am actually going through each and every input sequence and finding out the length of it. So I say, let's iterate over each and every sequence and find the length of each sequence. So I'm finding out the maximum length. So maximum sequence is of length 40. Okay. So I'm saying I'm going to use the pad sequences. So what is pad sequences going to do? It will pad zeros before it and make everything of the length 40. So I say here I'm importing the pad sequences. So then here we are finding out the maximum length, and this is where I say in the input sequences, pad the sequences based on the maximum length, and the type of padding is pre. By default, it is expected to pad this, yeah, by default, it is expected to pad all the relevant sentences. This is the input sentence number 1, which became like this. If you just look at the shape 40. Similarly, if you look at any input sequence, it's the input number 12. Is 40. And that will always be the case. So what we did essentially is, basically example of padding. So consider I have input sequence like this. And I'm saying that what is the maximum length over here? 1, 2, 3. Okay. So here when I'm doing this pad sequence, so what is going to happen is this. The maximum length is 5. So this remains as it is. 4 and 5 will also be made of length 5. And 1, 2, 3 will also be made of length 5. So you're padding zeros before. Here you padded 2 zeros, here you padded 3 zeros, and here you padded no zeros. That is what is padding. Did you understand what is padding? Found out the maximum length and did achieve this thing. समझ गए? Making everything of the same length. So everything I'm explaining you with the help of very small examples. So when I do that, I expect all of you to reply, not just a few of you. Let me be 100% convinced and not 10% convinced that yes, you. And what am I asking you? Am I asking you to transfer your car in my name? It won't take a lot of electricity. Trust me. Typing one character won't increase your electricity bill. So please participate. That will help me understand whether we all are connected. All of a sudden, don't ask completely irrelevant question. So now this is the thing that we understand. So if I look at input sequences dot shape. So you have 48,461 independent variables and 40 dependent variables. So we have 48,461 input sequences, which is nothing but independent variables, and each sequence has 39 words. Yeah, because the last is the dependent variable. Na? So basically, let me give you an example uh, of 5 input sequences. So consider I have I am learning deep learning. Exactly 5 are there. Now over here, what I want to do, listen to this. My independent variable will be is equal to I, and the dependent variable will be IM. Okay, that's where I say my first input sequence is I, second input sequence is IM, third is I am learning, fourth is I am learning deep, and fifth is I am learning deep learning. So what it happens over here is how it populates the independent and dependent variable. So initially it will consider the independent variable to be I and dependent variable to be M. Next time it considers independent variable to be IM and it learns to predict the next one. Next time independent variable becomes I am learning and the dependent is deep. Next time I am learning deep and the dependent is learning. Next time I am depending deep learning and it says dependent N. And thus my independent variable is this and dependent variable is N. Right? And here, the end is the end of the input sequence, which basically indicates that the sentence has ended. And I say this process repeats for all the input sequences. As simple as that. But here I explained you all in terms of I am. I am learning. I am learning deep. But in machine, it is all going to be purely numbers. right? So machine will not have this. So the input sequence, I would say, input sequence will ideally be numbers, and the output will also be numbers. Let's say, for example, I am learning deep learning. Well, the input sequence is I am learning deep learning. And the thing is going to be, right? I sorry, that was correct. I am learning, and output sequence will be fine. Or it can be input sequences I am learning and output will be deep. Or it could be input sequences I am, output could be learning. Or input sequence can be I, output could be 2. And that is exactly where input sequence is empty and output is 1. And that will be where now we have reached the next word. And this is to stop. Are you understanding? Basically, I explained the same thing. Here it was happening with text, but in real life, it is going to happen with numbers. So machines are going to understand the pattern between the numbers. Crazy confusing for humans to understand, but machines understand it the best way. So is the unigram used to derive the first dependent variable in the bigram? They are not. No, 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 absolutely not. They were, see, Ngram was just to increase the number of sentences in the training data. Other than that, they had absolutely no usage. Just for increasing the training data, we had that usage. Okay, now everyone, did you all understand? Wait. Before me asking that, whatever I did over here, basically here, the same thing is happening. So here, what am I saying? That colon means I want all the rows, right? But where? Right from column number 0 till the second last column. Right? So here I say colon means all the rows and 0 colon minus means all the columns except the last column. That is going from column 0 to column -1. So if you just look at the shape of this 39, and if you look at the shape of -1 colon, well, this is nothing but the last column of the data set. Now this is where I am having my independent variable plotted and dependent variable plotted. That's how I derived, and I have this. And once you have this, I say, now it's time to convert the target to categorical. So over here, the target has currently values from 1 to total number of words, and I'm going to convert it to categorical. And the reason is very simple, because we are predicting the next word in the sequence, which is expected to be a categorical value. And that is what I'm doing, converting to categorical, and the length is the total number of words. So these are the labels, and I also show you the shape of it, predictors and target. Now, let me look at just randomly third sentence with label, and the label of shape will be this. And this is just to show you. Okay, all of these are intermediate steps just to show you. Okay. When Chandra says, when we have one output variable for each combination or sequence, how does the model learn to output the combination of text? Okay, that's an interesting question. So, because it is model is just generating, model is just learning to generate one single word only. No, but how does that help? You'll understand. Basically, what am I doing is at a time the model is predicting only one word. At a time the model is predicting only one word. So if I say implementation of, it predicts deep, finish. Then I give the new text implementation of deep and it predicts learning. Then I give the new text implementation of deep learning. Then it predicts the next word. Precisely, this is what I'm going to call in a loop again and again. So if I say generate 4 words, I'm going to call these updated text again and again 4 times. That is how it is happening. So at a time, it is learning only one word. Yes. So in fact, we have a similar thing in our code as well. See, if you see over here, this is the method actually. You can see it's in a for loop. Every time adding. So the new output is added to the seed text and passed again. After converting the title column to this, does it know which sequences belong to title? Then it doesn't know. It doesn't know. Of course not. It will only know whatever you are teaching. So based on that, sometimes the output may not be correct as well, but in most of the cases, it ends up being correct because it understands the relationship between every word and the next word. So it is likely to be correct. It is likely to be correct. Then will the pad characters also add noise? No, no, zero means absolutely no noise. Zero means there is absolutely no noise. Then I'm not sure if I'm jumping the gun. Question is, if I give 2 words, let's say this and this, and ask 2 words to generate, then it might generate this. Is it based on engram? No, again, I think your answer is exactly, the answer to your question is exactly same as the answer to Chandra's question. The model is only going to generate one image at a time. Model is only going to generate one image at a time. One word at a time. And then that one word is added to the current value and passed again. Getting that, Prabhu? So there is no question of anytime getting more than one word as a prediction. Yes, perfect. Here we get into the LSTM architecture. Coming down, I want to first of all talk about this embedding part, right? So that will give you a good idea. Mm, so before I even talk about it, no, I'll complete with this and then only we will go ahead. So I say over here, listen to this. Now, this is the code. Max is equal to model equal to sequential. So you know over here what we essentially do, right? So I'm creating a sequential model and we'll be adding the layers later on. Okay. Now, this is the input length, which is the independent variables. Where layer. So what is embedding layer used to convert words to numbers? So ideally, it's not words to numbers. I would say we are responsible for converting the sparse matrix into the dense matrix, which is nothing but converting words to numbers. Now, if you see, the first parameter is the total number of words, right? Which is used to find the total number of unique words in the text. Second parameter is the number of output dimensions of the dense embeddings. That is 100 features to be extracted. Third parameter is the input length, which is the length of the input sequence. Then you have adding a LSTM layer. This is something that we know, right? This is what we have done. So here I say 150 ideally is the number of neurons in the LSTM layer, and return sequence is equal to true means that the output of the LSTM will be passed to the next LSTM layer. We have studied LSTM case study. That's not new to us. Then I am adding another LSTM. So as you can see, again 100 over here, which is the number of neurons, and this is the one. And then I am adding one more dense layer, which is the output layer over here, right? So total words and softmax. And then we are adding the following atom and compile the loss and model summary. Now, embedding, I am yet to explain. Don't be under the impression that I'm skipping it, but I'm just going ahead and showing you this is good, and something is wrong over here. Well, and I'm saying value error. This I did it for kilo code cell will work in Google Colab. I'll comment it out. If you are running the code in the local machine, then you use not this one. This will be dot keras. That's what it said. Dot keras. Then let me fit it. And I started it just now. What is the time? 8:39 p.m. 8:39 p.m. Let us see whether we are able to get the output today. I'll just make a note of it. Where it ends, we'll see it. It has started. Mac is expected to be very powerful, so I'm expecting it to execute in less than an hour. Now, by the time this is coming to the output, we will quickly discuss the code. So over here, we understood everything. We also understood model.summary. So it shows us what is this thing, and all these things are there. And then I like to explain you embedding. So what is embedding? See, first you understand what is one hot encoding. In the sense, this is very important, image, very important. This will make you understand embedding in just a single shot. What I mean by that over here is, see, I have, imagine I have a word like man. I have a word like woman. In this way, I have many words. You know how many unique words I have? Let's say I have 10,000 unique words. Let's say I have 10,000 unique words. How many? 10,000. So the first thing that we do is, how do you convert the text to numbers? So one of the way of converting text to numbers is, because there are 10,000 unique words, we decide to create a vector of 10,000 length. As you see, the length of this is 10,000. It's going from 0 to 999. One hot encoding we have studied during the get dummies method. Wherever, for one hot encoding for man was given the index 5,000. So what will happen is that index location 5,000, number 1 would be there. And at all other index locations, zeros are there. If woman is given the one hot encoding value as 9,000, only at index location 9,001 is there. Rest all places it is 0. So in this way, I have 10,000 words, uh, 10,000 total unique words. But in my corpus, let's say just like man, woman, so on and so forth, I have 500 words. So do you agree that there will be 500 such vertical vectors, each vector of length 10,000? Agree karte ho? If I say there are 500 such words, then there will be 500 such vectors, each of length 10,000, right? Do you also agree that if you look into this particular vector, all the values are zero except at one position? If you look at this vector, all the values are zero except at one position. So if I have 500 such vectors, then can I say that there will be exactly 500 places where the number 1 will be there, rest all are zero? Agree? What I want to say is we are storing a lot of redundant information. The matrix is sparse. You have a matrix of 500 cross 10,000 where most of the values are zero. So you are wasting a lot of computational power. So this is a sparse matrix and it's a huge matrix. Now, what does word embedding do? How does it solve the problem? So, word embedding is going to extract features. How that you talk about later, right now, just think about it. Listen to me like a fairy tale. So let's say what is word embedding going to do is it says, Darshan, you have 500 words, right? I say yes. It starts writing all the 500 words. And it also starts writing their encoded value. So this was 5,000, this was 9,000. So all these 500 words and their values are written down. So let's say that boy was given an index of 2,000, girl is given 5,000. Of course, man is also 5,000. So that's a mistake from my side. Just imagine that this man was having some other value. So every word and its one hot encoded value is given over here. Now it starts extracting features with the help of the neural network. How does that happen is the first feature, let's say, which it extracts, the first feature which it extracts is a gender. The first feature which it extracts is a gender. So, is the gender relevant in case of boy? Yes. So, let's say it assigns a value of -1. Is the gender relevant in case of girl? Yes. It assigns a value opposite to that. Let's say +1. It's not a guarantee that it will assign -1 or 1. This is just a story. Is the gender relevant in king? Of course, yes. I'm giving a gender value of -0.93. Queen is +0.92. But now tell me, is there gender among apple and fruits, apple and mango? Does fruits have a gender? She apple, he mango. Do fruits have gender? No, right? Because gender feature is not relevant in fruits, it assigns a value close to 0. Wherever it is relevant, it assigns value close to 1, else it assigns value close to 0. So if you look at this, the next is the royal feature. So in the royal feature, F2, boy. Is a boy royal? Huh. No one cares about a boy. Not. I gave a small number. Is a girl royal? No. Is a king royal? Of course, yes. Is a queen royal? Yes. So high values are given. Is apple royal? No. Mango is the king of fruit. So is it royal? I have given it not a value as high as king or queen, but I have given it a relatively higher value. Then let's say last one. It extracts age as a feature. Age does not matter in boy or girl. Who cares? But in king and queen, age matters, right? Who will rule the kingdom after them? But what matters more with respect to age is the age of fruits, right? Because they are perishable items, so they are given very high values, much higher than king, queen, and boy, girl. In this way, let's say it extracts around 300 features. In this way, let's say it extracts around 300 features. Now one very important observation, if you noted, if you look over here, this matrix was 500 cross 10,000 with all the values being almost zero. This matrix is 300 cross 500. Why? Because 300 features are extracted and there are 500 words. This is small, yes, and the more and none of the values are zero. I mean, most of the values are as good as non-zero. This is what is the idea behind it. This is what we understand from this. So word embedding is converting a vector to another vector using neural networks. And you know what? If you are very happy about it, that okay, fine. In this particular case, uh, I would like to see the gender, royal, and all these features. If you want to see that, it is not going to show you. This is just a story. You know what will happen when you ask it to extract features? You will be getting as output the contents of this white box. It will not tell that, hey, it's gender royal. Machine doesn't understand that it was accepting numbers. It will give you the numbers. So these all things will make purely no sense to you. These all things will make purely no sense to you. That is what is important to understand. So word embedding is about converting a high dimensional matrix to a low dimensional matrix, sparse matrix to a dense matrix, so that the neural network is reduced with the data given for computation. So it is faster. That is why word embedding is used. And so if you see over here, I'm giving it the total number of words, which we know is around somewhere around 8,000. I say that, hey, I'm giving you all the 8,000 words. I know you are going to do one hot encoding on that. And after that, you'll be getting a dense and a sparse matrix. Sorry, a huge and a sparse matrix. Then you do the word embedding and extract 100 features and add it to the model. And then those features are sent to LSTM, further sent to next LSTM, further send to next LSTM, sorry, the output layer, and you get the output, and that is how it works. Are you understanding what is word embedding now? It's a neural network technique to extract the features, and at the output, you will only give inputs as number and get the outputs also as number. It is a neural network in the backend. Absolutely not, Sutanu. Absolutely not. And it's not required. In fact, no one knows it, to be very honest. Tell me logically, Sutanu, that we implemented the MNIST problem. Can you solve it using pen and paper? Can you solve the MNIST problem using pen and paper as to how it predicted the digit? Is it possible? Is it possible for you to solve the MNIST problem? These 8,000 are given to the hidden layer. That hidden layer goes to next hidden layer. That hidden layer goes to next hidden layer. And at the last, the output layer will have exactly how many? 100 neurons. And these are the 100 features. That is how it happens. So it is a neural network only which is getting implemented. And the weights are nothing but the trained one. That is the concept behind it. You just can't think of even looking at one pass of it. Is that making sense to you that it is nothing but a neural network in place? What is the input? Our input sequences. Sutano, that's not fair. What is the input? Our total words are the inputs. Input length is the input, right? So we created a model. Embedding is going to get the total number of words, and that is what is passed ahead. That's the input. Right. So it is essentially the output from the n-gram only, which is saved into the input sequences. Here is for feature extraction. Does it use CNN kind of network? No, it uses a basic neural network. It doesn't use CNN. It uses artificial neural network, the one which we studied before CNN, or the CNN consists of two parts, CNN and ANN. So it is ANN only in this case, Nagdeep. And let's quench your thirst. Let's say I don't know word embedding. Let's say, I am just completely bluffing around word embedding. So I say that I just understood what is word embedding. It is a way to convert high dimensional and sparse metrics into low dimensional and dense metrics. But now I am very curious to know, how is the training of word embedding model happening at a conceptual level? Please help me out with that. Now let's look at the complexity. My MacBook's fan has started by the time this is working on it. My God, my this is taking a lot of energy. My laptop is dissipating heat like anything from the back, from the front. Oh my God, it's 8:56. It's that hot. Anyways, coming to the point. This takes 1 hour to execute. That is for sure. Almost 1 hour. One more thing, if you see over here, till this point of time, we understood the code. Then from TensorFlow, I'm importing early stopping. Early stopping, I have already explained you what is early stopping responsible for. And model checkpoint is to save the best weights of the model. So if you see over here, I'm creating an object of model checkpoint, and I'm going to save the model weights by model weight.keras. If it's running on Google Colab.h5, save best only is equal to true. So over here, I want to say over here that if you see the save best only, it means only true save this. Well, other values that can be used, that save best only can take, are false or none, where false means all the weights are saved and none means also all the weights are saved. Going on to the next one is, I'm asking it to monitor the loss, which means the loss is monitored and the mode is, the loss is minimized. 9, right? So 27, 37, 47, 48, 48 minutes, 48 minutes, 47.11 precisely. We got an output of 84% accuracy, and this is on the train data. On the train data. Okay. Then I say, let us plot the model accuracy. So as usual, I can see, I'll be plotting the history and the functions. So over here, we all know history is nothing but the history object, and string is the parameter that we want to plot. So here, whatever object we want to plot, we can plot it. And then we have the epochs versus the y label will be the string. So I want to plot over here the accuracy. So history and accuracy are being plotted. That's good. And here is the loss. That also looks nice. But now it's time for us to do the same thing on the unseen data. So how to do this on the unseen data? Now this is the last cell. This is the last cell over here. Now, there are two versions of it. No, over here there is only one version. Let me tell you, what am I giving a call to? This is the call that we gave. I'm gonna comment it out. So the call that we gave was this. So what is happening because of this is your seed text is implementation of the number of words to do that is this model is the model and the max sequence length is 40, right? So you can understand what am I passing. The seed text is implementation of. So here I'm saying the seed text is implementation of. Okay. Then for I in range of next words. So obviously over here, this is going to take the values 0 and 1. Initially it is 0. So tokenizer dot text to sequences. So what is that going to do? The tokenizer has already fit on it. So it will be converting that into tokens. So everything will be given a number. So implementation of will be given a number. So I can say over here that it will convert the seed text into numbers. Then after that, obviously you have to make it of the same length, that is 40 for padding. So it will be padding the sequence to make it 40. Max length is the max length minus 1 because one extra was added for out of vocabulary. So that will be gone and padding is free. And then I am going to ask the model that predict the next word. So given implementation of, it is going to predict the next word. So what will happen over here is over here, our neural network's last layer consists of total words. And total words is the total number of unique words, 8,000. There are 8,000 neurons in the output layer, 8,000. So out of those 8,000, I want it to choose the maximum. So that is choose the word with the highest probability. This one, 8238. So 38 words. Choose the word with the highest probability. That is what is done. Argmax does that. And output word is empty. So I say for word, comma, index in tokenizer dot word index dot item. So basically, what is predicted is a number. Do we want to print the number? No, we want to print the text. And that is exactly where we need to understand the things. So I say, in this case, for word, comma, index in word index dot tokenizer. So I'm going to each and every word index which I already have created. And then I'm saying that if the index is equal to the index of the word, that is whatever is predicted, then output word will be that word. So output word will be that word. So what will happen over here is, so here I say, is my prediction actually covering them? Is the prediction is covering them? That is, if the index is equal to the index of the total number of classes, then the word will be the output word and thereafter you break it. But if this condition is not satisfied, then that means further more words are yet to be generated. And in our case, obviously, we have not reached that. So what will I say? That seed text will be is equal to seed text plus this. So assume over here that our output word is the next word in the sequence, and that is equal to, we give implementation of, and it predicted deep. So what will happen over here is, now when I say seed text plus this, so implementation of will become implementation of deep. That is the original one is added deep now. And this seed text is now, we went to the next iteration. The next iteration, my seed text will be implementation of deep. And I'm into the next epoch. So again, padding it, model prediction, choosing the maximum, output word is maximum. And thereafter I check, is the word comma index in this? So basically, is that word available? Because we have to convert it back from numbers to English. And that is what I'm saying, that, okay, if you find that index of that particular class, then I want you to take that number and convert it to the equivalent English word. And if it is found out, then break. So break will be now breaking the for loop, and it will be returning the seed text dot title. And that is why when I give a call to implementation of, now you can see what it predicts this time. Let's see. Oh my God. Oh yeah, I didn't run this, no? Right. So this is good. I run this. Implementation of RN and LSTM, and the second one for predicting forwards, it says implementation of RN and LSTM and this. If I say implementation of RN and LSTM, and could you predict the next 10 words? Implementation of RN and LSTM and GRU SageMaker to Saturn, Cloud, and Mapping. And if I say, could you please predict the next 20 words, it will do that also. In government models, part 2 UX, data set for school. But if I say how to, and I'm saying model and this, so earlier it predicted use the time before median learn. Now it is saying how to use Google Maps properly, companies on free. Earlier, when I say forecasting and asked it to predict the next 7 words, it predicted forecasting and future prices of cryptocurrency using historical data. Now also the same thing. Data and next 3 words. It was data science recruitment. Now it predicted data science productionization scale. Deep learning is it was a budget earlier, is a full. And that is how it happens. And now, well, so save the model on the disk. So below code will work in Google Colab. And to save the model locally, you will have to write .keras. So when I run it, you will see the model over here. What is the name of the model? TextGenerator.keras. Let's see that. This is the one. And that's what you see, which can be further used for deployment. This is what we understand over here. And thus we complete with this case study. 100% done. So the data and everything with you, and you understand a lot of things which are mentioned over here. And now I would like to ask you, if in case you have any kind of questions, you want to have access of my notebook, you can have access of my notebook as well. How also, that I will tell you. If you paste this link in your browser, this will open. Then you need not click on open in VS Code. You click on continue in web. And then at the bottom, it will ask you continue as anonymous. You can click on that. And then give it your name. So I am giving my name as Dr. Darshan English, so that I'll come to know who is on my notebook. And you will be able to see my VS Code on your system. You can see same thing, everything which is there. You can see everything on your system. What is the agenda of today's thing? Even before I discuss the agenda, I would like to tell you the RN and the number of previous words they number. RNN is around 7 to 10 words. LSTM was somewhere around 70 to 75 words. GRU is somewhere around 70 to 80 words. Then, for the first time, we are going to explore attention mechanism. It can remember around shock laga. It's shocking and transformer almost infinite. So today we are going to talk about these two things today. That's my today's agenda. Right? Yeah. So now, what all things are we going to study? Here, we need to understand what attention mechanism. It is nothing but it is something which is built using LSTM or GRU. Yes. So basically, using these two, either this or this, attention mechanism is built. And using attention mechanism, transformer architecture is built. So it's all built on the top of each other. So this attention mechanism basically comprises of two components. One is called as the encoder and the second is called as the decoder. Now, in each of the cases, there will be training and testing. Here also training and testing. So here training and testing both are same. Here training and testing both are different. Now you'll be like how? थोड़ा patience रखना पड़ेगा आपको. You'll have to stay a little bit patience with patience to understand why am I saying so. But overall, memorize this content which I have written down. Ultimately, in the worst case, even if you don't understand the architecture, you should not forget the slide. It is okay if in worst case you say, sir, I forgot the architecture, but you cannot afford to forget this. Revise. Okay, going ahead. Now, friends, let us get started with it. So, see, a recurrent neural network, or more precisely, LSTM or gated recurrent units, they were found to be very effective in solving complex sequence related problems given a large amount of data. In the previous case study only we saw that, and that makes me recall, be very honest and type I did or I did not execute the case study which I shared you. Text generation using LSTM. Be very honest and answer me this in the chat box. I did or I did not. That's cheating. How about you should have done it in the morning only? How much time is done, Chandra? Most of them are saying I did not, but yes, I see some of them saying I did also. 2 minutes per epoch, so 100 minutes is what you will require. Are you connected to the GPU or CPU? GPU, okay. Nagdeep says I could not. You could not? Are you getting any error? Error is not there. What do you mean by I could not? Then you say I did not. Now, why are you unnecessarily putting anything in the chat? Misguiding me, huh? Could not do today. So I asked you to reply with I did or I did not. I could not. I thought that you're getting some error. Oh, huh? I started. Okay, okay. You started, but laptop got hanged. Oh, just give me 10 seconds. I'll be back. Hey, hey, sorry. Actually, since last 2 days, my I don't know what's wrong, but this lip here, there's a cut and it's bleeding from there. And when it gets dry and if I stretch it, then it again that cut is opening. So it is paining over there. It was all good. All of a sudden it started. So I just applied some cream over there. Else I would not be able to speak only. So I was saying this RNN, or more precisely LSTMs, they're found to be very effective in solving the recurrent sequence related problems given a large amount of data. So that is the reason if you look at the applications of them, they are very widely used in speech recognition. They are used in natural language processing. They are used in time series forecasting, etc. And among all, the special class of RNN architecture where it is mainly used is for solving sequence to sequence type of problems. And when I say sequence to sequence type of problems, it's not compulsory always for sequence to sequence, but mainly for that. And sequence can be considered as this, as you can see, right? So I'm talking about machine translation. It's there in one language, converted to another language, sequence to sequence example. Second example can be text summarization. So you have a big text. Analyst should have six main characteristics. One should master all of this, one, two, three, four, five, six. And this is the summary of that. And the third is where you have the chatbot. Yeah, it's written here only. Chatbot. How are you doing today? I'm doing well. Thank you, etc., things. Yes. Now, the purpose of this particular session is mainly to explain you how this sequence to sequence models are built and to give you an intuitive understanding of it on how they solve the complex tasks over there. So I am going to take this example, machine translation, and I'll be taking the example of English to Marathi. Before you start putting in the chat, I don't know Hindi, I don't know Marathi, relax. Okay, I know that everyone doesn't know every language. That's completely okay. But this is the problem that we'll be going through, translating one language to another, English to Marathi. And I am having some prerequisites for this session. So the first is I expect the learners to be familiar with the concepts of machine learning. Second, familiar with the concept of neural network. Third, at least the high school level linear algebra. Fourth, high school level knowledge of probability. Fifth, LSTM and GRU. At least looking at this architecture, you should know that LSTM has total 3 gates and GRU has 2 gates. Also, one more thing, LSTM has two internal states, hidden state and cell state, and GRU has one internal state, which is the hidden state. Among these all, the most important thing right now is you make a note of this. LSTM has two internal states, HI and CI. GRU has one internal state, HI. So I want you to memorize this. Memorize this right now after this. Now I am going to get ahead into the encoder-decoder architecture. I told you that it requires two things. So listen to this. The most common architecture for building a sequence to sequence model is called as the encoder-decoder architecture. And what I am going to give you on this slide is a very high level overview of this PPT. So, number one, who is this encoder? Who is this decoder? So, if you don't know that, you don't know this. Point number one. So, encoder is LSTM only. Decoder is also LSTM. Or sometimes they also use encoder as GRU and decoder also as GRU. Essentially, they are the same. As I told you, they are built on the top of it. Then, what is the job of encoder? The job of encoder is mainly to read the input sequence. So basically, I will be assuming that let's say I have a machine translation problem where I have lot of sentences, English and Marathi. So the English sentence is what is given as input over here. So let's assume the English sentence number 0 is Rahul is a good boy. That is given over here as input. Now we have seen using RNN that there is an internal state and the loop which goes on and processes the same input again and again. You recollect that, no? Loop where I showed you, right? This input goes, the output comes, this goes on. So when X0 goes, O0 comes as output, then X1 goes, O1 comes as output, very nice. Then X2 goes, O3 comes as output, then let's say X4 goes, then O4 comes as output, then let's say X5 goes, then after that there is no X6, so this O5 is sent ahead as Y hat, right? So this O5 comes over here and then there are weights and biases, etc. So this English sentence is given as input and encoder accepts it. And after accepting this information, the encoder is going to do summarization. So this English sentence, Rahul is a good boy, is summarized. And you know what you get as input, what you get are internal states. So let's say if you are using LSTM, then how many internal states are there in LSTM? How many internal states are there in LSTM? Can you tell me what are they? I asked you to memorize. What are they? Very nice. HIM, super. So first and foremost thing, huh? Before you think that does the encoder understand English, answer is no. Here you have the word embedding layer, which we discussed yesterday. So first and foremost thing, your English sentence, Rahul is a good boy, is gone for text pre-processing, which you have studied during the NLP class. After doing the text pre-processing, there is count vectorizer, which you also studied during the NLP class, which is going to convert that text to numbers. And that numbers are given to word embedding to make it in a compressed form, which is a dense and a low dimensional matrix. All these things happen before giving it to the encoder, just like it happened during any of the earlier projects of NLP. Do you recollect all those things? Text pre-processing and then sending it ahead? Yes. Now you also recall our day one, where you were like, generative AI, can you start with that? Now you try to connect the dots. On the day one itself, I would have started talking about this architecture. I think in 2, 3 weeks, all of you might have lost interest on the course because you are not understanding the things. And now that you know the fundamentals, connecting dots is going to be really seamless for all of you. So this is the strong base which is going to help you. Okay. So English sentence converted to vectors. I will just say like this. Listen to whenever I say English sentence is converted to vectors, by default, understand that text pre-processing is done, stemming, lemmatization, blah, 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 blah. All these things are done. Count vectorizer is applied, and then word embedding is applied, and it is converted. So when the sentence is vector, these all things are going to be always by default. After this, I will not tell this entire story what happens over here. So encoder takes that, summarizes it. Now, this all happens in terms of numbers for the encoder. It's not English, vectors. Summarization of vector is done, and what you get is the internal state vector, which is nothing but the hidden state and the cell state. So H is called as the hidden state, and C is called as the cell state. So, how is this? Just to give you a little bit more idea about this, keep this figure in mind. This is your recurrent neural network. Very basic, just a tanh activation function. Till this point of time, we have never used tanh. Here you see that. The center one is the LSTM. You have the cell state and the hidden state. This is a time instant t minus 1. This is a time instant t. Can't see? What are you saying? Okay, okay. Quite surprising. Let me do that. Patience. Yeah, I'm sure now you can see it. Great. Thank you. So here, RNN, as you can see, there is only and only one internal state, and you can see you have the tanh as the activation constant, which we have never seen earlier. This is this LSTM, where you have the cell state and the hidden state. At time instant t, this is at the older time instant t minus 1. Two internal states. Information basically in LSTM. Remember the one more thing. I never explained the architecture, but whatever is required, I'm telling you. The memory of the network is this cell state. What all information has to be remembered is saved over here in terms of pure vectors. And history is for deciding how much of the past information to be added to the cell state. And here in GRU, you only have the hidden state, right? So I say, I am pretty new to the concept of attention mechanism and transformer architecture. And I am trying to have a comparative analysis with respect to the number of previous words which can be remembered by the following: RNN, LSTM, GRU, attention mechanism, transformer architecture. Let's see, 5 to 10. I said 7 to 10. That's okay. LSTM 100 to 200. I said 70 to 80, right? It's 70 to 80 only. I don't know why it printed 100 to 200, but that's okay. 70, 80, 100, 200 is nothing. Attention mechanism, entire input sequence, and transformer architecture, theoretically unlimited. As simple as that. So we understood that. Now let's get back to our deck. We have it over here. So what am I talking about? First and foremost thing, one thing is very obvious that given a data set, we first divide the data into train and test. So if I would have started directly with this, your questions would have started coming from here only, that Darshan, why are we dividing it? But now you have all the things fundamentally clear. So what is being passed over here is the first sentence which is there in the training. So I can say what is being passed over here is extrain of I, where I will be 0, 1, 2, 3. Let's say you have 1,000 sentences. So this is going to be 799. This goes from 800 to 999, assuming that I have gone for a 80-20 split. So the first sentence, 0th sentence, Rahul is a good boy, is sent. Then summarization happens. You get the hidden state and the cell state. Now, in the LSTM, the network also gives the output. The network over here, it also gives the output, and that output is discarded, and only the internal states are sent out. Now, what does the decoder do? The decoder is going to take up the internal state as the input, and then they will also take the corresponding Y train 0. Do That's it. So understand relationship between X train, Y train. And this is not only with respect to the 0th sentence. First 0th sentence will go, then second, then third, and all of this. So this is what is training is happening, and what will be done with the output is discarded. And obviously, just like here, this give internal state because this is also an LSTM. So this will also give HI and CI. Again, they will be discarded. Also, you'll see that if decoder is going to receive some input, then encoder will also might be receiving some input. So here we try to feed 0 vectors over here because you cannot leave it empty. And this is what happens in the training. Learning of the relationship happens between X train and Y train. Then after that, coming on with the unseen data. Now what happens? The first row, which is this X test of I given. What happens? Same stuff. What do you get over here? Internal states. They are given as input to the decoder, and decoder is going to use them to get the output. Again, in this case, HI and CI are discarded. Here also as input, what goes are 0 vectors. So in this way, what happens is this output, this output. So this output is here. So this is the actual. In this way, you get a lot of values in predicted. So then the actual and predicted are compared and the model is evaluated. Same funda that we learned in machine learning, as well as deep learning, as well as NLP. But now these things are happening with the encoder. Also, you might have seen that here, I also said one thing in encoder, training and inference, that is the prediction. Both are doing the same job, which is summarized. But here, both are doing a different job. In training, you are actually understanding the relationship between X train, Y train. And while testing, you are predicting on X test. So decoder is functioning differently while training and while testing, whereas encoder is doing the same job over here. This is the high level understanding so far, which will be required, because after this, what is important for us to understand is what is actually there in this box and what is there in this box. So let us quickly revise what I just said. Number one, Our problem is converting English to Marathi. We divide the data into train and test. First English sentence given as input, converted to vectors. You know what happens over here. Encoder will do summarization. Encoder and decoder both are LSTM or both are GRU. In this case, I'm assuming LSTM. I have underlined that. They summarize the vectors and they give internal state vectors. They are given as input to the decoder, and then decoder understands the relationship between that vector and the Y train, and that goes without saying that your Y train as well will be going for word embedding, and then understanding happens between these two. Then the same thing happens for all the sentences. Then while inference, what is happening is the first unseen sentence is given as input. Encoder does the same job that it did during training. It will summarize it and get the internal state vectors done. And then using this internal state vectors, it will predict the output. So the output was discarded during training, but during testing, output is important. Also, one more thing, this internal state vector is also called as context vector or thought vector. So we see decoder is taking different approach while training and testing. Encoder is taking the same approach while training and testing. Revise this slide. Then after that, next thing over here is demystifying. This is a very high level overview. Now we get into this. So I am over here into the encoder LSTM, and for your kind information, right now we are talking about training. In testing also same thing happens. Okay. So when you talk about the encoder LSTM, so here what are we having, right? So if you see the LSTM is reading one sequence after other at a time. So if your sequence is of a length k, then you can think of it as it is going to get over in k iterations. So here this xi can be considered as the input sequence. Your hi and ci can be considered as the LSTM's states. Combined together, we call it as the internal states. And yi is called as the output sequence. So one more thing, technically, your xi, hi, ci, yi, they are what? They are actually vectors of floating point numbers, as we know, right? Now let's try to map all of this in the context of our problem. So if you recall, our problem is to translate English sentence into Marathi equivalent. So for the purpose of this, I am trying to consider a input sentence like this. So my input sentence in English, I am considering Rahul is a good boy. And the equivalent Marathi translation turns out to be Rahul, which is Rahul, Changla, which means good, Mulga, which means boy, Ahe, which means is. Ahe means is. Rahul Changla Mulga Ahe. This is what it means. Rahul is a good boy means Rahul, Changla, which means good, Mulga, which means boy, Ahe, which means is. Right, so this is one thing. Now, whenever you talk about this, this can be considered. This problem, as we know, it is a problem of sequence to sequence. Sequence to sequence is also of two types. The one is which is called as word level neural machine translation, and the next is the character level neural machine translation. So when I say word level neural machine translation, basically it will consider Rahul as a word, is as a word, O as a word, good as a word, boy as a word. So this sentence is considered to be 5 words. But when I say character level, then R, A, H, U, L, space, I, S, space, O, and so on. So char level NLP will consider this as a 19 character problem, whereas word level NLP will consider it as a 5 word problem. Now, here in this case, I am going to go ahead with word level NMT because this is more popular when you talk about any real life application. So we will be going for word level NLP, and because of that, I can say that Now my input is Rahul. So what is happening is we are having Rahul as input. My dear friends, don't forget this. So English word is converted to vectors and given as input. Okay, now what happens over here is these two things are added, right? So obviously here there is X, there will be some weight, let's call it as W and some bias. So what will be happening over here is W into X1 plus B, and here also you have H0 C0. So that will be again internal states coming over here. There will be some weights and there will be some biases. So that also W into X plus B. So this is there and this is coming some input from here. Some input is coming from here. Both of these are added. Some activation function is applied and this actually happens inside the encoder. So it's not truly just a neural network. It is the encoder architecture. So both of these things are added and it gives me what? It gives me an output Y1 and H1C1. Now this H1C1 is sent ahead because it's a recurrent neural network. Now X2 goes, these two are added and activation function is applied and the output is Y1 and H2C2. H2C2 is given ahead. Understanding happens between X3 and this H3C3 and Y3. Similarly here also H4C4 and Y4. Similarly here also. Now what will happen? H5C5 and Y5. Now, we don't need Y1, Y2, Y3, Y4, Y5. Why? See, what are we doing in the training? In the training, what are we trying to do right now? I'm just trying to summarize the sentence. What will I do with the output? It's of no use to me. So, over here, everything is converted and these things are no use to me. And I get H5C5. Now, you might be thinking, what is this? See, I'll tell you what is basically there over here. Now, in simple words, what is HI and CI? So basically this hidden states, remember what the LSTM has read, or I can say learned till now. If I say what is H3C3? H3C3 is summary of Rahul is a. What is H2C2? H2C2 is summary of Rahul is. What is H5C5? H5C5 is summary of entire input sentence, which is ideally called as input sequence. So that is the thing. Then, now at this point of time, we understand H1C1 is the summary of Rahul. H2C2 is summary of Rahul is. H5C5 is summary of Rahul is a good boy. The question over here which might come to your mind is, Darshan, what is H0C0? What is this summary of? Ideally nothing. So therefore, they are mostly in most of the cases, they are initialized to zero or using some random methods, right? That's something which is important. And again, our whys also, I am going to discard it. And see, it's not that you always discard it. It depends on the problem that you are trying to solve. Sometimes it is kept, sometimes it is discarded. Logically, in our case, we have nothing to output unless we have read the entire English sentence. Because after the model understands the complete sentence, then only it will generate the translation for it. So before understanding the sentence, how to generate the translation? Therefore, we are discarding the why, right? Therefore, we are discarding the why. What do you mean by summary over here? Can I give an example? No, I can't give an example. I can't give an example. Summary is summary only. So it can be anything. It can be anything. So unfortunately, is there a perfect example of this? The answer to that is no. There is no way I can tell you that when an encoder is summarizing a sentence like Rahul is a good boy, what do you exactly mean by summarization? But I can give you a very brief understanding over here is it will compress your sentence into something which is called as a fixed length representation. Like for example, in your NLP also you converted everything to numbers. Then you went to word embedding. Word embedding is going to give you different lengths. And then you pad everything to become of the same length. So the same thing happens when I say summarization is going to happen. So initially the sentence, Rahul is a good boy, it will be tokenized. So Rahul is a good boy. Tokenization happens. Then you send it to the word embedding layer. So word embedding layer could be word to vec or what we understood yesterday, where extraction of the features and all these things are happen. And then after that, it will find the small vector values of it, as I told you. So basically, you will get a very, you'll get a vector which is purely consisting of numbers. So essentially, we can say summarization means it is not truly compressing, but it is converting that to the vector form, where semantically, in terms of human beings, we can say that now it understands is what kind of person he is. It understands who is the subject. It understands what is the description, like the description is good boy. Then it understands the contextual dependencies, that is good is talking about boy, and it also understands synonyms. So when I say synonyms over here, it is basically the generalization that okay, is a nice kid. So it is similar to that, right? So Rahul is a good boy, same as Rahul is a nice kid. So basically, machine is converting it into a format which will be easy for it to interpret, and that is nothing but called as summarization, which is compressing it into fixed length representation so that the model understands and captures the context, relationships, and the semantics in between the two. That's the best we can think of, right? Cool. So this is what we have. After this, we have H5, C5, which are the final states of the LSTM. Now, see, YIs we discarded, X taken, we get H5, C5, and this is what is called as encoder LSTM training. Now, this is ideally given what? All the sentences in the extrain one by one, right? Then here we talk about so bad. I hate it when spelling mistakes happen. Decoder, LSTM, and I'm still talking about what here. Now, what happens? The previous slide gave me H5, C5, which was the summary of the entire input sentence. So that H5, C5 goes over here. H5, C5 goes over here. So basically, the output of encoder becomes the input of decoder. They are over here. Now the model has received the summary. Now what we do? Going back. For some reason, I add two tokens, start and end, before and after the sentence. Now you'll be like, but why are you adding it, Darshan? Any practical significance of it? Of course, there is a practical significance, but right now it's not important, so I'm not telling it. So I had start and end. So my sentence became start Rahul, end. All of this we will be doing it in our code also. So better be attentive over here. Okay, everything is going to be done in our code. So this is received H0 C0. Now our output sentence was what? Start Rahul Changla Mulga. So obviously that goes without saying that this is going to be a word embedding layer. The token start is converted into vectors and made available over here, and then these things get added and understanding of the relationship happens. In return, and you get H1, C1 and Y1. Now, very important thing, right? So there is a very important concept over here, which is called as teacher forcing. Now, what is this concept of teacher forcing? So recall what we used to do so far. In the sense, we used to have this input X1 goes, output is not sent ahead, output comes here. This goes, next input goes X2, and this O1 goes and gives the output O2. X3 and O2 comes mixed inside, and you get O3. Then let's say I said X4 goes, O3 goes, you get O4. Then let's say there is nothing after X5, X5 goes, O4 goes, you get O5, which is sent along this, and you get Y predicted. Now, what is the thing? Remember, very important point I'm telling. That's why I'm setting up so much of TRP. The output, the output is given as input. The output is given as input. That's what was the one of the very important point which I want to say. But there is a small problem in this approach. It's not that it's bad approach, but there is a small problem in this approach, and that's exactly what we are trying to understand when I say. Now, I want you to think about it from the very logical slide where, let's say, I'm just randomly searching for a poem on grandparents. Now, imagine you are a small boy, or there is some small boy in your family who is just somewhere around 5 years old, and the task over here is to memorize this poem because he has to speak in front of everyone in the school for the assembly. Right? So let's say the task is to memorize this poem. Now there are two ways a parent can teach this poem. The first one, listen to this very carefully. I'm going to ask you a follow-up question on it. The first one is, let's say the kid name is Krish, or let's say Krishna. The kid name is Krishna. I say, Krishna, go and study this poem. Put your heart into it and memorize this poem, right? Yeah. So I say the first way. The first way over here is essentially where I say that, okay, Krishna, go and memorize this poem. He goes, he takes a good amount of time. Let's say he takes around 3 hours of time, and he comes and says that, okay, Papa, I'm ready. Okay, I say, okay, start speaking. And he starts speaking. So now see what poem is he telling me? Obviously, there are going to be mistakes. He's a small kid, and what he tells me is like this. He says, from early in morning until I go sleep, day. I know my grandparents love me in very special way. Sometimes it is tea and crackers. Sometimes it is just hug when I am scared and in the dark. I love to hear their stories about the past, and I know their hearts are filled for me with never love. Now, I am hearing to him. Okay, that's nice. Okay, Krishna, okay, that's nice. You missed out a few words. And I tell Krishna that, hey, you know what? You missed out the word though here, each day here, oh here. And you missed out this, you missed out this, and you also missed out this. Okay, and Krishna is confused. Okay, fine. He's just a 5 year boy, right? So it's like okay, he has done some project, and I'm now finding and telling him that okay, these all are the lacunas in the project. Okay, that's done. That's approach number one. Second approach, which his father took, is this. You have to tell me which approach is better. So I said, okay, Krishna, you're done studying. He says, yes, Papa, I'm done studying. Start narrating. He says, from early in the morning until I go sleep. I said, no, Krishna, wait, not sleep. Until I go to sleep. Okay. Until I go to sleep each day, I know my grandparents, me. I said, no, Krishna, I know my grandparents love me in a very special way. Sometimes it is tea and crackers, sometimes a walk in the park, sometimes it is just a hug when I'm scared and in the dark. How is this approach different from the earlier approach? Is whenever Krishna is going wrong, his father, unlike the previous example where the father was hearing patiently and giving the opinion at the end as a summary report to Krishna, here the father is helping him to correct the mistake there and then according to your logical understanding among approach 1 and 2, which is the best approach for a student to understand. Approach 1 where you give the summary at the end, or approach 2. This is exactly what is called as teacher forcing. In very layman terms, this is called as teacher forcing. I'll let you know now. So, what is teacher forcing? Teacher forcing is when Krishna was narrating the poem. and he missed out a word. His father immediately didn't allow him to go off the track and then gave him the summary. He was going little bit off the track. His father immediately held him. Hey, Krishna, no, not like that. Each day. And then he continued. And then his father, like, no, Krishna. So his father was giving him immediate assistance. His father was giving him immediate assistance. And that is why Krishna was not going off the track. Else, let's say Krishna went off the track by missing this word, it might have happened that after that he goes off the track and directly comes here, and then after that he says this and finish. Why? Because Gadi Patri se once the train is derailed, it can enter into anyone's field. So it is important that you take actions at the right time. Essentially, what is teacher forcing? This is exactly what is teacher forcing, where a teacher is guiding the student periodically and not allowing him to go off the track because he is there to give the live assistance. So, see, it is not that in the case of memorizing this poem, that with the approach which father one took versus father two, it is not that the first Krishna will not be able to learn using the first way. He will be able to learn. But first time he tells the poem to his father, father gives him a summary where he went wrong. He goes and studies, again tells the poem to the father. Father again gives a summary that this time you're wrong here. This happens again and again. And every time this guy was going off the track, slowly, steadily, he will come on the track. Whereas in the second case, because you are getting real-time assistance from the father, your learning is faster. So maybe the way one approach would have taken Krishna, let's say 7 hours to learn a poem. The way two approach is going to take maybe 2 hours for Krishna to learn the poem. Do you agree that way one is taking 7 hours and way two is taking just 2 hours? Mota mota, roughly. I just said roughly, right? Time required in second approach will be less as compared to the first approach, correct? Don't agree? You slept or what? If you sleep, then even I will start sleeping because it is only because you are connected. I have that energy to speak, else my energy goes off, my voice goes down, and you will see me just explaining it for the sake of explaining. It's theory topic, it becomes very boring. So if you are not going to respond over the chats, then automatically it happens. I'm not saying that I will do it forcefully. Human nature. Like no one is listening, let me do it. Okay, fine. As somehow I will complete the topic. If you want that kind of teaching, then don't then your approach is good. Don't reply in the chat. So you are also not disinterested. You are also disinterested. I am also disinterested. We'll look at the clock. 10 o'clock over. Okay, guys. Bye. Good night. Or you show the engagement so that I will feel motivated and I will give you even better. So this is in your favor. You should know how to basically, if you are riding a horse, you should know how to control him. So I am the horse over here. You are riding me. So better control me in the right way. Cool. Let's go ahead. Okay. Basically, don't allow me to sleep and don't you also sleep. So basically, give engagement. So if my student only is not interested in learning, then as a teacher, I'll be like, fine, his father has sent me. Let me do time pass for 2 hours. After that, he will go home. But if he is interested, automatically I have that sense of belonging. I have that sense of responsibility that, okay, let me make him as best as me. So you take that decision going ahead. Teacher forcing. It is a method for quickly and efficiently training recurrent neural network models which use the ground truth from the prior time step as the input. What it means is, here, have a look at this. Mary had a little lamb whose fleece was as white as snow. So obviously you append start and end as I told you. So given the word start as input, it is expected to predict Mary. But Krishna predicted, oh, Hare Krishna, you skip the word at the start only. No problem. So what will happen if you remember whatever thing you give as input and that comes as output, that output is again given as input. That means this A is given as input now. So the input is start A now. This is the input. And using this input, what it will predict, it may happen that it predicted whose. Ideally, it was expected to predict had as the second word, but it predicted whose. So next time you will give star a whose, and what it will predict, it is expected to predict, but it predicted white. But understanding the problem, because it is going offbeat, then again and again I have to rectify, and that rectification is going to take a lot of time because it is not about one sentence, but you have a million sentences. So what is teacher forcing? Teacher forcing says that, hey Darshan, you give start as input. And we expect when start is given as input, I should get the output. Now, what should I get the output? I should get the output as Mary, because the sentence is Mary had a little lamb whose dot dot. So when start is given, I expect the output to be Mary. I say that whatever be the output, whatever be the output, I don't care. Next time, as a father, the next input I'll be giving is start and marry. Expected to predict a, whatever be the output, be it a or be it anything else. Next time I will give the input as marry, start, marry, had. Whatever be the output, it's expected to be little, but whatever be the output, expected to be a, but whatever be the output, next time I will give this. Whatever be the output, next time I will give start, Mary had a little lamb. Whatever be the output, next time I will give start, Mary had a little lamb and or whose. So essentially, what am I doing is here in the previous case, here, when start was given, it predicted A. So we see that the model is going off the track and is going to get punished on every subsequent word it generates. Therefore, the learning is slower and unstable. Whereas over here, the model will learn correct sequence or more correct statistical properties quickly. So if you see over here, if I take you back, can you see the PPT? Can you see the deck? Okay, thank you. So what is going to happen in this case is teacher forcing you. So what is happening? Let me tell you. Our encoder, this is the encoder. We gave Rahul is a good boy. Summary of that is available in H5, C5. That summary is given to the decoder. Then this H0, C0 and start are given as input, and the model predicts something. So now prediction ideally is expected to be Rahul is a good boy's conversion is Rahul changla mulga. So the prediction is expected to be this. I and what we got is this. Now ideally you never get this or this. What you get are these are two vectors. So how can you confirm whether these two vectors are same or not? This is confirmed by doing cosine similarity. Let's understand this. So cosine similarity is the measure that tells you how two vectors are similar by comparing the angle in between the two. If two words are unrelated, then they have 90-degree angle. If two words are similar, they will be close to each other in the space. And that is done by converting a word to a vector. But the thing is, how is a word converted to a vector? Don't ask me word embedding. Okay. Then we find the angle, cosine angle between the two. And in simple words, imagine the vector as an arrow pointing in some direction. Cosine similarity calculates the cosine of the angle between the two arrows. When the angle is small, the arrows points in the same direction. That is, the words are similar. And then the value will be 1 or very close to 1. That means they are similar. And when they are at 90-degree, that means there is no similarity. And -1 means they are completely opposite. Let's look at an example. So imagine that you are analyzing the taste profiles of two different types of coffee on three different attributes. So acidity, body, and sweetness. So you decided to represent each coffee as a vector. So coffee A has a rating 3, 4, and 2 by 3 people. Coffee B has rating 4, 3, and 5. Now, even if the overall magnitude of the rating is different, right? So 3, 4, 2, 4, 3, 5. What matters is the cosine similarity. In this case, we want to see if the way the attributes are combined is that similar. And cosine similarity has this formula. A into B upon norm of A into norm of B. What is that? Pretty simple. So this is A, this is B. First, you find A into B. So as you can see, 3 into 4 plus 4 into 3 plus 2 into 5, 34. Done. So this is the numerator computed as A into B. Upon how is norm of A calculated? See what is A? A is 342. 342 is A. Root of 3 square plus 4 square plus 2 square is this. So this is computed. Multiplied by norm of B. What is B? B is 435. 4 square plus 3 square plus 5 square whole in root 7.09. So now I have first term, second term, third term. Just substitute A into B is 34. Norm of A is 5.39. Norm of B is this. I get this, which tells me that cosine similarity of this indicates that the two coffees are very similar. Very simple. The code is also very simple. When you execute it, you will get this output. It's saying take these two things and then I find dot of this, which is the multiplication, which is the numerator part, upon the norm formula, norm of A, norm of B, and then A into B divided by norm of A into norm of B, and that will give you the output, straightforward. And the interpretation. Can you take a simple example to make me understand how is a word converted to vector and then plotted on a two-dimensional space? You can consider a very simple example to make me understand. I can also let you know, but let me see if it is helping. Else, I will let you know. Say word embedding and all things. That's okay. I'll take a more simpler example. Let's consider. I'm saying this, I'm not liking it. I'll take my own example to make you understand. So imagine that there are two features which I'm extracting, two features. So I am having a movie recommendation system. And let's say there are only two genres of movie. Ideally, there are n number of, but I'm assuming only two so that you understand the concept. So on Netflix, there are only two genres of movie. The first is action, and the next is comedy. And this angle is 90-degree. If you talk about a movie like Avengers, Avengers has 100% action and no comedy. So let's say it gets plotted over here. So I say action is complete, comedy is zero. If you take a movie like Minions has no action, I'm assuming, and it is having comedy. So Minion, this is having comedy but no action, and this is Avengers. Now, are these movies same or different? That you can find out by finding out this. So the cosine similarity is nothing but cos of theta. In this case, the difference of angle is cos 90 is zero. Zero means they are opposites of each other or they are dissimilar. Zero means they are dissimilar. Minions and Avengers, they are dissimilar. On the other hand, let's say there is a movie like Iron Man. So Iron Man is action movie. So let's say Iron Man gets plotted over here. Iron Man gets plotted over here. So now let's look at the cosine similarity, which is cos of 0 because the angle between the two is 0. So cos of 0 is 1, and that means they are similar movies. And that is how this recommendation system is working in two-dimensional space. You can imagine when you have multiple genres, action, comedy, thriller, etc., 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 and you have multiple movies, it is the same thing translated to n-dimensional space. But overall, this is the idea behind it. My pleasure. Save the screenshot. You will not find it easily anywhere on the internet. I'll share you this screenshot, and if you want the link, right? So save the screenshot. You may not find it easily anywhere. So easy, very easy to understand. All of you followed it. Excellent analogy. Very nice. That's my job, right? To make sure everyone understands how much ever complex concept it is. Great. Thank you, everyone. I was expecting today's session to go very dry, but I'm happy we are doing something exciting continuously. Okay, coming over here. So now our teacher forcing, who will forget that, right? So here, teacher forcing is like supplying the actual value rather than the predicted value. So when start was given and the summary was given, it predicted something. It's a vector.
and the actual is also vector. Just for our better understanding, I have written Rahul and Y1, but both of these are vectors. You find out the similarity in between the vectors, right? And you find out how much dissimilar they are. And let's say how much dissimilar they are, I'm quantifying in terms of errors. So your error metric can be considered. Let's say you're considering the mean squared error as the metric. Then you find out the actual minus predicted square divided by n. So here you are calculating the error by comparing actual and predicted. After that, ideally, if you recall what was happening earlier, whatever is the input, the output which it gives is given again, and this happens again and again, and then finally it goes up. So here also, if I follow the same thing, this y1 which is predicted is expected to come down. But we are not doing like that. We are doing teacher forcing. So I'm not giving y1 which is predicted, but I'm giving this actual vector here, teacher forcing. And then this H1 C1. So this relationship understanding happens. It gives H2 C2 and Y2. You compare actual and predicted, calculate how much different they are. See, if this E2 came out to be 0, that means this word and this word are the same. Correct, na? If this E2, which is the error by comparing this two, came out to be 0, that means Sangla and Y2 are the same. And if not, they are different. Whatever it be. What are we giving? We are not giving Y2, we are giving Sangla, which is the actual word here. And then the relationship building happens. It gives me S3, C3, and Y3. Now compare it, calculate E3, and this Mulga is what is given over here. Listen to this. And now something interesting. I'm not going to repeat telecast the same thing. Something new is coming. So Mulga and S3, C3, they understand the relationship H4, C4, and you get this. Compare this and you calculate the E4. Then this actual is what you give down, and then this understanding happens, and then you get Y4. Now you calculate your E5 by comparing this, and as usual, this END will be given down. Ideally, we should stop now. But how will a machine understand? The machine will understand this because of END. Why did we add start and END is for this only, so that it understands that I need to stop this loop. So this is for letting it understand you are starting it. This is for letting it understand that you are stopping it. And then obviously this will give H5, C5. Now, see, my job was just to understand the things. So in this case, I am not interested in the errors. I'm just interested in the training. So the outputs at each stage of the decoder are now going to be trained using the neural network through the back propagation and using the appropriate loss function as I discussed. H5, C5 are of no use, so we will be discarding it. And that is how the encoder does the complete training. Also at the bottom, you can see teacher forcing. The input at each time step are the actual outputs and not the predicted ones. So it's not Y1, Y2, which is given here. It is the actual outputs which are given. And this is called as teacher forcing, which helps in faster and efficient training of the network. So essentially, friends, if you recall, what we understood is the encoder and decoder, but only for training, which is the blue ink on this slide. The red ink we are still yet to understand. This is only the blue ink that we understood. Do you understand the entire thing which I just make you understood? Everyone, the training part, very nice. We are utilizing it for back propagation and reducing the loss. I said, na, here only we discussed. Na, see, read this point once again, Gurjit. Just go through it, right? You will understand it, right? Correct. Now you get it perfect. Now, trust me, if you understand this, well, you can actually be now a little confident or overconfident also that you understood the attention mechanism, because the testing part is a cakewalk. Testing part is a cakewalk. Let's understand how. Now, as Gurjit asked, where is the training happening? So you understood that here there is a continuous backward propagation. As you read this point, right? Everyone read this later on, else many people will ask the same question. Read this point once by self. Pick. So now, here I say, now that we are clear with this, we are getting into the overall thing, right? This is overall. What is this? This is the overall training. So this is the encoder. This is the decoder. Rahul is a good boy. Obviously, we know over here word embedding. These are the internal states HI and CI in place. These are the outputs YI which we discard. And what you get is the internal state vector, or it is also called as the context vector or the thought vector. Memorize this name. Internal state vector or the context vector or the thought vector. I had already written down this name earlier also. See here. And these are given as input. And then what happens is this Rahul only is given down. It predicts Sangla. And obviously there are, there will be, these are the actual, there would be predictions Y1, Y2, Y3, Y4, Y5. Teacher forcing will happen. This HICI are discarded and this YI is also discarded. And what is happening over here is back propagation in order to train the network to understand this. Now the testing part. So this is the encoder on the inference. Inference means what? Inference precisely means that I have taken a lot of efforts and continuously there has been a lot of forward and backward propagation happening. Now, if you didn't had idea of deep learning, you would have been totally lost. But now you know what is now you know what is a forward and backward pass. This keeps on happening multiple times till the loss is minimum. Now I need not explain you that what is that loss, how the training is happening, because you have that fundamentals clear. You are in a position today to understand this. So basically, if you recall with machine learning, right, if you try to understand in layman terms, what we have done is LR fit on X train and Y train. So I can say that my training is done successfully. Therefore, we can use the model for prediction. So the name of the model over here is LR. So I come to the next slide. Now what I want to do, LR, can you predict on the X test? That's essentially what I want to do. So this is the encoder part of the prediction. So what happens is, you remember previous slide where we started, I said this first unseen sentence is given as input here, input. Encoder will do the same thing. So summarization, done. And decoder will take this and directly start generating the output because the training is done. So decoder takes this and start generating the output. So what happens over here is Rahul is a good boy. Now, obviously, assume over here that this is an unseen sentence. So ideally, it has to be a sentence which has to be from the X test. Just assume that, okay, Rahul is a good boy was never seen in the training part. So Rahul is a good boy is given over here as encodings one by one. So where this is x1, x2, one by one it happens. I am not writing it in the form of a loop, but you understand how it is created. So this goes like this. It goes over here. And then, so H0, C0 are zero vectors. This goes one by one. And we know encoder is going to give us H5, C5 in this case. And we discard the thing. So this figure, basically, I have drawn in short only. And then this is given to the decoder. Essentially, recall this figure. Unseen sentence here given, summarization happens, output is discarded, and this HICI is ready. That's exactly what happened. I did not show it like this. Same thing happened. Rahul is a good boy event, and we get this. It is just that it is assumed to be an unseen sentence. So encoder did the same thing. Now you talk about the decoder for inference. So this is the one which is coming from the encoder. We save it into the decoder's initial state. Now what will the decoder do? It will do nothing. It will start generating. Now that it says that my training is over, now whatever input you give, I will generate the output for it. Right or wrong, I don't know. My training is over. Based on my understanding, I'm going to generate the output. So I give start. Obviously, start is what is supplied. And then it takes the entire summary, start, and this is the prediction. And this prediction itself, now you have nothing called as actual. We are in the prediction. One by one, it is generating. So in the text generation also, you remember implementation of was given and we asked it to predict the next word. So in the same way, it has generated one word. Now this Rahul will be given here. So this is my time step one. Now my next time step, where is time step two? Rahul is given here and H1C1 from where did this come? From the previous step here. Start given, this given, output was Rahul and H1C1. So this H1C1 comes here, Rahul comes down. Using this two, it predicted Sangla and H2C2. Next time step 3 will come. In 3, H1C1 and Sangla given. It predicted Mulga and H3C3. Now you should think over here that this process is going to repeat for how many times? Logically, when should this process stop? What does your gut feeling say? Because this H2C2 giving H3C3, H3C3 giving H4C4, H5C5, H5C6, H6C6, H7C7. That is awesome. Not necessarily 5 iterations. END, Anna. The moment this prediction comes out to be END, this should stop. That's the perfect answer to that. So here, so H3C3 and Mulga given and it predicted AHE. Because the prediction is not END, H4C4 and AHE will be given down. So at timestamp 5, H4C4 and AHE given, and now because the prediction is END, we stop. So overall, this is the inference where that's my encoder and that's my decoder, where encoder is doing the same thing to generate the internal state vector or the context vector or the thought vector. This and start. You just have to give it the seed value start, and using this two, it will generate the prediction. This prediction is given as input and this H1C1. Using this two, it will generate the prediction and so on and so forth. It will come, and because it is END, it will stop. And obviously here, whatever are the H and the C, they are discarded. End of those. Finish. This is what is the attention mechanism, precisely summarized as this. Are we good to go on a break? Have you understood everything? No, awesome architecture, no? It's really awesome. Very less people know this. They just know how to use it as the API calls. They don't understand the architecture. So you're lucky that you understand this architecture. Understanding and doing is altogether different level of coding as compared to blindly using the API calls. Good. So let us go on a break. It's 9:01. I'll see you in 20 minutes. So I'll see you back at 9:22. Thank you. Going on break, and then we'll continue with the transformer architecture. Bye-bye. Everyone, we are starting in half a minute. Extremely sorry for the delay, guys. A lot of technical challenges, actually. Okay. So now, first of all, I'm going to share my screen. And then, now the next problem. What you understood is not the attention mechanism. So it doesn't mean that I was playing around with you. That was the base for it. So now there are two things which are left out. What you understood was not the attention mechanism. What I mean by that, let's try to understand. So now we say, this is what we understood. Okay, this is all good also. Now, the critical disadvantage over here is if you see, Rahul is a good boy or Rahul Sangla, all of these work on what you call as the fixed length vector. Now, if they are not a fixed length, then they are padded and converted to the fixed length, and then only the processing happens. And this is one of the critical disadvantage of this. Often it has seen that your encoder-decoder mechanism forgets the earlier part of the sequence it has processed till the time it is processing the entire one. And therefore, the idea of attention mechanism came into picture. I'll explain in very simple words what I mean by that. Number one, consider a scenario. I have a book on machine learning. I'm giving you a book on machine learning, and I say that, okay, let us say I am talking to Gurjit over here. And I say, Gurjit, this is the book on machine learning. Take this book. And now answer my question. What is categorical cross entropy? So this is a 500 pages book on machine learning, and I'm asking Gurjit that what is categorical cross entropy? Now there are two ways Gurjit can approach this problem. Number one, you have to tell me which Gurjit is smarter. There are two ways. The first way Gurjit can do it is he goes home, he reads the entire book, and after that, he comes with an answer. He goes home, takes the entire book, and then he comes back to an answer. Okay, I'm so sorry, Gurjit. I don't know. Always it comes to my mind. Gurjit means boy. But yes, I know Gurjit can be a girl also. So she, it happens, right? Yes. So here I'm saying, so she reads the entire book and comes back with an answer. This is the first approach, right? So let's say this is the male Gurjit. Now I go on to our class Gurjit. So what does she do? She takes the book. She goes to the index of the book. She looks for the chapter of losses in machine learning. Then she looks where categorical cross entropies page is there. Then she opens that page. Then she reads it and she comes with an answer. Now, whose approach is better? The male Gurjit or the female Gurjit? That's so fast. The female Gurjit approach is better over here. And the reason over here is this approach is going to be number one, more faster, because the male Gurjit is going to read the entire book. So he is going to take a lot of time to read the book. And after that, he is going to come back with an answer. Plus, the answer given by the male Gurjit, which is the way one, is going to be very generic, because after reading 500 pages and then remembering what he studied about categorical cross entropy, female Gurjit approach is more faster and the output is going to be more coherent over here, because she has studied that page very well and she will speak exactly as she studied about the page. So the second approach is faster. So what did the female Gurjit do special over here? She focused her attention on categorical cross entropy. And this is exactly what is the significance of the attention. So the idea is very simple. There is no need to remember everything. What needs to be remembered is the thing which is important at this point of time. That is something important for anyone to remember over here, right? What is important is the things which are really relevant at this point of time. And that's essentially what we are going to understand over here now. So we understand what she did differently. Now, what am I doing? Till this point of time, we were using the LSTM. Now, just for a change, I will use GRU architecture. GRU consists of only one internal state, and that is HI. So as you can see, this is the encoder training. Inference will also be the same. Instead of H1, C1, H2, C2, we have H1, 2, 3, 4, 5. Now, you tell me, as per the encoder-decoder architecture, what is passed from this level to the decoder? Among H1, H2, H3, H4, H5, what is passed to the next level? H5. Correct. It is H5 which is passed to the next level. Correct? Yes. Now, I say that, see, now you tell me very honestly, if tomorrow someone comes and asks you question on encoder-decoder architecture, you will be able to answer it in a super awesome way because you just understood it today. If someone comes and asks you the same question, but not tomorrow, but after 10 days, do you agree that you will be forgetting some of the information and your answer may not be that awesome as compared to what you will answer tomorrow, right? Yes. In the same way, we all know that H5, what is H5? H5 is the summary of entire sentence, which means it is the summary of Rahul is a good boy. But wait a minute, H2 is the summary of Rahul is. H3 is the summary of Rahul is a. H4 is a summary of Rahul is a good, right? So H5 is the summary of the entire sentence. So by the time H5 is passed, we know that H5 will have very strong presence of good and boy, presence of Rahul and is likely to be little forgotten. And this is still a very small sentence consisting of just 5 words. But in real life, when you have more number of words, it is going to be even more difficult. So the encoder GRU in the attention mechanism says that don't just pass H5, pass all the intermediate states because everything contains some useful information. Then last slide and you understand the attention mechanism. There are 5 slides after this, but if you understand this slide, the rest all things are 2 seconds per slide. Now, my wife drives a Santro automatic transmission. It is called as automated transmission. It is not automatic. But what is that? Here inside the engine, there is definitely a gearbox. First gear, second gear, third gear, fourth gear, fifth gear, and reverse gear. But outside here, you just have one stick which can be moved to the mode or reverse mode or the neutral mode. So if I move it to that mode, then automatically there is a mechanism which automatically shifts the gear. There is no clutch in the car, but this mechanism, which is called as the automated manual transmission, it automatically shifts the gear from 1, 2, 3, 4, 5 or 5, 4, 3, 2, 1, depending on the speed of the car. So it is this unit which does the main job. In the same way, if you observe now, right from here to here, I have a close look at this. You know what? This is the similar AMT unit. In the sense, I still have an encoder, I still have a decoder, I still have an encoder, and I still have a decoder. What is there in between this is some mechanism added. And we are here to understand this gun-like structure. If you understand this, most of the things are sorted. Okay, so let us understand this part very quickly. And then we are good to get into the attention mechanism. So here Rahul is a good boy. H1, 2, 3, 4, 5. As you can see, all of these are given as an input over here. Now, after this, so before you start decoding, we need to encode our states and we are doing that and I'm getting H1, 2, 3, 4, 5. Now the hypothesis is that the next word in the output sequence is dependent on the current state of the decoder as well as the hidden state of the encoder. I repeat, the assumption is that the next word means this, Rahul. The next word to be predicted. Obviously, it has to predict Rahul as the first word. Then it will predict Changla, then Mulga, Hai. So we understand or we assume that the next word in the output sequence, it is dependent on the current word as well as the hidden states, which are this. So now the thing is, thus at each time step, we will have to consider these things. Now, since we are predicting the first word only, the decoder does not have any current internal state. And for this reason, the last state of the decoder, I am giving as the current state. Initially, at least, because I don't have anything. And rather than giving anything random, I give H5. So this is summary of entire thing. And this is H5. So now, why are we doing this? See, if you have to predict the word Rahul, as per the idea behind the attention, which female Gurjit was talking about, we do not need. Do you all agree that the information about Rahul will be more freshly available in the initial part of the sentence, maybe somewhere over here, hopefully, as compared to H3, H4, H5, right? Mota, roughly, information about this is likely to be in the initial part. It's not guarantee. It's not a guarantee. I'm saying likely, more likely. Everyone agrees to this, correct? Yes. So that's what I'm saying, that as per the idea behind attention, we do not need all of the encoder states to predict this particular word, right? We don't need all of these to predict the particular word, but we need those encoder states which are containing information about Rahul. And my assumption is mostly H1, H2 contain the information about Rahul, at least highly likely. Not sure, no one is sure about it, but at least highly likely. So rather than considering H5, let me consider some initial hidden states where the information is most likely to be there. The weightage is going to be very heavy, right? For example, if I ask you with respect to anything related to the LSTM for text generation project, you will be answering it. If I ask you something related to the Titanic dataset, you will be like, wait a minute, let me recollect. But if I ask that information to you when I was teaching Titanic dataset, then you would have answered it very fast. So that information about Rahul, look at my pointer, which Rahul I'm talking about. I'll be pointing with the pen, right? Else you'll start thinking this Rahul, I'm talking about this. So this information is likely to be there in the initial part. So we want our decoder to pay more attention to H1, H2 and less attention to H3, 4, 5. But how to make that happen? Because ultimately these all are vectors and this is also a vector. How to make that happen? For that, we study deep learning, right? So I'm training a very simple neural network which will learn to identify the encoder states which are generating a high score for the states where attention has to be paid and low scores for the sets where attention has to be ignored. So we train a very simple feed forward network where we say that, hey, I want you to focus on the initial part and less on the later part. And it generates me scores. So all of these scores are nothing but real numbers. So they can be 100, 500, 2000, 20, 30, 15, 1 lakh, could be anything. Now, after that, we apply softmax. What does softmax do? Softmax is like min-max scaler. It will shrink all of these values, which actually go from minus infinity to plus infinity into the range 0 to 1. And also the best thing is, if you took the summation of all these e's, it will be 1. So let's assume that after shrinking these values, you are getting the values of E1, E2, E3, E4, E5, something like this. So let's say after doing that, you are getting E1 value as 0.75, E2 value as 0.20, E3 as 0.02, because this 75 plus 20, 95 is over. This is 2%, this is 2%, and this is 1%. And you can see the total of that is 1. Yes, the total of that is 1. So why did we do that? Because machines hate big numbers. So we just use the softmax function, which we have used in deep learning. If I won't have taught you deep learning, then again, all of these things would have been completely bouncer, right? Please make a realization of this at every stage wherever I'm telling you. Okay. Now we have done that. And now you have E1, E2, E3, E4, E5. You also have H1, H2, H3, H4, H5. How do you populate the context vector? You remember earlier what was happening? Let me go back. How was the context vector getting populated? So here, input sentence given, summarization happen, and you get the context vector, which is HICI, and that is sent as it is. But now in between this, we have added what? A layer, which is the attention mechanism layer, which will take this context vector, do some processing, and then that is finally returned. So this is now not called as a context vector. This is the output of encoder, and something happens on that, and then the context vector is created. So here, how is the context vector created? It is now done E into H. So you computed all this. These are called as the attention weights. Very popular question asked in the interview. If you're able to explain it this way, no further questions will be asked. I can assure you. People don't even know this much. E1 into H1 plus E2 into H2 plus. Now, see, if the values of E1 and E2 are relatively higher as compared to this, when you multiply E1 and E2, which H1, H2, as compared to all others, the summation and the total summation of these values also will be higher, right? So this is expected to be high. And this E3, because it's small, so the multiplication result is also expected to be small only. So automatically the weightage of H1 and H2 has increased because you're multiplying it by bigger values. And H3, 4, 5 are reduced because you're multiplying it by smaller values. Now this is called as a context vector. Now, if you recall, by going back, what used to happen? Once you have that internal state vector or the context vector or the thought vector sent ahead, what was it concatenated with? Start. वही करना अभी. I'm going to do the same thing. This context vector is concatenated with the start. And that is called as a concat vector. You will see all these things in the coding as well. Next lecture. And that comes here. And then it goes to the decoder, and the same thing happens as I explained in the decoder, and it predicts the output and the internal state. This all happened at time instant 1. Then at time instant 2, what will happen? This decoder state will come here, D1. And this Rahul will be going here. Yes. Because it is going to run in a loop as I explained you. So make a note of this. I'm going to the next slide. See, D1 came here and Rahul came here. And at time instant 2, same thing happened. D1 here, same thing is going to run, and it created concat vector, blah, 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 concat vector, and it predicted Changla and D2. Next time, Changla will go here. Sorry, D2 will go here, Changla will go here. Correct? Let's see. D2 here, Changla here, time instant 3, same thing happens. Mulga and this. Next time, Mulga will go here, D3 will go here. This will continue till what? Till END is not predicted. So at time instant 4, or here, D3 here, predicted AHE and D4. Next time AHE goes here, D4 goes here. We are in the time instant 5, D4 here, AHE here. It did, because it predicted END, stop. And then that is how we are able to do the attention mechanism. So it is essentially just a small unit added in between the encoder and decoder architecture, and that completes. So we started our journey by this figure, and we ended our journey of attention mechanism by adding a layer in between the encoder and decoder. An encoder and decoder essentially are nothing but LSTMs or GRU. So without understanding of what is LSTM or GRU, again, this overall architecture would have been completely meaningless to you. So if you are clear with this, then I can go ahead with the transformer architecture. Let me ask you, everyone clear with this? Very good. So now, yeah, now I get started with the next part here. The next part is, if you are so happy with this mechanism, I will try to make you a little bit unhappy. So what am I looking at right now is the drawbacks of attention mechanism. So we say over here that we started our journey with why attention was needed, right? So before talking about that, let us start our journey with that only. Why attention was needed at the first place. So the first thing is, we say before attention, we had recurrent neural network and long short-term memory. But there was some problem with the RNN and the LSTM architectures. And the problem was they processed the sentences word by word. And because of that, there was a loss of context. So if I consider our example only, so when you are translating Rahul is a good boy, by the time the network propagates to the last word boy, it might have forgotten the word Rahul. So we realized that attention mechanism was introduced to focus on the important words across the entire attention instead of the last few words. But it also had some limitations. So that is what we are trying to understand now. What are the drawbacks of the attention mechanism? Number one is computationally complex and too slow for the long sentence. So the issue over here is attention scans all the words for the new word that are being generated, which means that for a n word sentence, it has to do comparisons, which means it is computationally very expensive. So let's see if I'm considering with respect to our example. What was our example? So let's say if I'm translating, Rahul is a good boy to Rahul Changla. So what is happening over here is our attention mechanism is while generating each Marathi word, attention has to look into all the English words. And this is fine for short sentences. For long sentences which are having 50 plus words, computation explodes. Now, why transformers in the case is because transformers are awesome. And why are they awesome is because if you look at this image, right? So I'm going to show you a very nice image. So why are transformers awesome? Beautiful girl and a lot of food. How much time do you think she will take to eat the food? If let's say she eats it, how much time do you think she will take to eat the food? And one image I generated using Chat GPT. Let me hear what are you saying? Let's say it's possible. Let's say it's possible. So I'm assuming that okay, let's say if it is possible, mota, let's assume that she takes around, let's say, 6 hours to eat this food. Now I am going to go on to Ravan. Everyone knows who is Ravan? The Ravan of Ramayana. Same food served to him. Now, if it is the same thali which is served to Ravan, same thali that this girl was eating, let's say similar, same thali is served to him. I didn't get the same image, but do you agree that Ravan will be able to eat this in 6 upon 10 hours because he has 10 heads? Agree karte ho? So what is Ravan doing over here? Can I say that he is doing parallel processing? Parallel processing. Yes, you agree that he is doing parallel processing. Now, today, today we have GPUs. If you recall on the day one only, I told you that if you have to train a large language model, you require minimum 6,000 GPUs, which will run for almost 2 to 3 months continuously. Now, in this case, what is transformer architecture specifically doing? The problem with the network that we are doing till the attention mechanism is we have only one mouth. That means if you have to process Rahul is a good boy, if encoder has to process Rahul is a good boy, it first takes input, right? So let's say if I have to process Rahul is a good boy, I told you that initially it will take Rahul, then it will process is, then it will process then good, and then it will process boy, which means that today, even if you say you have the GPU, but still you are processing the inputs one after other. Logically, tell me, can you process the word good before processing Rahul is a? Can you process the word good before processing Rahul is a? No. That means if you do that, your information context is gone. It will not understand the sentence only. Imagine me saying, good is a boy Rahul. You'll be like, kya bola? I said, good is a boy Rahul. What do you want to say? This will make only sense when I say Rahul is a good boy. That is the problem. So today we have a lot of GPUs and everything, but still, because we have to pass the input one by one, there is no point in using GPU. If you are passing the inputs one after another, there is absolute no point in using the GPU. And that is the biggest problem. So you cannot use GPU, or rather, GPU is not required only because you See, let's say, imagine you have this much of food, but you have only one mouth. If you have one mouth, then you cannot put food from your ears, nose into your stomach. It has to go from here only, right? So you just can't use it. Or imagine you have Ravan. Ravan has 10 heads, but he can actually eat using only one head. Rest all are dummy. They can shout, they can talk, but only through this food only through this mouth he can eat. So that means, in spite of you have all the powers, you still have to use only this. And that is the problem with the attention mechanism. You cannot, there is no need of using GPU because you're anyways processing the things one after other. So your CPU can also do the job. The overall process is becoming slow. Are you understanding the drawback of attention mechanism? Sequential processing is happening. Parallel processing is not happening. Everyone, yes. I need your due permission now. I need another 20-25 minutes of your time, because if we cover it right now only, then next time I will leave you half an hour early. Whatever time I'm extending the session right now, I'll leave you next time early, because if the transformer architecture gets covered right now only in the flow, then it will be, it will be very easy for you to understand. Can we give a try? Great. Those of you who have some commitment, feel free to drop off, watch the recordings. If you have any questions, next time I will take it. So why transformer? So the reason I said that is, instead of scanning the word sequentially, transformers can process all the words parallelly using self-attention, reducing the computation time. That is the first thing. The issue with the attention mechanism is, attention is still used sequential input. That means the inputs are processed one at a time, and that is what makes it slow. That is, with respect to example in our context, the model translates Rahul is a good boy word by word instead of looking at all the words at the same time. This is what makes the training slow. So that was the first drawback which we discussed, and I'm talking about the second drawback over here. So here also, why transformers? Again over here, as I told you, instead of scanning the words sequentially, transformers process all the words together in parallel. So that's again the big advantage over here. So I say here, why transformers? That said, transformers use something called as a self-attention and positional encoding. We'll see that what it is, which allows the model to process all the words at the same time. And this speeds up the training and the inference dynamically. Is context limitation for very long sentences. What I mean by that is, even though attention can look at all the previous words, but it will struggle with the long sentences. What I mean by that is, if our input was a paragraph and not a sentence, then attention will struggle to keep a track of the earlier words. Like, I'll give you an example. Translating Rahul is a good boy and he plays cricket well. His coach says he has a bright future. To Marathi becomes harder because he needs to be mapped to Rahul, and understanding that, okay, this he is Rahul, this he is also Rahul. And why transformers over here? Again, the advantage over here is transformers use self-attention mechanism, which allows to have a deeper context retention over the long sequences. Now you'll be like, but how part will handle it when we look into the transformer architecture? Next one, poor handling of the word order. That means positional information is lost. What I mean by that is, attention does not inherently understand the word order like the recurrent neural network does. What I mean by that is, if attention saw that Rahul is a good boy, it might misinterpret that boy is good Rahul. And this is also equally valid. This is what attention may feel. And because of that, we see that the meaning is completely lost without knowing the order. And transformer takes care of this thing as well. And how does that happen? Transformer uses positional encoding, which assigns numerical patterns to indicate the word positions. Now, again, how this happens, we will be studying it in the architecture. The last one is the high memory usage. So what I mean by the high memory usage over here is, since attention requires comparing each word with every other word, memory usage increases drastically. If I consider the example in our context, if our sentence was 100 word long, attention would need to compare 100 cross 100 words, which is 10,000 operations. And this is what becomes too expensive for the large text. So, why transformers? And that is because transformers actually optimize the memory usage using efficient self-attention mechanism, making them scalable. How? Patience. We will understand this. So, attention was definitely a great improvement over RNN and LSTM. It was slow, sequential, struggled with long-term sequences and all those things. And then to solve this problem, finally, the transformer architecture was invented. Okay. Now, if you look into this transformer architecture, there are two parts of it. Left side is the input, right side is the output. I'll show you what I exactly mean by it. This is where. So in the transformer architecture, you know what? That's your encoder. Yes, this is your encoder and this is your decoder. Earlier also there was encoder-decoder. Now also there is encoder-decoder. You will be getting the predictions from this. So everything is going to happen the same way. So let's understand each of this step by step. So I'll try to, what I want to do is I just want to somehow complete it today. If required for tomorrow, I don't mind. Tomorrow means next lecture. I absolutely don't mind in giving you a revision of this, but at least at a quick, faster level, allow me to complete this row. Let us quickly get into this. Here it is. Stage one. Let's try to understand it now. Keep this open over here, plus here. So now the first one, input stage, which is the here, right? First, you give the inputs, then you convert it using embedding, which is the word embedding and all those things. And positional embedding is what? Let's try to understand. What happens in this stage? The English sentence, Rahul is a good boy, is broken into tokens. So as you can see, Rahul is a good boy. Understand, if you don't understand tokenization, what are the various ways of doing tokenization? This would again have gone a bouncer to you. So that NLP background is helping you to learn. So each word, after converting them into tokens, we convert it into numbers, which is the word ID from the vocabulary. We have done that yesterday in the LSTM for text generation. है ना? Yes. Then these numbers are mapped into word embeddings to capture the meaning of the words. I told you yesterday word embedding where we did that for the features like man, woman. Then we looked at the features like age is the feature. Then some more features were there. But you understand, right? So everything is converted into word embedding. Now the thing is, since the transformer understand the word order, positional encoding is added. So basically, positional encoding will be assigning positions. Like in this sentence, it will be like, okay, this is the first one, this is the second word, this is the third word, this is the fourth word, this is the fifth word. So it will assign every vector a position because it is going to study the things parallelly. Later on, while connecting the dots, so it will assign positions, right? So position encoding is added so that the model knows the word order. And then after that, it comes into the encoder, where you have the multi-head attention layer, which is the heart of the transformer. If you understand these two, rest all things are as good as, most important are these two only. So I'm pretty sure in next 10 minutes, we are able to wind off our class. So focus on these two. These are the most important. Of course, they have a significance, but they are used to reduce the fitting and all those things. Now what happens? Encoder is responsible for summarizing the sentence, which is understanding the sentence meaning. So encoder now processes all the words at the same time, parallel processing, and that uses self-attention to figure out which words are important. So it will create a better representation of the sentences. Like Self-attention in this is responsible for finding relationships like Rahul has a strong relation to boy. Good has a strong attention to boy, but a weak attention to Rahul. So, an example weight matrix, something like this would be created. So, Rahul and boy, strong attention. Rahul and this 0.2 with is 0.1 with a 0.1. Good and boy 0.4. Good and Rahul 0.3. Good and good and is less. So the final output is a set of numerical vectors that represent each word in the context. So what happens over here is essentially these vectors are given over here, and what multi-head does is for every vector it will use the self-attention mechanism. Don't forget this word. This is very important for the interview. Self-attention. Which word is important the most and how is it relevant to other words and how much importance it has with other words. Then add and norm is like sending it to a simple feed forward neural network and normalizing the output, which is like scaling divided by 255. Again, sending it to another simple feed forward neural network, because what happens when these all things are coming at the same time is the output starts going haywire. So again, you are adding normalization layer, right? So feed forward added, and again you had the normalization. These all are just used for regularization, that is overfitting to be reduced. And then you send it ahead, just overfitting detection. Then passing the encoder output to the decoder. What happens here? Encoder sends the process sentence to the decoder. Decoder will use this information to generate the Marathi translation step by step. So the output of the decoder is a set of vectors. Rahul is some converted to vector. Everything is converted to a vector. And these vectors do not have any words yet. They are just numbers, right? We're just storing the meaning, which we will never understand. Now, what happens? We are talking about the decoder part now. So your Marathi sentence is given here. Output embedding happens. Positional encoding happens because you are training, right? Understanding the relationship. I'll tell you in short what is happening. So your Marathi sentence are here. Word embedding, positional embedding, all these things happen. And then what it will do is it will mask. Mask means it will hide the Marathi words. English words are summarized and ready. They are ready. But the Marathi translation is masked. So it is like the word is there, but it is masked. Then the word is there, but it is masked. So what happens? It tells you the encoder that, hey boss, you are summarized. You only predict, na? You only predict. I'll give you the start token, you predict. So now this encoder gives the prediction. Now it says that, okay, what did you predict? Okay, you predicted some vector. Now I will show you what is the actual vector expected to be. You compare it. And that is how the training happens. So it will release the next word one by one, and then it calculates the total error again and again. And that's how the things are happening. Because after that also, if you see, this multi-head attention layer is learning that relationship, that this prediction and the actual using the concept of teacher forcing. Yes. So initially you are hiding, then asking it to unmask, and then you're comparing the predicted and the actual. Same concept of teacher forcing. So if you look over here, the decoder starts with a special token start. It generates one word at a time in Marathi. It looks at the previous word it generated, which is the masked attention previous, right? Because if it is showing the word, then it will start to match the noise. So it will mask it. And then how the learning happens. So initially start, let's say it gives output Rahul, then Rahul ek changla, Rahul ek changla mula, Rahul ek. Now self-attention in the decoder. You again see over here multi-head. Multi-head is nothing but self-attention. After that is all this regulation parameter. What is multi-head? So here the decoder attends to the Marathi word it generated. It looks at the English sentence vectors from the encoder, and thus it matches the word correctly by understanding the relationship. So it understands that, okay, this in English is this in Marathi. Strong link. Is in English is ahe in Marathi. Strong link. Good is Sangla. Strong link. Boy is Mulga. Strong link. So it learns which English words focus on for each Marathi sentence. And then finally, if you see, what happens in the final word is converts the numerical representation into Marathi words back, right? Because it has to now do that. So what is this happening? Is the output is non-linear. So all of these decoder, which predicts the next word for the probability. This Ram, Changla, Mulga, all of these things are predicted, and the highest probability word is chosen. So Rahul comes first. Then next time, another set of words are there. From that, Mulga will come, no, Ek will come, then Changla will come, then Ahe will come. So every time it is generating a bucket of probability words. So first time it took Rahul, then it took this, then it took this. Then next time, when it took, the word which came was END. Now, obviously, do we want to print END? No. So that mechanism is automatically there to ensure that the last is not printed, because every word ending with END looks very odd. And then overall, this is what happens. So essentially what happens is, after this learning part is done, you again do the regularization stuff, same like you did here, nothing new. In fact, this entire part is same as this entire part, right? After that, there are a lot of words. Linear is going to make the output of the neural network is always linear, and softmax is responsible for choosing the highest probability word. And that is how this architecture predicts the thing. And the thing is, can you understand it in any way better than this? No, they are only and only vectors. This entire processing which you saw on the screen is all. It is only that here there is English, here there is Marathi. After that, right from here to here, it is all numbers which we don't understand. But internally, this is what happens. And the proof that this actually works is ChatGPT. That is why it is able to remember, it is able to do really fantastic. It's the proof behind it. And that is what is attention mechanism. End of session. Control S, closing it. This part, taking it out. After this, you have this. I'm also sharing with you some additional notes. Maybe these are helpful to you. I am going to export it. What is this? Encoder-decoder attention mechanism, transformers architecture. This is the case study that we are working on right now, right? So text translation, we also call it as the neural machine translation. But wait a minute, we have completed with the attention mechanism where we looked at the English to Marathi translation. Am I correct? Did we look at it in the previous class, English to Marathi translation? And then we moved into the transformer architecture after that? Yes. So this is English to Hindi. English to Hindi. So today's session will be a practical hands-on. Let us get started with it. And getting the screen. All right. Let's get into this. So we'll start by reading the problem statement. And could you please, meanwhile, someone please share our image after this neural machine translation. What is the next thing that we had? Great. Awesome. So text generation using attention mechanism. Then we get started today only with GAN or variational autoencoders. Perfect. So GAN is again something which takes a lot of time to train. Lot means much, much more than what we can actually think of. Okay, I should ideally save it where, let's say I'm saving it in my Learn folder. Getting started. Let's go through the problem statement initially. So what is our problem statement? As you can see, the title is, let's just increase the size a little bit, toggle header. The project is to build a neural machine translation for an e-commerce product description for global market, Amazon India. As Amazon expands its reach into the diverse international market, it has become essential to ensure that the product descriptions are accurately and efficiently translated to cater to the non-English speaking customers. Yes, very important. So for Amazon, Hindi translations are particularly important because they make the platform more accessible to a larger segment of the Indian population. Currently, this process of translating descriptions is time intensive and often outsourced, leading to inconsistent quality and delays. So to address this challenge, Amazon India wants to develop an in-house neural machine translation model tailored specifically for translating the product descriptions from English to Hindi. So the objective of this project is to build an automated English to Hindi translation model using the deep learning techniques.
The focus will be on translating the product descriptions with higher accuracy, preserving the product's key information and intended marketing tone to provide Hindi speaking customers with a clear and engaging shopping experience. This will not only enhance the customer satisfaction but will also drive engagement and the conversion rates on the platform. The goals of the project. We have to develop a neural machine translator model, create encoder-decoder based NMT, optimized for translating e-commerce product descriptions from English to Hindi. Then achieve a blue score of 0.3 at least initially, with a target of 0.5 or higher. Higher the blue score, more it is aligned towards the human side, right? More human acceptable, higher the blue score. So then we say reduce the translation cost, consistency in the tone and terminology, and scalability for additional languages. Look at the expected outcomes. Just giving you time to read up. I'm not reading it out. I'm giving you time to read it. Read the project scope and deliverables as well. Quickly read it. Don't invest a lot of time in reading. Going on this, you can read later. Long-term vision and the project summary. I want you to read this. Next, going ahead. As you can see, the first install which I have done over here, as you can see, is going to be the installation of the libraries. The first one is the word cloud, which is mainly used to generate the word clouds, which is visually representing the most frequently occurring words in the data set. So, word clouds will actually help us in understanding the common words in the text data set. Then contractions, we know, right? It's used for expanding the words like don't to do not to make the text more structured and meaningful for the NLP models. Then NLTK, we know what is it used for. I need not talk about it. Thereafter, we get into the necessary imports. As you can see, the first thing that we are having in over here is we are importing the regular expression, which is quite obvious and known to everyone. Then NLTK, then word tokenize and sentence tokenize is another thing that we have over here. Then, so what tokenize is for tokenizing into individual words, and sentence tokenize is for splitting the text into sentences. So it is important for NMT training because input must be in the tokenized form. Then from NLTK.corpus import Indian. What is that? Here, I'm loading the Hindi language data from the NLTK's Indian corpus. So it is mainly used for training and analyzing the Hindi text processing. And then you have the porter stemmer, which is there. Then you have the word cloud imported, matplotlib, Unicode data, right, which we are using over here. So Unicode data is basically for handling the Unicode characters in text, which is helpful for Hindi processing. So some Hindi words contain some special characters that need processing. So this will just ensure that the Hindi text is properly processed. As simple as that. Then we have from keras.models importing sequential. We know why. Then we have the embedding to convert the words into vector representation. LSTM is RNN, type of RNN, and denses, we know it, right? So all of this is for converting text into Hindi using deep learning. Then you see, we have the tokenizer. The tokenizer mainly is for converting the text into the numerical representations. So it will ensure that all the sequences are same length when you do the padding after this. So deep learning, we know, right? Deep learning library requires numerical inputs. We are preparing the text for model training and then train test split as we know. Then string is used for importing the set of punctuations, contractions, and all other things we know. Yes, one thing that we do not know is the blue score. So see, basically blue, what does that mean? See, blue means bilingual evaluation understudy. Blue means bilingual evaluation understudy. And basically it measures how accurate the model's translations are. We'll study this later, but in short, this is what it means. So it is mainly used to evaluate the NMP model's performance. Then you have to download the NLPK stopwords for Indian as well, and we are done. Then After that, I'm loading the data. So as you can see, we have loaded the data set. After loading the data, we are have no missing values. Converting everything to the lower case, we understand why we are doing it. No doubt about that. This is something which we all understand. What sample data, Yusuf? What do you mean? We have read the data set here. Yes, it is the CSV file. That's correct. Uh-huh. I didn't display it so far because I'm not executing it. It's going to take a lot of time to execute. You will see it. Have patience. Yes. So now we'll lowercase it. Okay. If you think you want to see the data, let me show you that. I think your question is valid. Maybe it's a big data set. I'll show you just a moment. Taking time, it's 40 MB data. That's why I was trying to avoid it. Sharing it. Hold on. This is how the data is. Help, hello, namaste, and so on. So many are there, right? So later on you can see. Open your mouth, apna move. Please sit down, bet here. She is a beauty. वो तो हसीन है, and so on. Right? I hope that gives you an idea. Now after this, it is as it is, Sudan. As you see, that is how it is. Okay, then I have created a function to remove the URL. So remove URL means there might be some website links or some URLs in the product descriptions which are unnecessary for the machine translations and can negatively impact the model performance. For that, I have created a function called as remove URL. So why is it needed? Because many e-commerce product descriptions include the links to the product pages which offer external websites. So these URLs do not contribute to the translations and can create noise. So if you see, the first thing is here is instance. So what are we doing? I'm basically checking if the input string is a text and it will prevent the errors and all those things. So I'm going to create a regular expression pattern. So if you see this pattern, right? So I would like to tell you what essentially is this pattern trying to match in over here. So here the pattern is different. My bad, sorry. So here, if you look at this particular pattern where you have the angular bracket and this. So what are we trying to do essentially is I am trying to ultimately ensure that my model gets clean and structured data without having unnecessary HTML elements. So here, this is this angular bracket dot star question mark. It will match anything between the angular bracket which represents HTML tag. So this pattern detects and removes all the HTML tags. So it will ensure that only meaningful words are retained. And then you see this sub as well. So this sub will replace all the occurrences of the HTML with the empty string. So it will effectively remove all the HTML elements while keeping the actual contents intact. Give you an example. If you consider that if you have a remove HTML which is given a text, something like this, then in that case, what you will have in the output will be this. You will get rid of all of these things. That's the number one which I want to talk about. So this is what I'm applying to both English and Hindi. Then it will return the non-string values, right? So if the text is not string, then it will return the original value unchanged. So this is what we apply to the English and the Hindi columns, and it will ensure that all the text entries are clean and that the pre-processing of the product description for training the neural machine translation model is perfect. Then we also have remove URL. So this function takes the text input and removes any website links, which is here. So I say this function takes the text input and remove any kind of website links. Again, many e-commerce websites, you know that they link to the product pages or the offers which they have or external websites, right? So the URLs which are not contributing to the translation can create noise. So I'm trying to do that, right? So that's one thing. Then, so the first thing is I'm checking if the input instance is a string, and then you have a regular expression over here. So what are we doing inside this regular expression? I'm matching HTTPS colon and one or more words in between having a www dot. So if you see over here matching the URL which contains HTTP colon or HTTPS colon followed by any non-white space characters. Also, this is also looking for any non-white space characters. So see why? Because many product descriptions will always have embedded links. And when I say embedded links, this is required because don't be surprised if you see something like this. Check this amazing deal, Amazon.in deal 123 and visit this. So you have to take care of all of these things. So now I like to tell you that if your input is like this, your output will be this. By now at home. I'm just removing irrelevant URLs that are not contributing to the translation. That's it. Not doing anything else. Then after that, moving down, we have removing the non-Hindi and alphanumeric characters. So I'm cleaning by removing special characters and the non-language specific characters from the English and the Hindi product descriptions. So the first function, reprocess text, well, it is defining whether it's going to accept the text, which is the product description, and the language, whether it is English or Hindi. So that I have created. If not is instance. So if you will check if the string is, sorry, if the text is not a string. So if it is not a string, it means it can be none, numbers or missing values. So it will return the text unchanged. So here, if you see, I'm using the regular expression and I'm saying that the language is set to English. And then I say re.compile. Now we all know A to Z are the English characters which we are talking about. Similarly, here, when you consider 0 to 9, these are the numbers that we have, and backslash s is nothing but the spaces. So I'm basically using the regular expression I.compile to remove the unwanted characters over here. So, for example, we see something like this: buy two, get one free, limited offer. If you see something like this, buy two, get one free, limited offer, then this is going to be converted like this. That is how it helps. Similarly, I have the Hindi language pad as well. So for Hindi language, you can see, first of all, we are checking for this, and I'm using the Unicode range. So if you see the Unicode range, which I have used this actually corresponds to the Nagari script, which is used in the Hindi. So don't be surprised if you see something like this. विशेष छूट है 50%. Jaldi karo. So you will only have wishes all things are removed. Then we say, if anything of this is not there, then I have also added an exception handling scenario. As simple as that. So I'm applying these functions and ensuring that everything is as perfect as it should have been. In the same way, after this, string dot punctuation is going to list down all the punctuations. So now I'm giving a call to get punctuations where I'm having Hindi punctuations empty list, and then you can see what am I doing over here. I have created an empty list to store all the Hindi punctuation characters. So this will hold the extracted punctuation symbols before joining them into a string. Now, if we look into this loop, so what is this range 0x2000 to 0x this? Honestly speaking, in very simple words, these contain punctuation marks in the Indian languages. So Unicodes basically assign specific code points for different punctuation patterns, and this range covers most of them. So it helps the programmers to extract punctuation characters instead of manually defining them. The next is r is equal to chr of I. Well, that is the place where I am converting the Unicode character integer value to the actual character. So this chr of I function gives the actual punctuation instead of the Unicode value. Like, I'll give you an example. If you say CHR of 0x2010, the output would be hyphen like this. Then after that, I'm checking is Unicode character PO. Now, what is basically PO basically means punctuation other. So I say that if the Unicode character to check whether the character belongs to punctuation other category. Is that belonging to punctuation other category? So if that is the case, if the character belongs to punctuation other category, then we will add it to the list. Then we'll add it to the list. And then I'm returning all the joined characters. This is what we see. Then in return, it tells me what are the punctuation characters available in the language. Then very soon we are going to look at the data now. So far, what do you think? Is it challenging? You should say no, ideally, because we are just doing the pre-processing. We are not yet neural machine translation. This is the text pre-processing for which we have spent an ample time upon. So there is nothing that, yes, you are learning something new, but yes, this is text pre-processing only. You are not doing anything else over here. Am I correct? Yes. And every time in text pre-processing, the challenges are going to be different. For now, these are the challenges. Perfect. Then I say, coming down, yeah, this one is done. Can remove punctuations in English. So this is going to be ensuring that the cleaner text is available because we are going to remove the punctuation from the text language English. So we have that. I'm seeing is the language equal to English. Then string dot punctuation, we know all the English punctuations are being saved. What are these all English punctuations? If the language is equal to Hindi, we know that we have all the Hindi punctuations as well in the place. So it will be joining it back. So if the character is not in English punctuation, do this. If the character is not in Hindi punctuation, do that. There is unsupported language if not among this. So essentially, I'm removing the unnecessary punctuations for the inner input text. I'm also thereby improving the machine translations and the NLP performance. And I'm ensuring compatibility with the different languages, English and Hindi. Plus, enhancing the text pre-processing for sentiment analysis. Now, after this, you have the contractions fixing. That's quite understood. We have done that contraction dot fix. That's the only thing. Then I say tokenization. Tokenization, we all know, is breaking it down into individual words. So tokenization is important for machine translation, sentiment analysis, as well as text classification. So over here, I'm simply calling the word tokenize. So I know that inside this, when I have a method like this, ultimately what shall be written after tokenization is going to be this. And that is what is my data right now. Okay. After this, give me a moment. Sorry, guys. So first of all, I am a little irritated today because my laptop is not working as expected. It's hanging in between because that processing is going on. You'll not believe till now the processing is going on, and I'm still on the second epoch. Almost second epoch is on the end of completion, but that's too long, right? I started at 3 p.m. It's 8:04. And this is the same notebook that we are discussing. Don't even think of executing it. It's very expensive. Okay. Then I download the stopwords of all from NLTK and Indian stopwords and Hindi, US parts of speech. Then as you can see, all the English and Hindi required stopwords are saved. Then here I'm calculating if the language is English, then all the stopwords from the English language to be removed and join it back. Same happens for Hindi and you call it because you have two languages and if you want, you can go through the code and this is what we get. Stemming is done. Voter stemmer create an object after tokenization using split. I'm just applying the stem function on English and Hindi. So this is what is the thing. Then look over here how the sentences look like after stemming. Then we have a word cloud in place. First of all, why don't you have a look at the diagram? So this word cloud visually represents the most frequent words in the data set, right? So it will very much help in text analysis or sentiment analysis or even topic modeling. Now, if you look into the code, which let's go through it now. So first and foremost, I created this function by the name generate word cloud, which will help me to visualize the most frequently occurring words in the text data and explore the text patterns. if any. So that's going to be something that will be helpful. Next, what is there in the chat box? Two messages all of a sudden. As a part of training, we are doing all this text pre-processing. Just trying to relate to our earlier NLP examples where we only did pre-processing. We those before doing fit. So we are also doing the same thing over here. I'm just getting rid of all the noise in the data and keeping only the relevant stuff. Yes, what you heard is absolutely correct. If you have anything else to say, now better raise your hand. I understand it better. Next, Yusuf says, I see single quote next to yes. That is correct. You are correct. We are able to see single quotes. Even I did note that, but that's okay. Not a big deal. So the single quote is not actually the word I would say. Maybe did I plot anything like that? Because after removing, if it has added, in fact, to every word we have it. This is what my experience is. Yes, this is how our image looks like. Can be very well seen. I understand that. So let me tell you what could be the reason for it. I'm not pretty sure about it, but the very practical reason for having that single quote next to many words is because of the apostrophe in the words. For example, if you have a word like India's, or instead of people, if you have a word like people's, or instead of it is, it's. So that can be something which are being retained as specific tokens, and that could be the reason for these things being there. So also there can be some special characters or punctuations which might not have been completely removed during pre-processing, or our word tokenize might have treated a single quote as a separate token. Anything is possible. One can go back and check, but this is not a big problem because I have executed this case study and I know the overall output is good. But yes, if the output is bad, you can definitely consider working on this part, right? Yes, it can impact, it may not also, but I have already executed this case study and I have realized it is not impacting. But for some other project, if it is impacting, then you may have to probably consider removing it. Perfect. So, what are we actually doing over here? The first one, I am joining everything. As you can see, all these things we are joining together. Map function is ensuring that all the words are converted into strings and they are joined into a single block. Number one. Then it's very simple. Basically, if you have thing like this, after doing this, expect the output to be like this. So after this, we can see we are creating an object of the word cloud where width and height is obviously the image width and the image height is what we understand. Then we also have the background color, which is the white for better visibility is what I have set. Then color map, we know it's nothing but the color scheme. And then you have the generate, like the text str, which is generating the word cloud. So it can give me quick insights into the text data, thereby helping me identify the current themes, trend, and the words. Then I have the PLP.figure, which, and this is what is responsible for displaying the word cloud. And that's why you see it like this. And also, this is for the Hindi words are not being displayed, unfortunately, because it's not supported. So it is a not supported language as per the word cloud library. Then after that, the next one is we get into the process of calculating the maximum sequence time. What is that thing which is happening over here? So in this calculate maximum sequence length, I'm trying to calculate the max length of the sequence among all the text sequences that I have in my corpus. So the goal is to determine the longest sequence length, which is useful for padding sequences when working with deep learning models. So first I have created the function which will be accepting the text. So text is the one which has to be combined sequence. Then as you can see, it is going to iterate over the list of the words and Max is going to consider over here the longest sequence in this. And that is what is written. And that is what happens with the other ones as well. Then we are tokenizing it. English and Hindi, done. Then adding start and end token. You remember in the theoretical part, I said that start and end tokens have to be added to ensure that the lengths are getting matched. Do you recollect? Yes. So start end, and we only add it to the target language. We don't add it everywhere, only to the target language. Then, yes, thank you. Good, you remember it. Then after that, I added special token start and end. As you can see, just go through this code. Then it's time for us to convert the text to sequences. Remember the LSTM text generation problem, the same thing. Then again, we are finding out the maximum length in both English and Hindi. That's straightforward code, right? So you are passing the text and finding out, converting it to sequences and finding out the maximum. Then, oh, I don't know when it started. Sorry, my mistake. I didn't even realize. I think X to Y in the second print is a typo. Where? Ah, that's okay, na? That's correct. Typo, yes, here. That's not a code error. It's basically understood your concern. There is nothing which is going to hamper the coding, but my printing thing has to be X. That's correct. That's correct. That's a good observation. Okay. Then after that, finally we have this on which we are doing train test split also. Go through it. Because this is known to you, I don't think I should talk about it for them. Now, this can be considered as the next level. After this train test split, I'm just finding out how the things are looking. So this is machine is going to understand the relationship in between this. This sentence, govern also thought problem, mini steel plant, and this looks like this. And in Hindi, "Ya laghu is the path." And then we are doing the padding. You know that this time I'm doing the post padding, and we have already studied what is padding. So on both the things, I'm doing the padding, and right now this is what is the scenario. Quite heavy, na? It's not heavy actually. For the first time, you're looking for such a big project, and it takes a lot of time, right? But more of text pre-processing is like this only, but it's really interesting. It's really interesting. Now we will go on a break because after this comes 50% modeling done. Also, one more thing I want to let you know that today, right? Yeah, last time we extended the class. I said apologies for that. Today we will be freeing up early. Hopefully, fingers crossed, if this case study is over, else we will extend up to 10. Better be prepared for that. So, anyone having any questions so far? Anyone having any questions before we go on a break? I want to know it. Are you able to understand the things that we are discussing, each and every line I'm explaining us? So I'm just trying to confirm, are you still everyone is able to understand every line of the code? Is that understood? Or you're finding it difficult? Tell me your honest opinion. According to me, it is straightforward only. We are actually not doing anything out of the box. It is just that this is big. That is the only difference. Perfect. 8:30 on the clock. I'll see you in 20 minutes. 8:50 we come back. Follow this time. See you then. Welcome back, everyone. Is there anything which I am not in a position to explain you today? I don't see the rating of the training as expected because I mean it is good only overall, but still it is not the best. So is there anything which needs to be revamped? I need to get those answers. I need to understand. Unless and until you give me inputs on that, I won't be in a position to take any kind of actions. So the first question has 100% ratings on the first option, but one candidate out of 10 in the second question has given 7. Why? What is the reason for it? Would you please take some time to help me understand where I am not going as expected? If you are finding the case study challenging, and if that is the reason you are saying that it is 7, then that's not the right reason to justify. And if there is anything where I am failing, then I would definitely like to know that. I have all the right to know that so that there can be some kind of corrective actions taken. So, do let me know what is the reason for this. I shared it. So anyone can give in the inputs. So those two, and see, ultimately, the session is for you, right? It's not for me. So if you let me know the reason, then only some proper actions can happen. If you're gonna not take this thing seriously, maybe the curriculum
or things are going to get more and more complicated. Just because you find the things complicated, that cannot decide the rating of the class. Essentially, I want to be very clear over here. If you do not participate in the chat and all of a sudden expect that, okay, still I should understand everything, and if I'm not understanding a thing, or maybe you're not revised anything in the past, then please do not hold me responsible for the same. Equally, it becomes your job as well to reciprocate. At regular intervals, I have asked you any questions, do let me know. At regular intervals, I have taken pauses for you to go through the difficult code. Each and every line of the code, I have taken an effort to explain. So, where am I lagging? I have all the right to know that. So, be bold enough to come in front and justify your rating so that we get some idea about the scope of improvement. I'll wait for 30 seconds. After that, also, if you can't come, then I'm sorry, I may not be able to help you out. You cannot shake hand with a single hand. If you don't speak out, I will never be able to help you out. Take this very seriously. So do not, under any circumstance, take it lightly. Right? So you have 30 seconds from now. I would like to definitely know the scope of improvement, if any. No use. I pity you, my dear friends. Anyways, let's take a step ahead. So now, the next thing that we have is the LSTM encoder-decoder model. Have a look at this. Yes. First and foremost thing, as you can see, I have created a function over here. And this is the function which is actually defining neural machine translation. So here is where we are defining and using the encoder-decoder architecture, which is the LSTM. So as you can see, the things that I am giving as input, first of all, the first input that you see over here is the vocab size, right? Vocab size is the input, which is the size of the vocabulary for the source language English. Similarly, you have it for the source language Hindi. Then you also have the maximum sequence input length, which is nothing but the maximum sequence length input sentences. In the same way, you have the maximum sequence length for output sequences. Embedding is nothing but the dimensions of the embedding. And lastly, when you talk about the hidden neurons or hidden, that's quite obvious. We are talking about how many LSTMs are we going to use. So we are going to create a model, and you can see after that, I'm having the encoder which is going to pre-process the text input. So when you see encoder inputs is equal to input shape, something like this, we know that the input is given with the shape of the sequence of tokenized words. Once that is done, and after the input, you know that we apply the embedding. So I'm giving the vocab size as the input. Output is the number of features I want to extract, and this is the functional API style of coding. So this encoder inputs are given as input over here, and the output is encoder embeddings. This encoder embeddings is given as input. LSTM with that many number of neurons is what is passed over here. So encoder LSTM doing this, and as you can see, we get the following things. Now, what is this encoder? This is nothing but the LSTM of certain neurons, and it gives me encoder outputs, history and the cell state. You remember, now we did that in the code where we had the history state and the cell state. If it is GRE, you will only have the history state. So the history and the cell state is what encoder is saving. And then you have the decoder, right? Embedding layer in place. You have the decoded embedding. Again, LSTM in place for getting these things. And you have the dense layer, which is the output for softmax by the decoder. And this is the functional API style which we have learned, which is going to call it. And it's done. Great. Or what an easy thing. Hidden units in LSTM is the number of neurons are we referring. Number of neurons in the LSTM, not the encoders. Every LSTM is nothing but an encoder. LSTM itself is the encoder. It is nothing but the LSTM. Yes, it is the same thing over here. In fact, in the previous two case studies where we did the sentiment analysis using LSTM and then the text generation using LSTM, in all of these cases, whatever was the meaning of the LSTM having the number of neurons, same is the meaning in this case as well, Nag. Things don't change. That's why I've taken this case study from level 0 to level N. For simple to difficult, and it is the same that we are talking about. Is that clear? As we did in the previous two case studies, exactly the same understanding. Yes. Of course, yes, that's correct. Because LSTM is recurrent now. When I say n neurons, that will run in that many time steps, or it will run it in the form of a loop. That is the idea behind it. Welcome. Now we say this is the same thing that we understood in the architecture. We are not doing anything new over here. After this, the next thing is now I'm writing a code to calculate the vocabulary sizes for the English and the Hindi data sets using our tokenizer. So I'm also over here. First thing is I'm saying that the vocabulary input size will be the length of token dot word index plus one. So just for your kind information, token dot word index is going to be nothing but a dictionary containing unique words mapped to their indices. Similarly, the length is the number of the unique words in the English data. And why are we doing plus one? We understood it that day as well when we talked about out of vocabulary. And here also the funda remains the same. So plus one is responsible for adding one extra token for padding. The same thing we are doing with Hindi, and we see the number of vocabulary size. English is less as compared to Hindi. If you want, you can just read it once again. And calculating the sequence length, which is straightforward only, right? You pass the text, you are giving the text, finding the length of the maximum sequence. That is what I'm doing with English and Hindi. And then finally, when I give a call to the create model, which I created above, I'm passing the vocabulary size, which I got here, vocabulary size output, maximum sequence length output, embedding dimensions, and the hidden units, which are this. And when I say I'm going to compile it, these all are the things. Optimizer, loss, and metrics. You can see going ahead with the defaults. So knowing the defaults is so important because this training is starting since now I have started this training at 3:08 p.m. today, and I have still completed only little bit of third epoch. There are total 10 epochs. I think I will have to keep my system on for entire night, and the fan is also running. So lot of efforts. Anything which is there behind the Mac is getting hot. That's the architecture. Input layer, embedding LSTM bends. Then this is where we are storing the things, right? So I'm defining callbacks. You know this callback very well. Monitor validation loss, patience 3. Checkpoint also we did during the LSTM where I'm saving the best values of the weights, right? That's all done. And model.fit on X train main and Y train main. So why am I saying this -1? Because it's last token from the decoder which I want to be excluded. Box and all things are good. This training. Right now I have just reached 3 and the training has to go on for 10 epochs. That's the result that I usually get, right? 96 and 96, quite good. Loss is also minimal. These are the model weights. I'm gonna save it so it will get saved into my system. And then I also plotted the loss. And you can see that if I train it further, maybe see this is not it stabilized, right? I think it can further go down. So ideally one should train for more number of epochs. This is less, right? So this is how it looks like. If you look at the accuracy also, there is a lot of scope for the accuracy to further go up. But that 10 epochs only took so long. This is what we realize. And then I give a call to the create model with the vocab size, sequence length, and all of these parameters and ask it to this. We can't really say that the model is overfitting. We can't really say it's overfitting unless and until you train it further because it looks like this has stabilized also. So you can't say it's overfitting. Look at the curves very carefully. Overfitting means it is like a crocodile mouth. It will become bigger and bigger. This is not the case over here. Are you getting this? Yes. I'll take a question at the last now because I think it will hamper the flow. So then I'm checking its thing on the first 200, right? Just to check its prediction on the first 200. So as you can see over here, we are just trying to figure out how it is able to work on the first 200 sentences. So just for your kind information, the first line where I say number of samples is equal to 100 comma length of X string. So basically, I'm just trying to ensure that we don't process more than 100 test samples. So it will ensure that if the X test has less than 100 rows, then it will take all the available rows. That's why I said minimum of 100 or length of X test. The advantage of this is this will limit the computation time during the testing. Then I'm creating an empty list to store all the model predictions. And I say, you see over here, single X test main I colon I plus one. So it is selecting one test sample at index I. And I colon I plus one means it will ensure that it remains 2D array instead of converting it to a 1D array. So the model expects the input batch shape, right? Even if it's a single sample, it will expect it in the form of a group. And that's why you have to do this thing. And then you have the single prediction on which the model is going to predict. And that is what we see. And here, finally, you have this decoding. So now this function decode prediction is mainly responsible over here. So I'll say this function is used to convert the predicted numerical tokens into human readable sentence using the tokenizer. So the first thing is I'm calling this function. I say predictions is equal to NP array. What am I doing? I'm basically converting it into a NumPy array. All the predictions are converted into a NumPy array. It will ensure that the functions that handle different types of inputs like lists, tensors, etc. Then I'm trying to find out the most likely tokens. So np.argmax predictions is equal to 1 else axis equal to this. So basically what am I saying is I say if the prediction has multiple dimensions, apply the argmax. Yes, that's perfectly explained. Else take the prediction as it is. So basically when I'm applying the argmax, I am mainly trying to select the most probable to each position. And else in other case, I'll just select the prediction. So this basically transforms the probability distributions into actual token IDs. So the model does not directly output the words, right? But instead it's a matrix where each row ideally represents a word and each column represents a probability of the word at that position. I'll give you a quick example of it. If you're having a prediction array like this, and if you're taking the argmax, see the maximum of this is 0.5. Sorry, yeah, 0.5. Then maximum of this and maximum of this 0.6 and this is 0.3. Right, so it will be choosing the one with the maximum index. So this is that index 1 in this list. This is that index 0 and this is index 1. That's what it has chosen 101 in p.argmax. Then after that, holy. Okay. So then you have the decoded, yes, the decoded sentences. This is what we see over here. Because I said decoded sentences is equal to an empty list. So that is quite obvious from iterating over the model and converting them into a Hindi readable form. So I'll be storing all the final decoded Hindi sentences inside this list. Then I say for I, form a prediction in enumerate of this. So over here, what is basically predictions? So predictions is nothing but the output from the model, which is the predicted token sequences. And when I say enumerate over it, I'm looping through the predictions at the index side. And the decoded sentence, as you can see, you have the decode prediction over here. So it is going to convert the numerical tokens into Hindi using the talk Hindi in the Hindi tokenized. So basically, I would say that this function maps each predicted token to its corresponding word in the Hindi vocabulary. And then I'm going to append it to the decoded sentences and it will display the output. Now, see in the output, you might have seen unknown. So in the output below, unknown represents an unknown word that the model could not translate properly. That means the word is missing from the tokenizer's vocabulary or the model is unable to predict the word due to limited training data. Some sentences are mostly correct. If you observe the sentence number 6, right? Sun Khatta G 634 Khali unknown. So some of them have meaningful things. So the model in some other sentences actually failed you to translate. you see a lot of unknowns like this. It failed to translate wherever you see unknowns, and some of them are partially correct. And why is this happening? The reason this is happening because number one, I would say, is the vocabulary limitation. So the tokenizer might not contain all the Hindi words, therefore that could be the issue. So there is one more tokenization technique which is called as subword tokenization or byte pair encoding to handle the unknown words. Also, it might be possible that the training data is too small or the model is struggling with the uncommon words. And the third thing which can be a problem is LSTM has too few hidden neurons, so it might not be able to understand the complex pattern. So in this case, if we have to improve the model, we can say the first option that we can consider is to increase the data set size. The second one is a more advanced tokenization. So by that I mean, as I told you, we should go for subword tokenization, word piece, sentence piece, or byte pair encoding. Another thing is improve the model architecture. So instead of using this, the next one that we are going to look at is the transformer based architecture, which is way more powerful than this. That is why this didn't go ahead for a very long duration, and that's why the transformer architectures came into picture. And the next is you can fine tune the hyperparameters, which is one of the heart of our generative AI sessions. And that is what happens in this particular case. So overall, the output is not bad, but you understand there is a lot of efforts that we have to put in to ensure that we are getting the things that expected. And that completes this case. It could even be due to the apostrophe. It could be due to anything. But yes, this is what it is. I have given down some steps over here, which you can definitely go through. Now, before I conclude the session, I would like to take the question asked by Nagdeep. Meanwhile, anyone has any question, feel free to put it in the chat. Nagdeep says, as we see in LSTM, there are several recursive loops till the number of the input words. But with respect to code, can't we consider all these loops as a single part of the dense layer that we added using the LSTM function? Yes, that's a very insightful question, I would say. So, see, we are asking whether the recurrence in the LSTM is internally handled as a part of LSTM and whether it can be considered equivalent to a dense layer. Here, LSTM uses a loop internally for sequential processing. So, in the mathematical formulation, LSTM processes the input word by word. So, every time in the code, when you define an LSTM layer, you need to understand that we don't explicitly write a for loop to iterate over the words. The TensorFlow, Keras, they do those things within the LSTM layer automatically. Whereas a dense layer, it just applies a single transformation like a matrix multiplication W into X plus B, as I explained you on the very first day of deep learning. So LSTM is maintaining that internal loop where all of these hidden states are updated at each step. So dense layer is like applying a single formula to all the words at once, whereas LSTM is like reading a sentence word by updating the memory, which is the hidden state at each step. So can you consider all the LSTM loops as a part of a single dense layer? No. LSTM contains internal loops over the time, whereas the dense layer does not contain that. LSTM has a memory. We remember explaining the architecture, there is a cell state, which is nothing but the memory. Dense layer does not have that. Else, there was no role of being there, right? What we studied overall in the architecture is it has internal loops, and that is why it is able to handle it. So LSTMs are not the part of the single dense layer. They automatically handle the recurrence. I'm talking about the transformer architecture or the transformer models. See how easy and convenient it is to use them. Number one, connect to GPU. Done. There was a time where I had to install transformers in Google Colab. Today it's not required because Google has already installed this library. So even if you don't do that, okay, so not required nowadays.
as this library is already installed in Google Colab. So I'm directly clicking on this. Let's see whether it works. You understood for training, it takes a huge amount of time. So we will not be training it. Rather, we'll be directly using the pre-trained transformer model. Are you all able to understand what am I trying to do over here? Pre-trained transformer models for summarization, because people have already trained on it in the past and these models are really state of the art, so there is no need as such for us to train it from the scratch. We can actually use the available pre-trained models. That is what is the idea behind it. All of you, are you clear with it? That's nice. Perfect. Now you might be thinking that, Darshan, from where have you got this code? I have copied this code. I'll tell you from where also. Pre-train means, is it specific some problem? Do you remember we had earlier classes on transfer learning? Did I explain you guys transfer learning? No. Okay. No problem. I'll explain you. So what is this essentially? See, last time we looked at neural machine translation. So what was neural machine translation? Where I wrote the entire code, I created the network, I built the network, and then I fit on it, and it took me almost 24 hours for the code to get executed. Now I don't have so much time. In fact, forget about me. Everyone has to train it for so long. So what they did, this model which is available, they saved it. We know how to save it. We have also seen the deployment part of it. The model can be saved. In fact, in our case also, you might have seen that we had saved this model and we are using this. In the same way now also, these are models which is being saved as .h5. H5 is nothing but the Google Colabs extension of saving the models. So lot of such state-of-the-art transformer models which are far more powerful than the attention models are already available. So this is what is called as a model which is already being trained on. Therefore, I call it as the pre-trained models. So this pre-trained model is what I'm directly going to call like an API, and I will ask it a question, whatever I want, and it should do the task for me. So someone has already done the training, I am directly calling it. So because the training is already done, the weights of the model are also directly available. That is how it is. Now, do you understand what is a pre-trained model? Someone has already trained this model. That is what is a pre-trained model, right? Perfect. Now, don't ask me any questions for a while. Give me some space to explain. So I imported this. Then if you see, all of these are commented. Everything is commented except this line. I'm executing this. I'm creating an object of pipeline by the name summarizer. Passing this model. What is this model? You don't know, na? Right click, copy. Should copy over there. Paste. See, I copied this part. Copied this. I copied this part, and when I pasted it, it's here. This is diverting me to a new website called as Hugging Face. So what is Hugging Face? Hugging Face is the website where lot of pre-trained models are saved. You can find it over here. Have a look at it. You will have various types of models over here. Multimodal, computer vision model, NLP model, audio model, tabular model. Right now, I am looking into natural language processing models. Specifically, I'm looking into summarization. So, I click on this. You can also click on this. When you click on the summarization, so it will show you all the summarization model. Yeah, it's selected. All of these are the summarization model. And then what you do is you come on to this. This is a summarization model by Facebook called as BART large CNN. Let's open it. Now, if you see, first of all, don't look into every part of the website. The first thing is they have given us the endpoint, which you see over here. It says that you can give a sentence and I can help out. And in fact, they have given an example as well. Example one. So this example is there. After that, it will automatically start computing the summary of this and which is below. I'm talking about this one. Let's say I'm taking Holi is coming, right? So looking on this, Wikipedia, and let's say I'm randomly taking a paragraph. I paste it over here and let's say compute. Let's look at the summary. So this is already a deployed model. It says Holi is a sacred, ancient, and tradition of the Hindus, a holiday in many states of India, with regional holidays in other countries. It is celebrated at the end of winter on the last full moon day of the Hindu lunisolar calendar, marking the spring. The date falls typically in the March, but sometimes late February of the Gregorian calendar. This works good as expected. You can also try it out. Now, what is this model? Well, that is what we can learn about here. It says that someone has already trained this model on which data, for how long, what are the overall results of the model. Read here. This is the model fine-tuned for CNN Daily Mail. So it is a pre-trained model on English language. You cannot use German or other things. Let's say if I go to ChatGPT and if I paste this and I say translate to German. So this model is not capable of understanding this. Come over here, compute. Did that. Now I go to ChatGPT. Come over here and I say I gave the same German thing and I asked it to translate to English. So this is what it says. Okay, because it was able to do that, but not necessary. Yeah. And what is it saying? Let's see. It says that we have trained it on English language. We fine-tuned it on the CNN Daily Mail. What is CNN Daily Mail? Click on this. This is the data set on which it trained. Let me just, yeah. This is the data on which it is trained. You can see, you can go through it, everything in detail. What is the data set about? That also one can study over here. It is an English language dataset containing over 300,000 unique news articles. So it is good for news article summarization, not for Holi, which is written by journalists at CNN and the Daily Mail. The current version supports extractive and abstractive summarization. Extractive is extracting from these things, and abstractive is understanding that and summarizing as a whole. Supported task, just like your blue score, you also have a rogue score for the translations. Again, if I go over here and I say, we understood, right? What is blue score in NMT? What is acceptable range for it? What is rogue score and how is it different? Blue score, let's only look at the important things. It basically is about the quality of the translations. Acceptable range, C, 0 to 1. 0 to 10, poor translation. We got this. I got this, right? 0.1718. So it was something understandable, but many errors. 30 to 50 is good with many errors. 50 to 70 is high quality. 70 plus is nearly perfect. Okay. What is ROC score? It stands for Recall Oriented Understudy for Gisting Evaluation. It is again a set of metrics to evaluate text summarization and machine generated text, focusing on recall. So, unlike Blue, which emphasizes precision, that is how much machine translation resembles the reference, Rogue emphasizes on how much of the reference of the translations appear in the machine generated output. Distinguish. Blue is precision oriented, how much of the machine output is correct. Rogue is how much reference is captured because we have to summarize it. It is best for machine translation. This is best for text summarization. Blue, human like 30 to 60 is expected. Here we expect 50 to 90. Okay, this looks good so far. And because I'm happy with it, I'm gonna come over here and then I say the output summary of the blue score with a rogue score of 44.1. That's good. Then you can also see the data set, article, example, etc., things. Number of instances in the training data, and you have to read about it. Then after this, you also have where you can find, and all of these are open source models, huh? All of them are free to use. Then they talk about the BART. They say that, hey, it is an encoder model. Both are encoder with a bidirectional encoder and autoregressive GPT like decoder, etc. This is particularly effective when fine-tuned for text generation, intended use and limitations. Then how to use it from transformers import pipeline. From transformers import pipeline.
Summarizer is equal to pipeline, that is create an object of it, give the task, and if you want this Facebook BART large model, basically just copy this line. Yes, here. Right now it's commented, but sometime earlier in the previous session, I had shown this demonstration to my students. This is done. So I have this model in place, but right now I'm using the Schiffler BART model. Then you give an article. So easy, whatever article you want, you give it. And then I am saying summarizer is equal to that article, which has to be summarized, maximum length and the minimum length of the article, and do sample is equal to false. So let us say for some reason, we do not understand this code. I can, though it's quite obvious, but let's say coming over here, and I say explain each line of code, because that is itself the we are loading the pre-trained model. So first importing then I'm loading the model, then I'm creating an article, and I'm asking it to summarize the article into minimum length 30, and do sample is equal to false. So do sample is equal to false means do not sample, basically do not repeat the things. So we import the transformer library from the pre-trained model, as I told you. Pipeline is nothing but the class inside which you have everything. Then summarization, it indicates that it's a text summarization pipeline. Then this is the name of the model. And what is this model? It tells us. Then after that, whatever you want to do, limits the article to maximum of this, minimum of this. And do sample is disable sampling and forces greedy. That is, choose the most likely word at each step instead of generating random variations. As you can see, it has given an article which we just gave is vibrant and such a long article. I say summarize it in 50 characters maximum, minimum 20. Do sample equal, and that is what the output that you see over here. So if you now look into the code, I imported transformers pipeline. Yes. From where will I get this name? That's very simple, right? So from where will you get this name is I just Googled for it. It landed me over here. You know, this copy button is the one that will give you the name, this copy button. So I come over here and I paste it. Model is equal to, I'll just delete this and control V. Same thing comes, load that. Model is loaded. It is over here. You can see the line. So this is the transformer model which is getting loaded and it's freely available. It is establishing connection via Hugging Face. First and foremost, you will have to, meanwhile, you'll have to go and create your profile over here. That kind of has become mandatory nowadays. Earlier, it was not. And then the model will be downloaded. You can see so many tokenizer is downloaded, tensors, etc., etc. Here, there is an article. You don't always have to be, give your boss the finger. Maybe it's your first day on the job. Perhaps your manager made an announcement. You are asked to scan your fingerprint, etc., etc. Some article is there. I say summarizer, take this article, minimum, maximum is this much length, and do sample is equal to false. And that's the output. Employers are starting to use time clock machines that fingerprint employees. The machines are tied to your unique characteristics such as face, fingerprints, how you talk, and even how you walk. The Center for Disease Control says that coronavirus can remain on surface for years. Similarly, I took one more article about the G20, which happened in Mumbai recently. So that's a long article about it. The G2 was founded in 1999 after the Asian financial crisis as forum for financial ministers and central bank governors to discuss global economic and financial issues. It has expanded its agenda to include the trade, climate change, sustainable development, health, agriculture, energy, environment, and anti-corruption. Similarly, I took one article on machine unlearning. Very interesting. And look at the summary. And our model. This is the meeting summary model. So you can load any model in this way. So many models are there. I'll show you one random thing. Let's say for some reason, I'm commenting it out and I don't know which model to use. I'm thinking of going for which can be a good model. I can sort it by trending. Gamma is by Google. This is summarize adapter and anything else. Small Turkish summarization. We will not understand. It is anyways the default one. We summarize. Python code explainer. That looks interesting. Let me take that. I have never taken it. So what is that model trained on? Everything is there. Then you see over here, model name is also given.
It is by some person. I'll just try to copy this and see if I can utilize it over here directly. And then I'll do it as a separate cell only. Yeah, let it be there. Here also it's still downloading actually. Now, yes. Meanwhile, let me take your question. You asked me over here how to select the right model. See, now I give you two options. Number one, would you prefer to train a model from scratch where in spite of me investing 24 hours, I got just a blue score of 0.17? Do you prefer to use a pre-trained model? Obviously, the answer to that is you will prefer to use a pre-trained model. Then which is the good model? I don't know. Who knows it? No one knows that. Yes, so you have to find out the pre-trained model by doing it as a part of your research. You have to go through the website, read what is that model about, what it can help you, and then with an educated guess, think of using it. But at least it is going to save your time that you were required for doing the pre-training. Are you getting that thing? Yes. Same question by Yusuf as well. Just loaded. Yes. And it gave some error. No, actually, this was the older one. Let me run it again. Model is loading. You can see the size of the model, 2.95 GB. And you can see, yeah, this is what it's saying. Create a function, preprocess the function that creates this. To do so, you should do this. At first, we need something to be converted from text to string. At last, we'll replace space by space. At last, we'll call the tokenized function. That's exactly what it is saying. And then you have to say join and all. So you can see next step is to join them together along with the list of tokens. Text summarization model. Coming on to a very good question given by Nag. In the traditional machine learning and deep learning, we use TensorFlow, scikit-learn, and many were pre-trained. None of them were pre-trained. That's completely wrong. We had trained it right from the scratch, but often we had to retrain them with one custom. They are not the pre-trained models. Just like here, the library is transformer. I'm trying to understand why MLDL require retraining with custom data and TensorFlow models. No, absolutely wrong question, Nagdeep. We were training during our machine learning and deep learning from the scratch. Now also this training has happened. It has taken care of by someone else and the model is saved in the form of dot or dot pickle file. And that is what we are using. I hope you are able to get it. That's a 100% opposite understanding of what I explained to you so far. We had trained the model from the scratch. Over here, we are directly consuming the model which someone else has already trained upon. Sometimes I really worry about you, Nagdeep. Please don't get confused. It's a very straightforward concept. So understand where it is used and where not. Exactly. Those were libraries. So now I'll take it out. I'll download it. And let's say first notebook on summarization. I'll share it with you also. Try executing at your end as well. You all are using your systems, right, at the moment? All of you are using systems? Yes, you can download it locally as well. But don't be so much, what do you call, overwhelming. Stay connected with patience. I'll explain you everything. Another thing is there is no need to download it locally. Downloading locally is altogether a different process. You need that environment as well. Focus on understanding the topics. Rest we will understand it later, right? Perfect. When we get into fine tuning and all, we'll be doing all these things. Don't worry about it. Yes. So I want you all to execute this notebook. Not now, Akash. You please get it from Anish. Anish will help you out for the same. Right now, I'm in a session. I think just a second. If I have the zipped version of it, I'll share it quickly. I guess if this was the one, zip, 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 zip. I don't know. I'll just try to see if I can. I'll share it. No, it's not allowing me to share. I guess today we have this additional thing as well. Here it is, Akash. It's coming in the chat box. Yeah, I think you can download it now. Just confirm me when you are able to download it. Great. Everyone will be executing these books with me. This is one of the very important thing. I'll be just there in a minute. By the time you execute, I'll just use the washroom. My dear cricketer, are you all done? Very good. I know. I just went outside. I don't watch cricket. My wife said Virat is out, so everyone is stressed. I was like, okay, which match is going on? So my father said finals. Which finals? Some cup so going. Okay, fine. By the way, I don't watch cricket. Very rarely I watch it.
I'm certainly not a fan of. So let's, oh, yes. I don't know whether it's good or bad. Half of them will start hating me. But how come, Darshan, you don't like this? God knows. Yes. I used to watch. Today, the thing is, I just know the names of the Indian players. Sometimes I might even forget the names. If you tell me, yeah, this one, yes, I know him. But I don't get into details of lot of things. Let's go ahead. We have to cover the GAN architecture as well today. This is properly generative AI, where you're actually using the Gen AI models, Hugging Face, right? This is true generative AI session which is going on. Next, again, this is commented. And yes, one thing I want to see over here is it's saying that device is set to use CUDA, which is 0. Now, what does that mean? Well, before that, let me just run it. This is sentiment analysis notebook. Just look at the screen. Pay attention once again on the screen. Sentiment analysis notebook over here. And then if you see, I have not supplied even a single model. Earlier, I used to say summarization followed by model equal to. Here also you see model equal to, but I didn't supply a model. Let's see what happens. If you do not supply a model, it will go ahead with the default model. If you don't supply a model, it will go ahead with a default model. You see, no model was supplied. It defaulted to the Distilbert base uncase fine-tune SST English. The link is also given. You can click on it and you will understand that it has defaulted to this model. Information about this model can be read over here. I'm not interested in going through it. You have the option to use this. So here I can put in any sentence like they have given an example. I like you. I love you. Computing. It doesn't take so long. Sometimes it happens. Oh, this is too long, man. It never takes so long. Anyway, no problem. I can refresh it. That can be one thing. Let me refresh. You see, yeah, positive 1, negative 0. So I'm coming over here. And what is, it always says over here that, okay, you have not specified. What is this device set used to this? There is a parameter called as device. It's not shown in the documentation. I don't know here at the bottom if it is shown. No, there is no parameter shown called as device. Right? You don't see it. In fact, in Collab only, I'll copy this and I'll go over here in this. Where is it? Gemini. And I can say code is this. And then I can say over here, the output which I have got is this. And I say how to use the GPU. See, basically, I'm using the CPU because the device CUDA is set to 0. There is a parameter called as device which takes two values. Have a look at it, right? There is a parameter called as device to use the values. I don't know if it suggests yes, device equal to 0. So if you have multiple GPUs, you can change the device to 1 or 2 to select the desired ones. This is what it says. So here, to use the GPU, you should say device equal to 0. I never used it, but you should use that. So I say over here, device equal to 0. Now when I run it, device set to use CUDA, I'm still getting the same thing. If I say device equal to 1, it will say that, hey, the GPU is not available. So better you set it to 0 only. Okay. Now I say I'm giving it a sentence. The model is the default one. It's a general purpose model. So I'm giving it a general purpose sentence. So I'm calling the Senti pipeline. I'm extremely happy to share my knowledge with you all. It is positive and the score is on a range of 0 to 1. It is 0.99% sure that it's a positive one. In the same way, we have this text classification model, which is specifically fine-tuned for financial news sentiment analysis. So over here, I am giving it a sentence like Reliance Industry shares continues to be on the Jefferies buy list with a price target of 2990 and upcoming renewable ventures key positive. It says it's a positive sentence with this. I give it a sentence, senti pipeline. I'm sad that this year has come to an end. It's a negative sentiment, and we get this. Let me ask it a little odd sentence, right? I say that the stock prices of Walmart are not performing good. So I'm giving it indirectly. Good is also there, not is also there. Our NLP model was struggling to handle this. But here, see, it is 99% sure that it's a negative sentiment. Or me saying that Walmart stock is not good to invest today. So I'm not saying it's bad, I'm saying is not good. You see, our text classification model, if you remember, sentiment review analysis on the restaurant reviews data set, it was badly suffering in such cases. Here, this is way more better. Do you understand the power of the transformer model over here again? Yes. In spite of getting 72% accuracy, but it was not performing well. So this is the next notebook for sentiment analysis, which I want you to execute. One thing, every time your notebook is over, it's important that you go to runtime and disconnect and delete runtime because you are using the free version. If you are using a free version, it cannot execute more than one notebook with the GPU connected. So disconnect and delete runtime. Can it handle sarcasm? Chandra, try asking it and do let me know. My answer to your question is yes. I want you to try out that and let me know here only in the example. Tell me what example you tried and also paste in. Basically, Chandra, you paste these two things. I want you to paste these two things. The first thing is tell me what you gave, and the second is what you got. Okay? I'll wait for this from all of you. Cool. We sent a screenshot. That's awesome. Let me see. Vacuum cleaner? Chandra? Vacuum cleaner? What is this model for, Chandra? But try sarcasm in stocks, na? This model is fine-tuned for financial news analysis. The second one is, what did you say? Oh, great, another meeting. Just what I needed to make my day better. And this camera sucks. Give it some news related thing. It will not perform well on that. Try giving some news related prompts and let me know that stock related things. See, if you are using this model, Chandra, the fine-tuned model for financial news sentiment analysis, then you please give sarcastic sentence for that. So I'll do one thing. Generate some sarcastic examples for. Try out these three, these are good. And there is one negative one as well. Meanwhile, I'll check what you have shared. Wow, my stocks are down again. Guess I will just retire early with all these gains. What's the output? I gave you sentences. Oh, cricket here. Come back to play cricket here. You shared something. Just a second. Okay, inflation at 40-year high. Perfect. Who wouldn't want to pay triple for the gross? Still be told the economy is thriving. And it is a negative sentiment, but it is saying it's positive with a score of 0.99. Failed. Oh wow. Stock market just crashed again by 1%. What a fantastic time to go all in. Who doesn't love to bargain sale on a financial ruin? 98% negative. Okay, one by Nagdev as well. And 98% negative by 1%. Okay, cool. Let me go ahead with the next one now. I think we invested a good amount of time here. The next one is, again, this is not required. So I am this time using a vision transformer or model which has eyes. So as you can see, vision transform for feature extraction. What will it do? Given an image, it will extract features from that. You remember, na, convolutional neural network where the features were extracted. Yes, the same thing. And then we have the vision transformer for image classification, whose job would be to take the features and perform the classification. Then I'm also loading IMG from image for some reason, and give me 10 seconds. Sorry. So I was saying, what is this image library used for? We'll see it later. Oh, here only we see it, right? So for displaying this, we have it, right? And ipython.display image. So I do that. Then I have to upload an image. So this is the Egyptian cat photo. I'm uploading Simplilearn D9, this ball photo and this cat, right? So let's say this time I'm going ahead with the ball. Uploaded. I will share with you also those two photos so that whenever you try it, You have it. I'm copying the path of this, copy path, and closing it. So I don't want to go ahead with the cat. I want to go ahead with the ball. So this ball thing, I'm going to delete it and I'm say control V. File name loaded. So that is loaded into file name variable. That is what I'm plotting over here just to see what is there. I have already seen that, but I just used it. Okay, this is the image of what? What is this image of? Don't say it's a ball. Huh? Tell me something better about the ball. Cricket ball, right? Basketball. Yes. And the earlier image was of a Egyptian cat, by the way. That also you can try it out. So first and foremost, I am opening the image. Now you know that image has to be open and the type of the image is what I'm checking. It is a JPEG. Oh, sorry, ball image. Now, what are we calling it as? It's ball.jpg. So I will have to use this. Now I am calling the vision transformer feature extractor from pre-train. So this is the Google's model. This one, Control C and opening in a new tab. What is this model trained on? You can see ImageNet dataset. It is trained on ImageNet dataset, which consists of total 21,000 classes of image. And there are 14 million images inside this. All of these images were given to the model. And before giving that, they were converted to the shape 224 cross 224. And then it is fine-tuned on the image data set and it can now predict on 1,000 different classes. And that paper can be seen over here. This is the research paper where it says images were 16 cross 16 words, 2020, right? October 2020. They have also given an inference endpoint over here. I'll just try to upload it. I'll take the image of Egyptian cat and let's see what it predicts. The coding has become so simple now. It should tell me that it's an Egyptian cat, right? I'm just trying to see if it does tell me or not. Taking a lot of time for the first time. It never takes. See, Egyptian cat. Okay, I see that it can detect so many classes. Training data, ImageNet dataset. I can click on that. Let's see what it says. These are the 1,000 classes of ImageNet dataset. So I just want to try randomly one of it. So if I say wombat, I'm just randomly Googling for the image of the wombat and JPEG. So let's take maybe something good where little bad. Let's say this one. Face is not directly visible and I'm taking that. I'm just saving this image in, you can give any name to it. I'm just giving it for my convenience. And this is the place where I'll just upload the image wombat and see what it is. Wombat with 100% accuracy. You can try it in your system as well with any of these 1,000 classes, which would make sense. What are these 1,000 classes? Well, these are the ones. So we are extracting features from this and saving it into feature extractor. And then I'm also calling the vision transformer for image classification, which is loaded from here and saving it into model. So that will load the model. After that, I am giving, see this feature extractor and model. These are the two things that we have. The image array is given and return PT. PT stands for pre-train. So it has to return me the tensors from the pre-train. So feature extractor is responsible for extracting features from this image, save it into inputs. And these inputs are what is passed to this model because this model is responsible for classification. So this will extract features and this will actually do the classification. So we give that over here. Now the inputs can be, the features can be few features or many features. We don't know how many they are. So therefore you have star star, which is for accepting any number of parameters. At any point of time, you don't understand this, you can always say explain code and it will explain you the same thing, right? So here, first line is anyways what we understand. Inputs are going to be nothing but the input features. And over here, what is this star star inputs? We are passing the pre-processed image data to the model with a double asterisk. So double asterisk is what? Input features. There can be 100 features for one image. There can be 5 lakh features for some other image. For some other image, there were only 30,000 features. So the number of features are going to change. So star star is responsible for unpacking them and ensuring that the model accepts it. That is what is the main idea behind it. So I do that and I'll be getting total 1,000 outputs. You can see the shape of the logits. 1 cross 1,000. And I'll be choosing the one with the maximum probability. So I use the argmax. And what I get as output is 430. Now, what is 430? You will have to go over here and check. Control F, 430 kya hai? Basketball. But I want to see here. So you have directly with the model, right? You remember the model which you loaded, model. So this model has a method called as ID label. Just pass this 430 and you get the basketball. This is the entire code done together, and this is on this Egyptian cat, right? This one photo. Image is available on a public repository. So I have the entire code written over here, and I want to see whether it predicts it that it's Egyptian cat as well. And it is. All works good. I go to runtime, I disconnect it, and I call it as image classification. Question by Chandra, can we give any picture and it can predict, or should it be only from the training dataset which will give good accuracy? The same goes with the model. The model is trained on that data, Chandra. So how can you expect it to be given anything? Just a second. Can we give any picture and it can predict? Or should it be only from the training data? Chandra, again, you already know the answer to this question. This question goes to the audience. Chandra has asked a question. This question goes to the audience to answer. Let me see how many of them are able to answer it. Come back from the cricket mode and please answer Chandra's question. I'm sure you should be able to figure it out. Can we give any picture and can predict, or should it be from the training data set which will have a good accuracy? No, no. Chandra, you are asking a very simple question, which I'm expecting the answer of which you already know. So if you recall this old school thing that we have been doing for so long, Chandra, when we had X and Y, we used to divide the data into train and into test. Then we used to ask the model to fit on this. And then we used to look at the accuracy on the train by comparing this. Then we used to ask it to predict on the test and accuracy on this test data set. So we not giving the unseen images or text data or the raw data earlier as well. Yes, the only thing is the unseen data must be similar to the training data, not the same. Same applies over here as well, Chandra. What is the confusion? Where are you lost? How should I unmute you? You raise your hand. By the time you find that option, I only give you the access. Yes. Tell me, Chandra.
So that I'm not lost by the way I'm asking. See, the thing what I'm trying to ask you is similar to any of the machine learning models or any of the models that we have seen earlier, right? So where we have training, testing, all that is fine. So we also have something called as out of sample, and we give that, and basis that we predict whether it is a good trained model or not. So similarly, now you have given a basketball, and basketball is there in the training data set, right? So it can identify that it's a basketball because the model has seen the image and it actually identified that it's a basketball. Let's say
Okay.
you give a cricket ball. My question is, will it be able to identify or not? Or should it be part of the same training data set is my question. That's it.
Now, first of all, did you check whether cricket ball is a part of this 1,000 classes?
No, I didn't check. I randomly, told you.
Okay, let us go ahead with an assumption. Assuming that cricket ball is not a part of that. Okay. If it is not a part, that means it is not trained on the cricket ball. So
Correct.
obviously it should not be able to predict because it has no output variable where it can predict. Just like here it said Egyptian cat, there is no way it can predict it's a cricket ball. Maybe worse to worse, it can end up giving you a basketball in case. But again, as we understand, garbage in, garbage out. It's not even necessary that it will give you a basketball. It can give you something abrupt as well. So answer to your question is still the same. If the image is not a part of the training data set and not even similar to something that it has studied, so there is no way it can predict. And if cricket ball was a part of this, then definitely it should be able to predict. That means if it was a part of the training data set, then it should be able to predict. The idea is very simple. If Chandra is shown something, then Chandra will be able to predict on something similar. If Chandra is never shown ever that, hey, this is the cricket ball, but he knows what is the basketball, so it will not understand that, okay. So if that is the case, logically, if I show you a watermelon, then also because it is circle, you may say that, hey, this is a basketball. That should not happen. So the funda is still garbage in, garbage out. If anything comes out of the training data which is not similar to the training data, expect the output to be garbage. Let us try to give one such thing, Chandra. So I am, that are very difficult to find it. Let's say, let me see, do I have a mobile over here? I have it. Let us look for some very obvious image of a spectacle so that it's very easy for it to recognize, right? That's a very clear and obvious image. Let me save it. It's just similar to, oh, it's not in the right format. I think I need to go for something else. Let's see, garbage in, garbage out, or what? Ultimately, even I am not the control of it. I don't know what's gonna come. But according to me, it's a clear scene of garbage in, garbage out. But let's see. If it is going to take anything more than 10 seconds than this, I'm gonna refresh it. Sunglasses. Those spectacles was not there. It is predicting as sunglasses, and that is not wrong as well. Dark glasses, because they have trained it on similar things. So think of an object which it has not been trained on. So what can be the thing? Maybe getting over here. Torch, a torch is also there. What I can see over here in my room. Bag. Bag will definitely be there. Post bag, this bag, punching bag. Tell me one object, Chandra, which you think is not likely to be there. Just a guess. Anyone? Any object which is not likely to be there. Shirt is also there. 1,000 classes are there, right? It almost covers everything. Speakers, okay. It's there. Sad. 1,000 classes is like almost covering everything. Air conditioner. Okay, that's Earth star is there. I don't know what is Earth star. Let me see what is Earth star. Okay, Earth star is the flower, but Earth is not there. No problem. Let's go for something like that. And I'll take a very obvious image of a Earth. Same image as fingers crossed. Now, yeah, this is what you think, but we really don't know. Let's see. Fingers crossed, we don't know. And Earth. That is also there. It's predicting it with a low score, planetarium, and it's quite close to it. Okay. But anyways, Chandra, I guess you got the idea that if it is something which is not there, garbage in, garbage out. If it is there, it will predict. Accuracies may differ, right? You think of any object, anyone, and try to put in the things over here, and but the funda remains the same as machine learning, garbage in, garbage. I hope you understand my point. And no, forget about accuracy. The idea is very simple, that the model will not predict it correctly. So garbage in, garbage out means the score would be low, or it may also happen that it predicts it wrongly with high score. That is also possible. But anyways, it can happen. And that's one thing which I wanted to show you all. Next, so vision transformer comes to an end. Yeah, you have to try it, right? Please try this out. Feature engineering is about matching the features, right? So the features of Earth will not match to anything else. It's very smart over there. It's a transformer architecture. Now, you can, with an image which is not there in the training data, and confirm it. The idea of entire thing remains same. How much so ever time you try to ask me 100 different questions in 100 different ways, my answer to all of this would be very simple: garbage in, garbage out. You get convinced or you don't get convinced, answer is the same. If there is something which it has not seen, don't expect it to predict, or don't expect it to work the way you are thinking. It may not. If it worked, you are just lucky, but don't expect it. Yes, that's exactly what everyone says in the world of machine learning, and so do I. Perfect. Quickly try executing this book. Egyptian cat. Once you are done, just put me a message in the chat as done. Kash is done. Others also. I think before again today, I think entire lecture will go on hugging face only. Oh, cricketers, come on. Quickly say done. Update your status. Okay, Ashish. Akdeep has sent some image.
Actually, you have to change that path, na? You uploaded, you didn't upload that image. Left side say upload Egyptian cat image. If you are calling it as cat, you have to upload that image, na, Nagdeep? Did you upload the image which I shared you? Share me your screen. Let me see. Screen share karo. Nagdeep, you can speak. You can unmute. I've given you the access. Sorry, your voice, microphone as usual. Adjust it.
Am I audible now? Where do we upload it actually, like into the
Bring your
Hugging?
bring your screen up.
Okay.
Beautiful photo. Is this you and your wife and kid?
Yeah.
Oh, so nice. To the left side, you see the bar, vertical bar on the left. There, little up. Yes, there.
This
Little
one's
down. No, down. Down. Yes. Click there, and you see the arrow going up, little up. Arrow pointing up. Yes. From there, you upload.
okay.
Which one is that? Yeah, this one.
Cat.
Double open. And the path of that will be copied into the file name equal to.
Okay. So here will be the path, so copy path.
Correct. And file name equal to will be that path instead of this.
Okay.
And that's it. Rest all is well sorted.
Okay. I think it should come. Got it. Yeah.
Yep.
Thank you, sir.
Welcome.
Thank you.
Should I stop your share?
Yeah. I'm trying to remove the share.
I did it. I did. No problem. Sutano, you're also busy in watching the match today. Okay. Harikant is done. Yusuf is done. What is the status? Are we winning or losing? Nagdeep, just update me once you are done. Then we can go ahead. Means we'll go on a break. I think that would be better. We are winning. Okay, we are winning. Great. Done. Perfect. So I think it's all understood to everyone. The next one that we have to look into is exactly what I planned for today, which was the generative adversarial networks, but it's a different architecture called as the stable diffusion. We'll be having a separate session on stable diffusion. We'll discuss all these things once we come back from the break. So as you can see, it's 8. So we'll be coming back at 9:16, 20 minutes from now. I'll see you then. So follow the time at the top right, 9:16. We are back. Thank you. Enjoy your break. See you then. Welcome back, everyone. One wicket down. People are stressed. Okay, going ahead. Assuming you all are back, right? Now, the next one is stable diffusion. I was telling you all that stable diffusion, we will have one specific session on stable diffusion, its architecture. And what is this stable diffusion model? Well, it is a open source model. Just like Hugging Face is an open source model, stable diffusion is also open source model, mainly for image generation. Image generation. So it will generate images. The first thing, connecting. Diffusers needs to be installed for this. So that is what I'm installing. Pip install accelerate. In this, you have lot of places where you have to do this. So you can just take down the small explanation for this. Basically, stable diffusion means I'm installing the stable diffusion library by saying diffusers, right? So I'm installing the diffuser library. As you can see, the specific library that we are installing. And this is library developed by Hugging Face and is commonly used for working with the diffusion model. So then we have accelerate as well. Accelerate, as the name says, it is used for fastening the process of the GPU, right? So it will properly do the quantization so that your output comes out faster and best use of GPU is done. You can see this library is developed by Hugging to simplify the process of training and running the models, especially the deep learning models with multiple GPUs, TPUs. As I said, is mainly used for helping the resource management efficiently, distributing the training across the devices and optimize the performance. So we use that, and it takes a lot of time to install, but that's okay. Still, it gives so many things. And then after, I have imported stable diffusion because I'll be using the, why not TensorFlow? Because stable diffusion guys have implemented this using PyTorch only. So you will only find the PyTorch model of this. So the model which I'm using is the Runway ML. If you see, that's the one where it says, tell me the image that you want to generate. So I'm saying that I want to generate the image of beautiful futuristic scenery of green mountains, sunrise in snowy
else? Definitely not a great image, but not bad also. Okay. If I say Mickey Mouse with, that's good. Where it will not work good, let's say a man walking in the corporate tall building for his office. Something wrong, maybe. I don't know. Oops. Anyways, you can try it later. You also have the access to it. You can try it. So that's the model and no longer affiliated with Runway ML. Modifiers to this model are in red or green. Stable diffusion. Now we can use diffusion in Runway ML. Now depicted. So I get over here and look for some other version of stable diffusion. If yes, I'll just go over here into models and in the image, text image here. So many models are available. Stable diffusion model. Let's say I'm going ahead with this. And here I say man walking, man corporate meeting in tech office. You see over here animated images. If I say a man drinking coffee and finding it satisfying, I'm referring to this link. I say a realistic man, not animated. You have been given it, Harikant. Please try it and share us the image. I think you also tried it. I think that could be the reason. Okay, share us the image. I'll also try it out. That's good. Man writing with his left hand and it is going right hand. This could be due to the bias in the data. That's looking good. Yes, I'm trying to give negative prompt. Okay. So it's saying that you cannot use it more. Someone please try using this and tell me how are you getting it. Try this and share with me the image. Stable diffusion is still not good for generating images which are related to the humans, right? It's not really great on that. Tell me what output are you getting? Because it contacted another bomb. Anyone is doing it, na? I hope I'm having realistic expectations. Let me see why are people not responding. That is the reason I thought so. Google sign up. 25 runs, 26 balls. That is the reason. Then why do you join? Better don't join now. Why are you fooling me? If you are there in the session, please be active, else don't be active. Unnecessary, you're putting pressure on me. It's just a very simple process. Sign up with this Google account and it's done. It hardly takes few seconds. Your email yet not come. Oh, still it is giving right only. Yes. It's not good with generation of the human images, but that's how it is. But if you, that's good. If I go and take this same prompt to ChatGPT for the same thing, you see, this is using the DALI model, right? And this is super awesome. Here also, I can see where Harikant also is showing a right only. Most of the images that it has been trained on are likely to be right, and therefore there is a bias in the data, is what I understand. See here also, in spite of saying left, it is showing right. I say that's right hand, not left. Please regenerate. Let me see. Does it take feedback? Could be possible. See, OpenAI is also not able to do that. But this is not a big problem. Okay, this can be easily handled. That's not a big problem. Okay, coming to our notebook, right? So we had installed diffusers, then this, and then I'm loading the model, and this model is what I'm passing over here because it's a torch one. You have to give the of an astronaut riding a horse on Mars. And that prompt is given over here, and I'm asking it to generate the image. So pre-trained model is loading. You can see the size. Since we saw some usage limits for free account on inference, if you try to do inference locally on the system, should it be? Yes, still you will be having that usage limit because it will be ultimately hitting the same API. So if you're doing it locally, yes, there will be, basically these models are very costly and they are paid as well. So now this image is generated and you can see this is the one. I just loaded it and this is the image of the astronaut riding on a horse on Mars. That's what we see. I will go to runtime, but yes, what you are saying is correct. It needs a paid account But the open source one, if you're downloading it, it will consume a lot of resources. You just can't even think of executing this on your local system, or else there are some UIs available like Comfy UI, which can help you to achieve this. If you want, you can research about it. In fact, it is also written on their webpage somewhere. I don't see it here, but it's there. If you just go on to, this is used for doing the things locally. It's open source node based that allows users to generate image and text of images via the prompts, and this can be done locally. Control A, Control C. You can do it using UI as well. Then you can research about it. Comfy UI, it's good. You can do that locally as well. So yes, I mean, this is one thing. The next is sentence similarity, which I want to show you. So I'm installing the sentence transformers first of all, then importing the sentence transformer, and then I am giving two sentences. This is an example sentence. Each sentence is converted. Passing these sentences to the model. How? As you can see, the model is being called sentence transformer, and this is the model, right? So you can give sentence and the sentences to compare, right? Let's look at one example which is given. This is a happy person. Sentence compared to this is a happy dog. That is a very happy person. Today is a sunny day. This is something which they have newly called. So basically, this is the restriction from the Hugging Face to make money. Earlier, it was completely free. The recent one. Anyways, we can do it via the API call. So after having this installed, I'm going to pass it to the model embeddings, and you can see these are the embeddings for the sentences which are generated. And after the embeddings are generated, sentence one, sentence two, and encode the sentence to obtain the embeddings. But there is a similarity check. I think God knows. Similarly, this is token classification. You know what it does? You have a sentence. Neither had given Syria the lead with the well-struck header in the 7th minute. This example is given for parts of speech recognition. You can see it is saying that, hey, neither is a person, and it's saying that with 99% probability for the index one, which is this. Then the next one, right? The next word it is saying nad, starting from 0 to 3. That's a word. Then after that, entity, it's a person with score as this index location 2. And then it's starting from 3 to 5. And after that, in this way, it is going on for each and everything. So here this khadi, right? So this kha going from 8 to 11, it is recognizing this as a person, and so on and so forth. The dar, hash dar, that is something before that. Then after that, Syria, right? So it is considered as the beginning of the location. The word is Syria. So it was able to identify the parts of speech over here. The last one is text to image. Look at this beautiful image. So what are we doing? First of all, I'm installing the necessary libraries. Then I'm loading these two models, which are responsible for text to image generation. This is again stable diffusion 1.0 only. Loading the model, you can see the model ID is given to from tree train. The data type is float 16. It's always good to give float 16. Float 32 can be given, but it will not accommodate in your system. Floating point 16 is always preferred. Then once I have this pipe has to be scheduled, and therefore you give it to the LSM scheduler, which is nothing but the latent consistency model, which will ensure that the latency is the least, and then transferring it to CUDA. Once that is done, the things are very simple. That thing is given to the LoRa, and then I'm giving it a prompt. Self-portrait oil painting, a beautiful cyborg with golden hair, 8K. And then that will get saved over here, but I like to generate it, right? So I'm giving the prompt. Number of inference steps is 4. That is, it will try it for 4 iterations and try to get a best one. Guidance scale is 0. We are not playing with it. And I'm asking it to generate the image, which will come here only. The topic for next time is going to be the generative adversarial networks. We'll be designing how to create the network from the scratch. You see the model is getting downloaded. It takes a lot of time. I mean, it's not 89 MB, 67 MB. So it takes time. You need a good internet, 244 MB and so on. Here it will come now. And you can see what was the prompt. Self-portrait oil painting, a beautiful cyborg with golden hair, 8K. Beautiful image. Say black hair. Oh, that's interesting. Cyber dog with yellow headphones. Oh, it doesn't look like a cyber dog for sure. But yeah. I can definitely. There are many other things also which I planned, but as and when we go ahead, we'll be looking into that notebooks as well. Now, for this notebook to run, you will have to configure the Hugging Face, but that I will, for time being, leave it to you. Yes, we get started with the generative adversarial networks today. If you have ever heard about generative adversarial networks, that's awesome. If not, I would like to tell you that it's going to be really an awesome learning experience because generative adversarial network is a very cool network. As I told you, this will help you generate new images. So let's discuss about it. Okay. Now, this is one of the great advancement in machine learning for all of us, and therefore this is going to be one of the very interesting thing that we are going to study here, which is the generative adversarial networks. So they have a numerous applications, and one of the fanciest application of the GANs, we call it as generative adversarial network, GANs, is the face recognition. So if you go to this page, which is called as this person does not exist.com, you will see in action that these images which you see here are of the people who do not exist. They have been fully generated by using a network. And this is fascinating considering how detailed our expressions are in this image and how to generate faces with this. This is going to be one of the craziest applications. So we are going to understand this mathematics right from the scratch over here. But before that, let's try going to the website. This person does not exist.com. And you can see over here. So you see this, the background, or the I guess this the ear of the next person problem. One more, you see how real it is. Look at this. I mean, so nice and real. All perfect. So this network has been trained on millions of images and it has captured the faces. And this is very much similar to the convolutional neural network. So it has captured the faces and on the features captured on the faces, it is now using those features to generate a new image, as you see over here. See, whenever you try using this to generate more than one face, this is where it doesn't work as well as expected. Right. So, yep, it's just a proof that yes, it's a generated image. Right. So we are going to understand this mathematics with just a single pair or a single layer neural network to understand this detailed mathematics. So that's going to be something which is interesting for all of us. Okay. So let's get started with this. I'm going to keep it very understandable. Let us try to develop a general idea or a general intuition. So that will give you a good overall understanding of how the flow is expected to be whenever you talk about the generative adversarial network. So over here, whenever you talk of, they consist of pair of neural networks that are going to fight with each other. One is called as generator and the other is called as the discriminator. And they behave like a counterfeiter and a cop. This is like the counterfeiter police, and this is like the counterfeiter, which is nothing but thief, and the cop, which is the counterfeiter over here, which is the thief or the chore, is constantly trying to make fake paintings. And the cop is constantly trying to catch the counterfeiter, right? So you have this chore and police, as you can see, left hand side, which is the counterfeiter, and the right hand side, which is the discriminator, or which is also called as this. So this guy is going to create a image, and obviously his role is to catch what is a real image and what is not. So he creates an image, this counterfeiter, and the discriminator catches it. No, this is not an original image. So what happens over the time is, based on the feedback from this guy, he understands what is good and what is bad. So this time this cop says no. So counterfeiter understands that, okay, let me make something better. Then he further prepares one more image like this.
He again says no, but when he prepares an image like this, he says yes. So basically, you can consider like, there is a examination going on in the classroom. So a student is caught copying. He doesn't have the copying skills. Next time, he improved over that. But he's again caught copying. He understood, okay, I should not do this also. Next time, he again improved. He is again caught copying. A day will come where he becomes so smart that he copies and the supervisor never comes to know because he has improved, right? So for the supervisor, there is no scope to improve, but for the counterfeiter, there's a lot of scope to improve, and that is exactly what happens over here, right? So the cop is going to keep on continuously feeding this and improve its painting until he learns to finally paint a perfect one. And the painting, something which fools the cop. Aha. So he generates it and he says, yes, I won it. And that is exactly the idea behind it. As you can see over here, this is how the overall things are going to happen, right? So whenever you have a pair of networks, the generator and the discriminator, and we can train them over here. So what happens is, we have a counterfeiter, we have a cop. Now, this cop is going to receive fake images as well as real images. Whatever image he receives, maybe from here or maybe from here, he just has to say that whether the image is real or fake. Obviously, if the real image is given, because it is a trained classifier which we have studied so far, classification. So for real images, it is likely to say it's real only. And this is going to be smart in catching fake images. But this guy is also improving over time. So a time will come when he is not able to catch the fake images. So I am giving it a real image and I am giving it a fake image. So real image will be detected as being real. But when a generator gives a fake image, it detects it's a fake image. This happens. So generator understands that, okay, this is a fake image. He doesn't understand what is the real image, but he understands there is a fake image. So then the generator generates one more and he says, no, this is also a fake image. Sorry, this is a real one. This came from here. Generator again understands that, okay, that earlier image got caught. Let me give something like this. It again detects that, hey, this is a fake image. Now this happens again and again. Obviously, real images are also given parallelly, one by one, but we are interested in the generator output. He generates another image and now he says, it's a real image, as you see over here. So essentially, we have a set of real images and a set of fake images generated by the generator, and the discriminator is tending to identify which images or which images are the ones which are coming from the generator. And the generator over here is trained to fool the discriminator. That's something which is very, very important, right? So the discriminator's job is to classify the images either as a real or a fake image. So now let us try to build a very, very simple pair of generative adversarial networks. So simple that we will be able to understand the mathematics in the simplest way. So now over here, imagine, this is our setting. So our setting is like we are living in a world which is called slanted land. So this world is what is called as slanted line, where everybody looks slightly elongated and they walks at a 45-degree angle, right? So if you look at this angle, 45-degree angle. So this world has a technology, but it is not as developed as our world. Technology is there in their planet as well, but it's not as developed as in our world. They have a computer screen as well, but that computer screen is having a display images. Best of the best resolution that they have discovered so far is 2 times 2.
So they have a black and white 2x2 pixel screen, as you see on the screen. Also, they have developed a neural network, but that neural network is also very simple. As a matter of fact, they only know neural network of one layer, but I can show you still that even in this simple world, we can still create a pair of generative adversarial networks that will generate faces of the people who will live in the slanted land. So let's understand this. First understand the setting and then we'll go ahead. So this is the setting, first of all, that we need to remember, right? So that's setting part is what we need to remember over here. Now we say, okay, so we are living in a slanted line. Everyone is at a 45-degree angle. The best of the best screen resolution is 2x2, and you have only one layer neural network, which is being developed so far. Now let's consider over here that we have total four faces of the people who live in the slanted line. Four faces. Obviously, their faces are also slanted. If you notice that everybody is elongated and tilted 45 degrees to the left, since the screen are only 2x2 pixels. So this is how the pictures of the people look in the screen. They look like sucked across the diagonal and a backward slash, right? That's exactly what we see. Obviously, you see darker colors over here. And these are good images, huh? These are good images of faces. Make a note of this. Wherever you see, these are good images. But wherever you see this, right? So this is how noisy images look like. These are not faces since they do not look like a backslash, and these are mostly generated randomly. So in simple words, friends, I would just like to help you understand, see the goal. The goal for the network is to distinguish between the faces like these from the noisy images or the non-faces like this. Understand this problem statement really well, right? So what are faces and what are non-faces is what we need to understand. Now, see, I mean, this is understood. Darker values are the available values and lighter are not. Now, what will I do after this? Here I say, I'll just replace these colors by some numbers. You can see I have put in a proper color bar over here. Darker color is 1, lighter color is 0. So obviously you see higher values means it's faces and lower values means not face. So as like here you don't see a pattern, it's a noise. But here you see higher values, same over here, same over here. Then after that, so this helps us understand. So going forward, we'll be only talking with respect to numbers only, right? So we have a scale where white pixel has value 0 and black pixel has value 1. Now, you may have seen this in the opposite way in real life because grayscale values, I know 0 is black and 1 is white, but this is just for our understanding. I know when I taught about the MNIST data set, 0 was black and 255 was white. I know it very well. We will do it like this, right? So, but don't get confused, right? This is just a small part of mathematics which I'm trying to explain you. And I have just attached a pixel value in this 2x2 screens. Okay, so now let's go ahead and build our discriminator. Discriminator we have been building consistently. What is there over here, right? So the first thing is, how do computers train them and start by building the discriminator? For that, we need to have our first question, which is, how are we going to tell the faces apart from the non-faces? It's very easy, right? Notice in the faces, if you see in the top left and the bottom right corners, there are large values, and that is because the pixels are darker, whereas the other two corners have smaller because their pixels are light. And how do you tell, whether these are faces? Well, that can be done in a very simple way by adding the values corresponding to the top left and the bottom right corners and then subtracting the values from the corresponding other two corners. Something like this. add these two values. Therefore, I have associated plus with this. Same applies over here and subtract this. How to confirm? The way we can do this is by doing W into X. Now, what will happen, you will always see very high values in the real images, and in the noisy images, the value will be low. You might be thinking, can you explain with an example? Yes, definitely. Have a look at this. See, I'm considering the value over here to be 1. This is 1. This is also 1. That's minus 1. 1 into 1 plus 0 into minus 1 plus 0 into minus 1 plus 1 into 1 equals 2. Same thing over here. 1, 1, minus 1. 1 into 0.25 plus 1 into 0.75 plus minus 1 into plus minus 1 into 0.5, which gives us this. This is what we understand. Now, how do you interpret this over here? After you get all these things, the way we can do that is we can add a cutoff threshold. Let's say I'm considering the threshold to be 1. So say that any image that crosses 1 or higher is a face, and any image which is less than 1 is not a face, or it is a noisy image. So is 2 greater than 1? Yes, so it's a face. Is minus 0.5 greater than 1? No, it's a noise. This is what is the mathematical part that we have got. Now, after this, we can say that, see, in neural network lingo, if I have to demonstrate this to you, I need to have a neural network, which means there will be a neural network with 4 input pixels, which look something like this, where the values of our 4 pixels get multiplied by +1 or -1, purely depending on what diagonal they are on. And then we subtract a total value of 1 or the bias which we add these 4 new numbers. And then we look at the score, right? Whether the score is greater than 1, or based on that, we classify the image. Like, these values have to be multiplied with positive ones, right? And these are with the negative ones. So that's what I'm saying, these are my inputs x1, x2, x3, x4. This has to be multiplied by +1. This also has to be multiplied by +1. This and this has to be multiplied by -1. That's the bias value. So what happens over here essentially is this: 1 into 1 plus 0 into -1 plus 0 into -1 plus 1 into 1 plus bias, which is bias. So it's basically Wx plus B. So that is classified as another face in this case. This images in a face, because it is getting a score of 1. So we can also put the probability that something is a face by using sigmoid function, where we apply the sigmoid like this. So I got the output over here, right? As you can see, when I solve it, 1 into 1 is 1 plus 0, 1 minus 1. So +1 -1 gone. Output is +1. So that's what I said. The output is +1. And then we are going to apply the sigmoid, because that's exactly what happens, right? If you recall the neural network, we did say over here, activation function of Wx plus B. So Wx plus B is computed. Activation function I am applying is a sigmoid over here, let's say. So if I am applying a sigmoid as the activation function, we know that the sigmoid will always give the value between 0 to 1. And see, whenever you see numbers which are close to 1 or numbers which are close to 0, like that's one thing, and we can get any value, right? So for example, here, if I'm doing sigmoid of 1, so what does sigmoid of 1 happen? So x value is 1. So when you look at the sigmoid of 1, it gives you 0.73. Sigmoid of 1 is 0.73. It will look, hey, it's 0.73, about 0.5. If yes, then it will give the output as 1. If it is below 0.5, then it will give the output as 0. And that's why, because it's 0.73, it will finally consider giving the output. So basically, what are we trying to say in this? That it is assigning to this image a probability of 73% that this is a face. Since it is a high probability, which is greater than 50%, we conclude that the discriminator thinks that the image is a face, and which is correct as well. That if you notice, that's exactly how the neural networks thick edges are positive, and then the thin edges I have given, which are in blue, as the negative. And this is the convention that we'll be using throughout our GANs. So if we now enter a noisy image, right, which is not a face, still, the corners are by positive and the non-corners are negative. And when you do that, I get this. And when you actually end up solving this particular thing, the calculation gives you the value as minus 0.5. Now, after getting this minus 0.5, you are definitely going to pass it sigmoid. And what does sigmoid of minus 0.5 give? Well, when you apply the sigmoid is going to give you 0.37, and because 0.37 is below 0.5, so this is where the value is less than 50%. So we conclude that the discriminator thinks that this image is not a, or the discriminator is correct again, right? Okay. Now let's get into the generator. But before that, I would like to come to you all and ask you, what is the status so far? Great. Very good. So I can assume everyone has understood the things. That's nice. Then perfect. Thank you very much for calling it good, great, nice explanation, understood, and all those things. Now let's get into the thief. Discriminator is exactly what we have studied so far. WX plus B, which we have studied in our first lecture of deep learning for the MSc. We also studied it during our CNN for classification. So discriminator is the same, but now what comes new is how are the images created, and that is going to be a new learning. And before that, I want you to just excuse me for 10-15 seconds. I actually need a coffee. I don't know why, but feeling a little sleepy. Just give me 10-15 seconds. I'll be there. Maybe because it's a theory class and I'm only speaking, I don't know. Or maybe you guys are less interactive. All of a sudden, I started feeling a little sleepy. So let me come back to normal. I'll just get a coffee, 10-15 seconds. I don't have to make it. I'll just have to tell it someone in my family. So I'll be there in 15 seconds. This is the variational autoencoder, no, generative adversarial network. This is a notebook which is given by Simplilearn on generative adversarial network. I thought it ran, but this actually went into an infinite loop and kernel crashed. I don't know why. It's training. No worries. So this is responsible for generating new images, and you'll be seeing the output something like this. Bad, very bad. Anyways, we'll talk about it later. I just want to keep on coming to this periodically and keep on checking what's the status. So now we are getting into building the let's go and build a generator, and this is going to be nothing but a neural network that will output faces. To build a generator that will take into account that along faces, the two corners which are having the high values, and the other two corners which are having the low values. Whereas in the noisy images, you will see that anything can happen, right? But how is that happening? See, one thing is for sure, this into this, plus this into this, plus this into this, plus this into this. Be it here or be it here, the same thing happens. Okay, that is what we know for sure. So the question is how the generator works. So first we start by looking into this. So you know what does generator do? By its random function can be used for picking up a number in the C1. Okay. And then once it has picked up a number in the range 0, 1. So I'm assuming, what number can I assume? Let's say the number which is being taken over here is 0.7. So in general, the input will be a vector that comes from some fixed distributions. So now let's build a neural network that we really want. What we really want is to have some large values and some small ones, something like this. Right? That's exactly we said, right? This corner elongated 45 degree to have higher values, and this one should have lower values.
That's why I represented it by the thick and the thin edges, so it is very easy to understand what is higher and what is lower. Because if you remember, the large values are for the top left and the bottom right corner, and the small values are for the top right and the bottom left corner. Now, since I want the top output to be large, we will have to give it higher weight. So what am I doing is, because I want the output, this output to be large. Now, number 0.73 generated, I am multiplying that by plus 1. So 0.7 into 1 plus bias. What happens over here is plus bias. This value is going to come as a higher value. And let's see what you get over here. So when you do that, what you essentially get is going to be a score which is on a higher side, which is 1.7. Right. And now that we have this, let's look at the second value. Now the second value is so this came as 1.7. What will come over here? I want a value over here to be small. So I'm putting the negative numbers over here. I put a negative number over here. And what do we get for this, right? So that's going to be giving you minus 1.7. Similarly, here I again need a higher, and here I again need a lower value. So I'm going to put negative values over here, -1 and -1, and I get this value. And for the last one, I want a higher value. So as you can see, it's +1 and +1, and I get a higher value. So these are the values that we get. And once we have these values, we apply a sigmoid. And sigmoid of each of this is going to give us a probability in the range 0, 1. So what you get is 0.85, 0.15, 0.15, 0.85 over here, and that is exactly what we wanted. If you notice in our image, this actually looks like a diagonal, which is how we defined our faces, right? So we build this neural network by generating large values over here and the smaller values over here. So now no matter what values that the input is going to have, because you remember that it is between 0 and 1, and therefore this neural network will always generate a face. That means it will be a good generator. So bias is simply added. So if you have +1, that would be added only. So here also, as you can see, here I consider the bias to be 1. So for every neuron, you have a different bias, no? So that is why it is, for every neuron, I'm having a different bias. So for this neuron and this neuron, I'm considering a higher bias +1, and these two, I'm considering lower bias. Don't get confused with the concept of neural network, Shailesh. Is that making sense to you? That's nice. So how does that, whenever you talk about a neural network, right? So something which is a good network, or maybe something is bad, we do that by eyeballing the weights. This is how it's normally done, right? We have to train a neural network to get the best possible weights for this. And let me tell you, this is nothing but a error function in place, error or a cost function. And that's the way to tell the network how it is doing in order to improve. If the error is large, then the network is not doing well. And if the error is small, it's doing well. Or do we need to reuse something to get the error minimum? But see, we understood how this thing works. But it's not about us. Are we here to do these things manually? Of course not. So we want to ensure that a machine understands it. So the thing is, how to make a machine understand that, okay, this is going good or this is going bad. The generator is improving or the generator is not improving. How to make a machine understand this. And that is the biggest challenge as of now. Be active. See, this is how it is created by randomly choosing a number between 0 and 1, and then multiplying by the weights and getting the output. Go through this, you will get an idea. Yes, just go through it once. Okay, now that we have an idea about this, we will take it ahead. How to ensure that a machine understands this, and that is where I would like to propose a function, and this is how machine understands it. This is not for you or me. It is for a machine. Machine says I can make this thing possible by using a log loss function. This is a tricky part You may ask me the same thing again and again. So I'm just warning you to be more active, right? Because now that storytelling is not going to continue, we are going to look into many new and more meaningful things. So everyone make a note of this. See, I am running it. How much time has over? Around 19 minutes? 19 minutes. It looks like it has been stuck up anyways. This is epoch number 5, which is going on. This is the loss of discriminant. There's a reason I came over here. There is a loss of discriminant, and there is a loss of the generator across every epoch. That is exactly what we are studying here, the loss. So now I want to say that the natural logarithm, that is the logarithm to the base e to the y, it appears that among a lot of error functions, this one is something which works good for generative adversarial networks. So let's say first that we have a label of 1 and the model predicted 0.1. Understand this, a label is the actual and the predicted over here turns out to be 0.1. Now, this is a bad prediction because we are expecting 1, the actual should be 1, and it predicted 0, which is in a range of 0 to 1. This is very, very bad. So we should produce, in this case, the error to be very large because, boss, you had to predict this, but you predicted this. So the error is expected to be very large because 0.1 is quite far from what is expected in the actual, which is 1. On the other hand, if the label is 1, right, so that's the actual and that's the predicted. If that's the scenario, and it is expected to be 1 and the model predicted as 0.9, that's a good scenario. That's a good prediction because the prediction is very close to the label. And so this time the error should be small. So actual, predicted. So actual and predicted, way different, large error. Actual, predicted, very close, small error. So how then can we find a formula for this error? If you notice that the negative natural logarithm of 0.1 is what? This is 0.1, which is the prediction. I'm using the log loss function. So I'm saying, what is minus ln of this? It's 2.3. What's so great over here? 2.3 is a large value, right? And if I say minus ln of 0.9, because the difference is huge, minus ln of that value gives a small value, and minus ln of that value gives the large values, right? So error is large and error is small. That is how the error is computed by the machine. Negative logarithm of 0.9 is 0.1, which is low. As a matter of fact, the closer the number is to 1, the smaller is the negative logarithm. And therefore, when the label is 1, the function's negative logarithm of the prediction is good error function as of now. After this is 0. And the prediction, oh, that's a good scenario, right? Actual is 0 and predicted is 0 point. That's a good scenario. So I want the error to be small. And here, the actual is this, predicted is that I want the error to be large. I want the error to be large. So can negative logarithm work over here? Well, no. Negative logarithm will not work over here. So what should I use in this particular scenario is little change in the negative logarithm. So the slight change is the error function will be minus ln of not prediction, but 1 minus prediction. That's the slight change over here. Does that really work? One can quickly check it out. So if I say what is minus ln of what? 1 minus prediction minus ln of 1 minus 0.9 minus ln of 0.1, which is 1 minus, that's what, 1, oh, 1 minus 0.1, na. I thought something went little ulta, 0.1, which is 0.9, and that gives a 0.1. Similarly here, minus ln of 1 minus 0.9, which is minus 11.1, which is 2.3. As you can see here, I want it to be small. It is small. Here I wanted it to be large, and it is large as well.
So this is something which is one of the most important point that you should look into. Revise it. If you have understood this, please type U in the chat because this is one of the very important thing and completes almost 50% of our architecture. Hardcore mathematics. Very great. Yes. So here we cannot use this. Of course, yes. No, that's exactly what I invested so much energy in making you understand right now. Sid. You cannot use the absolute error. Pradeep says, why is there a minus sign for log, which is expected to be positive? Because that is how it is, right? So there is a log function as well, and there is a negative log function as well. So in deep learning, negative log function is also something which is very popular because this is how it works and turns out to be in favor. So see, basically, it is like you are having a car inside which there is a hole like this. You're planning to buy this car. So you will look for a metal sheet and cut it exactly like this. And then you'll fit it over here and then you will do the welding. That's exactly what we are doing, right? So our problem statement is to predict this. So we're predicting that this function turns out to be the best, and that is the reason I'm using it. So basically, based on the problem statement, you're trying to fit in the right mathematics so that your problem for generation of the images is solved. That's exactly what we call as the research, Pradeep. So these all are results of continuous research, right? No one knew that. These are invented during the research. Welcome. Okay. Now this topic is going to be continued now. So we understand that. See, what do we understand? When we want the prediction to be one, like here, right? Here, when the actual is one and we want the prediction to be one. That's exactly what we say. No? Actual is one and I wish the prediction would have been one and it is very close to it. So whenever you want the prediction to be one, right? So this is the formula. And whenever you want the prediction to be zero, like this. Okay, so here that's the actual and prediction. I want the prediction to be zero and it is very close to it. That's the actual and that's the prediction. I want the prediction to be zero. It is way more away from it. So whenever you want to ensure that this thing is properly quantified, we use the minus ln of 1 minus prediction. And that is exactly what am I trying to say, that when you want the prediction to be 1, you don't use minus ln of 1 minus prediction, which means that if you want it to be 1, we define the log loss to be negative logarithm of the prediction node. And if you notice, if you see in the graph as well, right? So the negative logarithm of x is big when it is close to 0, and it is small when the prediction is close to 1. And then when the label is 0, which means that I want the prediction to be close to 0. And then we use an error function, which is the negative logarithm of 1 minus that, which looks like this. All right. So this is exactly how we see that, whenever the prediction is closer to 0, there is low error. And when the prediction is close to 1, there is a high error. These two are the error functions that we are going to use for training the generator and the discriminator based on if we want the prediction to be 0 or we want the prediction to be 1. Then, so now that we have our functions, we can get to the meat of the training process, which is nothing but the back propagation. So I'll explain it very briefly, the way we train our networks. And that is by first take data point and performing what you call a forward propagation, right? So you start from here next, and then you get the output over here, right? So you do the forward propagation, and after performing the forward propagation, what you get ultimately is the error prediction, and from that you calculate the error, which is based on the log loss that we previously defined, and then we proceed to take the derivatives to go in the backward direction and update all the weights And all of this is done using the chain rule, which will tell us how much to update each particular weight in order to decrease the error the best way. And that is exactly what is done using the process which we call as a gradient descent. So long story short, what you do essentially whenever you talk of gradient descent is you plot the arrows back to calculate the gradient, which is nothing but the slope, which is the direction of the greatest growth, and then take tiny steps in the direction of the negatives. Have a look at this figure, right? So calculate the slope move, and this is how the training happens till the network becomes expert, right? So that is exactly what is called as gradient descent, but ultimately what happens over here is just the weight updations. That's it. What happens over here is nothing but the weight updations. This is what we have understood so far. Now I am talking about training the generator and the discriminator. So we are ready to do that. But what we have to do over here is to put the right error function at the right place. So it's going to generate any value in the range 0 to 1, and discriminator is going to take that and identify whether it's a real or a fake one, whether it's a real face or non-face. So what am I going to do is, see our parent neural network, if you notice the weights are yet not defined. So we start by defining the random numbers. So I pick up any value in the range 0 to 1, and then after we have selected any values in the range 0 to 1, then we are going to give that as an input to the generator. So what we do is a forward propagation. So the generator is responsible for obtaining some image. It's a face image which I wanted to generate, but it is fake. So it may not generate face. No problem. Now it generated something. It's a random one, right? So I don't think it looks like a face. It looks like a noise. What do you think? It's looking like a face or it's looking like a noise based on the output of the generator? N for noise, F for face. Noise, right? Yes, even I think so. Randomly generated one image, and that turned out to be a useless image. That's exactly what we see over here. Okay, so this is what we get. And then after that, once it had generated this, we know, right? So all WX plus sigmoid has given us this value. What will happen to the discriminator? Discriminator is going to take up this image and it is going to classify whether it's a real or fake image. And how is that going to happen? Well, you pass it ahead, you have this train network where you will be having these things. So discriminator wants, if the discriminator was great in doing the classification, it should output that image is not a face. Generated image from the generator is going to be classified by the discriminator either as fake or not fake. So I do that over here. I calculate the error function. And then what I want the neural network to output over here. See, you only tell me after doing that, I got the output as 0.68. What I want the neural network to output, I want it to output that, hey, this is not a face. As a discriminator, I would like to output over here that this is not a face. So I want the output to be 0. So how should I minimize this? So I'll be using the minus log of 1 minus 0.68, and we know how this is going to minimize the thing from our previous slides. And if you want a 1, right? So if the discriminator wants to detect it as 1, and then in that case, we use it like this, right? So in order to generate an image so good, so real that the discriminator classifies it as a real. So in that case, the function is going to be like this. So the generator wants the whole neural network, the connection of the 2 to output to 1. That means that the error function from the generator is negative log of the prediction, which is minus ln of 0.68. This will help us to train the weights of the generator. And on the other hand, if you look at the thing, I also call it as if G of Z, listen to this very carefully. If G of Z is the output of the generator and D of G of Z is the output of the discriminator, then the error function for the generator is negative ln of D of G of Z. And similarly over here, it is 1 minus D of G of Z. So that is what they are trying to minimize in their fight or in their war, one versus others, and they all try to improve. So generator tries to reduce its loss function, discriminator also tries to reduce its loss function. So discriminator tries to become better and better at catching it. However, because generator is also becoming better, so you see that a time will come when generator also becomes awesome, so awesome that discriminator is not able to catch it. All right, so the error function is the only one which changed over here. Have a close look at it. I'll be just there in 10 seconds. Okay. Now that was an important thing for all of us, and now we are almost at the end of it. Now see how convenient and cool is this going to be. So that is what we are going to study the next thing, na Nagdeep? Patience, patience. So this was just the working of it. Now we are going to study that as the next thing. Okay. So now we understood whatever are the fundamental, whatever is the base required, that all things are ready. Now let's actually understand how are we going to go ahead with this, right? So how does this thing happen? This is just one. So I say, what have we understood? We understood that these two error functions are fighting against each other. How is this happening? See, one thing which we understand over here for sure is that the generator is going to use negative logarithm of d of g of z, and the error function from the discriminator is negative logarithm 1 minus d of z. So here, the derivatives of these two are what help us update the weights of both the neural networks in order to improve that particular prediction. So if you notice that these two error functions are fighting against each other, but that is okay because the error function only changes the generator weights and the blue error function only changes the discriminator weights. So this is responsible for changing only these weights and this is responsible for changing only these weights, and therefore they do not collide with each other. They simply improve. Both of them keep on continuously improving. One is to produce the counterfeited images and other is to catch the counterfeited images. So when you repeat this thing many times, where there will be continuous forward backward propagation and you keep on repeating this many times, then what we do over here is we pick up a random value. Now this is where we are talking about the crux now, and my laptop got hungry, just plugged in the power. Yes. So now we repeat this process for many times. So what are we doing is we are every time going to randomly pick up a number for a value of z, and that value is going to be anywhere between 0 and 1 as we decided. So we apply the generator to produce fake images. So some number is generated and we know that there is a function d of g of z minus ln of d of g of z. So this is going to generate fake image. Right, and then on the fake image, you apply a discriminator. You know how it works, how it backpropagates. So it is going to do that and it will, now, once you have this thing, then this fake image, you apply the discriminator on this particular image and you use the back propagation to update the weights on both the generator and discriminator. All right. So what happens is one fake image is generated, multiplied, you get some output, you know what we want, what you want and what it predicted based on that. And then, of course, you also give a real image, right? So real image is like this. So discriminator will receive both. It's one fake image from the generator and one real image for here, right? So when we actually take a real image and we plug it into the discriminator on the updated weights again, and we use the back propagation. So what happens is after many iterations or epochs, it happens so many times that after so many number of epochs, what we are left out
is the training in the notebook, right? So you have the weights over here, right? So we got these values for the weights to make it easier. So I have drawn the thick edges over here for the positive weights, and I have drawn thin edges over here for the negative weights or the zero weights over here, right? So here it's minus ln of d of g of z. This is minus ln of 1 minus d of g of z. So these networks, as you can see, right, so they are continuously going to fight with each other. Generator tries to minimize the loss function, and obviously this loss function is responsible for predicting a fake image which is as good as a real image, and the time comes when the generator becomes better and better and better. And discriminator, obviously, see, if I show you a painting of Mona Lisa and I ask you to identify whether it is fake or real, so we are not experts in figuring it out unless and until if I show you a very pathetic painting. So a time comes when someone creates the first copy of any product so nice that it looks like the original one. And that is why generator becomes better, and it becomes very difficult for anyone to predict whether the watch which I'm wearing is a original Rolex watch or it is a duplicate one. So that is how generator becomes more and more powerful. It starts generating realistic images, which are images of the faces, and the discriminator is not able to actually distinguish the faces from the non-faces because the faces generated themselves are so nice that it becomes really difficult for the generator to catch it, or discriminator to catch it. So that is how this overall thing happens. So let's just convince ourselves. If you look at the generator, if you notice that since the input is between 0 and 1, and top two edges are positive, and then the sigmoid value of this output is large, which is going to give the value of this pixel over here. Therefore, that pixel is also going to be large value. And similarly, when these two values are also positive and they give a large value for this pixel. So after this, now when these values are given with a negative value, they are obviously going to give you small values for this pixel, and then these two values are going to give you the negative values. So again, a small value, and that is exactly how you are able to get something which is a diagonal man, right? Diagonal face, slanted line, 2 cross 2 pixels, as we want. And candidly, like this is the resident of the slanted land over here. That's exactly what we built using the generative adversarial network. And that marks the end of it. That's just a basic Python code for it, but we will not be using this for doing it. That is just for our understanding, right? So we're not going to get into these all things. That would be crazy, right? So basically, remember the thief or the counterfeit and the cop story. Coming to you, Nagdeep, is that making sense to you now? How are the things actually happening? Great, superb, very nice. Anyone else having any other questions? One question: generator works on its own feedback. A discriminator's feedback, na? Generator works on the discriminator's feedback. See, you generator is creating an image, which is the counterfeit creating an image, and it is sending to the discriminator. So basically, I am a counterfeit and I am responsible for generating fake images of Mona Lisa and sell it in the market. So I create a bad image. People catch it. Hey, this is duplicate. People catch it. It's a duplicate. It's not like this. It's not like that. A time will come where I become so awesome that people are not able to catch it. So this is coming as a feedback from the people. So here also it's from the description. Is that clear? Log loss functions run on both. Where are you sleeping, man? See here. See, this is the function on the generate, and 1 minus is the function on the discriminator. Right? Perfect. Will you be giving us in the tree a relevant examples of using GAN, maybe a sample use case? Your deepfake images are one of the best examples of GAN. That is quite obvious. So today, at least,
We are going to go ahead with a simple one. Then going forward, see wherever you think images can be generated, it is generative adversarial networks. Your deepfakes are one of the best possible examples, or the DALI model, right? So that also works on the similar principle. You talk about any tool or any large language model which is used for generating an image. You call it as a generator. As simple as that, guys. As simple as that. They are simply responsible for generating images. Okay. Now, if you look into the status, now this notebook is also responsible for generating images, but I have just cleared off the output, but I have kept the original output as well. So what I have done over here is, if you look, this is the notebook. This is coming from your resource folder only. Generating fake images with the GANs. As you can see, what are we doing is, we know the MNIST data set, right? So we are loading the MNIST data set, and then we are creating a generator and discriminator. And after that, we are compiling the thing, training the model. And after training the model, here in this case, my training is still going on, but we are going to train the model. And after training the model, you will be able to generate images. These are a few of the images which are generated. They are really very bad, at least in the notebook which I see shared with me from the Simplilearn folder. But it's not that it's bad, it's just because it's been trained for less number of epochs. You need to train for many more epochs than this. Are the discriminators able to detect images from the deepfake? Now, see, these questions are very irrelevant at this point of time. Think about it. How can you say this with confidence? Are they able to detect it from the deepfake? Maybe they are not as well. It purely depends on use case to use case. You really cannot say that they will be able to detect or they will not. Usually, some cases they succeed, some cases they do not, because the images generated are so real that it is difficult to get caught, right? Unless and until you see that typical style in the image. So unless and until that thing is there, it is not easy to catch the image between a deep fake and a real one. Can there be such adversarial framework in the language processing as well? Absolutely not. See, here we are having it. In the text processing, you don't need such a framework. Here you are purely working with the pixels, right? So for generating images, it makes sense. But for generating text, we have our transformer architecture, which we studied, which is far more better than this. Since I don't want to play with the pixel values in the text data, I want to play with the vectors, right? Which we found using the word to vec. So why will I use this architecture and unnecessarily increase the computation cost if my transformers are capable of doing it the best way? In the Simplilearn's notebook example, they're only generating images using generator, just one epoch. Does it also have discriminator in the notebook? I don't know what you are referring to. And I think you should not get into those things before I teach. If you look the notebook, I clearly see there is a generator and discriminator both. Okay, so that maybe you're referring to some other resource. I have absolute no idea about it. Please confirm it. I see everything as expected. So it's still running. It's been so long, but it's execution queue. I think maybe need to do it. If I try to push it to Google Colab for doing it, maybe does that work? This is to here. No, I'll take Simplilearn's notebook. I have my own notebooks also where there are some real world examples. But to start with, I'll go ahead with this Simplilearn's notebook only. What am I going for? Set runtime, change to T4, edit, clear outputs, runtime, run. This may take a longer time, but that's okay. So these earlier steps will happen very fast. Problem will come with the later one. So this training takes a lot of time. It's trained for 50 epochs. It's here right now. This is where it's going to take a lot. It takes hours and hours for training. In fact, if I just look into these notebooks, right, which I have for GANs, we actually generated faces like this. We have a discriminator as well, generator as well. And I trained on it. See, these are the results at epoch 0. We will go through this notebook later on, but I'm just trying to show you. At epoch 5th, this is at 10th epoch. See, every time it is becoming better and better. 15th epoch, 20th epoch, 25th. Oh, wow, 30. And I actually got this. So you really need to train it longer. These are just few of the results for the phase generations. How many epochs did we train it for? They have written over here. I forgot. Epoch means better resolution. No, not at all. Epoch means training, right? Epoch means iteration, forward propagation and backward propagation once done is considered as one epoch. You have forgotten deep learning or what? You are stressing me out today, Shailesh. Have you been attending the earlier classes? You have forgotten. And that is really stressing me out. Guys, let me confirm from all of you. What is an epoch? May I hear it? I mean, so much of efforts we have put in. Let me ask everyone, what is epoch? And also one more question, which Shailesh asked. More epoch means more better results? Yes or no? Or you have anything else to say? More it means more better results? Yes or no? Or something else? If you train it too longer, yes, if you train it too longer, then the model may start overfitting also. So the correct answer is exactly what Sultanu said. May or may not be. You have to actually find a sweet spot in between too many training and too less training, right? So that's exactly what happens with machine learning as well, right? Too much data sometimes is a curse, sometimes it is beneficial. So it depends. So that is what is the answer to this. Shailesh, if you are struggling with anything, please consider watching the recordings at 2x speed, at least the important concepts, so that you are not left out because you are starting with something very, very crucial, right? So I would strongly recommend you to invest some more time, because going forward, I don't want you to be lost. Please do not consider that I am trying to demean you. I am just trying to talk in benefit of you in a long run. So your questions, keep on asking. If they are something which we have covered lot time in the past, and if I'm saying that, Shailesh, why are you asking such questions, then please understand that these are something which are very, very basic. And if I am pointing out something like this, then there is definitely a concern. So do not take it the other way around. Take it in a positive way, as you have to revise the things else in a longer run. After completing the course as well, you will be left out with nothing in hand. And it does not only apply to Shailesh, it applies to everyone. He is proactive enough to ask questions. If anyone is struggling, then probably you need to strengthen your basics. Please take my inputs seriously, everyone. Okay, fine. Now we can go on a break and continue after the break. Any further questions by anyone? Shailesh says makes sense. February recordings are important. Yes, absolutely. You said it right, Shailesh. So please, if you struggle somewhere, go through it, and I'll be there to help you out. Okay. And as far as the notebook sharing is concerned, I will definitely love to share it, but there is one disclaimer I want to tell you. Things in generative AI are changing so rapidly that the notebook which runs today does not run tomorrow. So I am going to put this notebook, which you see right now on the screen, for execution today night. And then I will be sharing it with you in the next class. Right. So that is how these things are. But no worries, I'll be sharing that positively with you. My pleasure, Nagdeep. Thank you very much. Great. Welcome, Vijay. Basics are same, but if this notebook gives you an error, I know Nagdeep will come to me next day saying that, Darshan sir, the notebook which you gave is not running. And then I will try to rectify the error, and I will not be able to do it in front of you because the errors are at times so weird that, even I don't understand what to do. Then I have to Google, I have to look Stack Overflow, I have to get into ChatGPT, I have to look into the documentation. Sometimes I get the solution in just a minute, and sometimes it even takes hours. That's why I said, let me just try it once and then I'll share it with you. At least the one which I share with you today, today it should be working. Tomorrow, if not, then that can happen with anything. If you can suggest some hackathon for implementation, which would be helpful for hands-on practice. See, you know what? Image generation is good, no doubt about it. But I would recommend you all not to get into too much of image generation. See, today industries are looking for text generation. They're not looking for image generation. No one is looking for image generation in the industry. Text is the king. So if you really want to excel somewhere, please focus on text data, not on image. Just because this is there in the syllabus, I'm teaching it. I have been delivering for so many corporates, but GANs is something which they are not interested in learning. See, logically, you tell me, are there good algorithms for generating Hindi language, or are there good algorithms for generating the text in Gujarati language, Marwadi language, Marathi language? No. But are there good algorithms for generating nice images, or are there good cameras available for capturing the best of the best photos? Yes. Essentially, what I want to say is the research has gone to the finest level with respect to images, and there is not much scope left out for generating something better than that. But on text data, there is a lot of scope, and hence industries are focusing on that. So I would recommend you as well to focus more on the text part, how to gain knowledge on generative AI. What are we doing right now in our course is hands-on only. So I think I should be in a good position to give you a complete idea about it. You don't worry about it. The topics which I cover, you will be getting a complete idea about it. What you will not be getting an idea, which is trending today, is agentic AI. Else, as far as generative AI is concerned, Srikant, we are going to learn everything, right up to fine tuning. So that's not at all going to be a problem, right? So that for that, you can completely rely on me. Welcome, Akash. I may not be able to help you on any kind of project. I can help you only during the live session for the delivery, right? So for project related help, honestly speaking, that doesn't come under my roles and responsibilities, right? Whatever projects Simply Learn has asked, and whatever I think they are important, I will take it for you. But anything additional, you will have to find it out by yourself. Then for text data, and okay, and I work for. Oh, you're working for service now. So nice. I can vouch for Darshan sir said agentic AI is the future. Yes. Okay, there has been a training on service now, but I don't know that service now. So great. Vernacular is still challenging for the LLM models. That's correct, Shailesh. And some resources link which we can work. Kaggle is the best as of today, right, Nagdev? If you go to Kaggle, you'll find a lot of resources. In fact, even I also rigorously look for some good resources on Kaggle at times. Documentations are also having good resources. I'll share a few with you. Cool. Fine. So we are left out with our implementation, and we will cover it once we are back. I'll see you then. It's 9:08, so 9:29, 29 minutes from now. I'll see you then. Bye. Going on mute. Thank you. Okay, everyone. We're just starting in half a minute. Let's get into the explanation of this. Here we are. Now, we are getting into the demo for the generative adversarial network. Let us get started with the very first thing over here. So what is our problem statement? The problem statement is generating images. So we are going to generate fake images with the generative adversarial networks. The steps that we are going to perform is going to be importing of the necessary libraries, loading and pre-processing the data, building a discriminator generator both, then compiling the model, training the model, which is coming from the deep learning only, and then generate new images. So first and foremost thing, as you can see, I have imported in over here TensorFlow. right? So we all know TensorFlow is a main deep learning framework for building and training the GANs. And it is a high level API like Keras, which is simply used to build neural network implementations. Then I'm loading MNIST dataset and its layers. So MNIST dataset, all of us knows it is a dataset of 60,000 training images, all grayscale, and 10,000 test images. All of these are of the handwritten digits 0 to 9, and it is one of the commonly used one for benchmarking the image generation tasks. Then I'm importing the input layer for defining the input shape for the model. Dense is nothing but a fully connected layer that is used for both generator and discriminator. Reshape is for reshaping a tensor from flattened vector to a 28 cross 28 image. Flatten is for converting a multi-dimensional tensor into 1D tensor used in the discriminator for processing image. I'm importing after that the sequential layer and importing as well. That's the very first thing that we do in over here. So next thing, if you see, we are loading the MNIST data, and then the interesting thing is after loading, we are also normalizing the data. So while loading, you can see I have said extrain underscore. It is notebook. It is given by MNIST, so not MNIST simply learn. Extrain, ytrain, xtest, ytest, because we don't want to use them. Underscore is just to ignore the label since GANs do not use the class label. So it's basically extend white and xtest whitest because it's not needed. We didn't use it. Now, while normalizing it, we are not dividing by 255 here. So in the Simplilearn's notebook, okay, it's not my notebook. In the Simplilearn's notebook, I'll be giving you one demonstration of my notebook as well. But here in this notebook, we are converting the data first of all into. So first and foremost thing, here we are converting the data from uint format to the float 32 for better precision. And what is that essentially doing, right? So the next thing is we are also shifting and scaling the pixel values from the original range 0 to 255 to this. And how is that happening? That is happening because we are subtracting 127.5 from the center pixels around 0, and then we are further dividing them by this, and that is what is going to get this thing. And why are we doing it? Because the generator is going to use the tanh activation function, and tanh is always going to have the output in the range -1 to 1. So why are we doing it? Because of this. And that is the reason this time we are not doing the scaling in the range 0 to 1, but between -1 to 1. Okay, that's one thing. Thereafter, we get into the next line, which is expand dims. Now, what is that expand dims actually doing? See, we are simply in very simple words, we are expanding for compatibility. So if you look originally, extreme has the shape. Now, over here, the problem is Keras requires 4D input for the CNN models. And so basically, what we want in over here is the shape to be 60,000, 28, 28, 1, where here 1 is going to represent nothing but the grayscale channel. And that is exactly what we are doing. Then after that, we go ahead and create a discriminator. So what is precisely the generator going to do? What is the generator doing over here? The first thing we understood that it is taking up a value between 0 and 1, but that was for a two-dimensional network. Here we are generalizing it on a bigger problem. So it will take random noise, 100D vector, because we want a 100-dimensional output. And then after that, we will be further transforming it into an image of 28 cross 28. Further, we'll be using the fully connected dense layers to upscale the data. And then we have the tanh to match the normalization. This is what we are essentially doing. So if you see over here, first line where I am saying that I am having a sequential layer, we know that dense of 256 and input dimension is equal to this. So over here, we clearly understand that I'm having a fully connected layer of 256 neurons and the input is a 100 dimensional vector. After that, I am having a dense layer of this with rail, another dense, which you see over here. But you might be thinking that, hey, usually Darshan sir asked us to increase it in the power of, sorry, kids play with this door. Sometimes fingers and all get into that, that becomes really dangerous. So you see, why 784? Because 28 is the size of every image in the MNIST and we wanted of the same size, which is 784. So that is what is one thing which we are doing over here. And then I'm using the tanh as the activation function because I want the output to be normalized in the range -1 to 1. And you can also see at the end, we are having the reshape to make it into 28 cross 28 cross 1 because it is 28 cross 28. That the generator learns to map the noise into realistic digits. And also the progressive upscaling from 100 to 256 to 512 to 1024 and 784 allows it to extract the complex features, and tanh ensures compatibility with the pre-processed data sets. That is what we have in over here. Then coming on to the discriminator. So the question is, what does the do? Well, so that upper one is going to generate images. So discriminator is going to take 28 cross 28 image. It could be a real image or it could be a fake image. Its job is to discriminate whether it's real or fake. So it will take it and then it will classify it, and it is going to use the fully connected dense layer to extract the meaningful features. And thus, it is going to end with a sigmoid activation function for the binary. So if you see, the first and foremost thing is the input layer where I am converting 28 cross 28 by flattening it into 784 values. Then we have the hidden layer of 1024 to extract the features. Now it is going in descending order. And then we extract the more abstract features in 512 layer. In 256 layer, we are further condensing them. And you can see at the last in the output layer, we are just asking it to give one output, real or fake. So in simple words, the discriminator acts like a classifier distinguishing real fake images. Again, over here, using the progressive feature extraction, we are able to map it finally as a real or fake. And finally, this competition between the generator and the discriminator improves the overall GAN performance. So generator is converting random noise into realistic images using fully connected layers to upscale the data. It also outputs 28 cross 28 grayscale images with the tanh activation function. And then you have a discriminator which is going to classify it as a real or fake. So this is the main foundation of a neural network. Then after this, it's time to compile the model, which involves defining the loss functions and the optimizer. So loss functions evaluate the model's performance while the optimizer aims to minimize the loss. So first and foremost, what am I doing over here is I'm creating and compiling a discriminator. So create discriminator function is being called, and I am doing this job of initializing the discriminator. So it is going to use the loss function as binary cross entropy. So why binary? Because discriminator is performing a binary classification, real or fake. So binary cross entropy is a natural choice. Optimizer is Adam, which is going to adapt the learning rate. So you need to understand over here that the discriminator is trained separately to classify images as real or fake before being integrated into the full GAN. That is what I'm doing over here. And once that is done, I get into creating and compiling the generator, where I'm calling the generator that will be initializing it. Same loss function, binary cross entropy optimizer. I can play around with it, but I'm using Adam. So again, if you are thinking that why in the generator are we using the binary cross entropy, then I want you to think once again. See, the generator's goal is to trick the discriminator into thinking fake images are real. Therefore, I say, even though the generator itself doesn't directly classify the images, it is trained on how the discriminator responds to its outputs. And after that, I'm going to create a combined model. So if you look over here, when I say discriminator is equal to this, what's exactly happening when I say discriminator dot trainable equal to false? So I say that discriminator, now you relax. I'm freezing your weights. So you're not going to update that going forward. And now I'm going to mix you with GAN. Okay. So, the advantage of this is that only the generator weights are updated during the training, because discriminator has already learned it. Now the police is ready, police training is done, cop training is done, so cop is highly equipped in catching real and fake. Now it is a time for the counterfeit to become better and better. So I am making it as false. So this is the one here. What's exactly happening over here when I say GAN input is equal to input? So first and foremost thing, I am defining the shape, 100-dimensional vector. Then whatever is generated, I'll be passing it through the generator. So it will generate some fake image, could be good, could be bad, I don't know. But initially it's going to be bad. And then that is going to be, so that generator has generated. Then you pass it to the discriminator. So you give it to the cop that, hey, this is what I've generated. I'm sure you will not be able to catch. So the discriminator may or may not catch. We don't know that. So then I am creating a combined model, as you can see. So here the first part is the GAN and the second part is this, right? So you can see over here, the generator is the first part and the discriminator is the second part. And this model is trained using this. So how is this working? Generator is going to create a fake image from the random noise. Discriminator is going to evaluate the fake image and output the probability as real or fake. So generator is trained to fool the discriminator. And if the discriminator is fooled, then the generator gets rewarded. If the discriminator correctly identifies fakes, then it updates its weights, right? So this freezing of the discriminator is very, very important, because the discriminator else would quickly overpower the generator. So I say, why is this important? Number one, if both are trained together, then the discriminator might quickly overpower the generator. So by freezing the discriminator weight, only the generator learns, not the discriminator. That is the idea behind it. Then finally, there is nothing left after this. Now we are training the model. So we train the model, which involves feeding the data into the model, adjusting the weights of the model based on the outputs. The primary aim is for the generator to create images indistinguishable from the real images by the discriminator. So this function is responsible for training by alternating between training discriminator to distinguish real versus fake and training the generator to produce more realistic images. First thing, below the MNIST dataset, normalize it, expand it, done. Then after that, what I want is, there are images that I have to create. So this is where I am creating labels for the real and the fake images. So when I say ytrain underscore ones, this ytrain underscore one is going to be the batch of labels for real images, and zeros, which will be for the fake images. And this y test underscore ones is going to be where we are going to train the generator, forcing it to create images as real. And the best part of it, this network may at times look a little bit complicated, but trust me, nothing changes in this network. Even when I show you the advanced example, little pre-processing things would change, but not most of it. So here is where I am going to get started with the training. So I say for in range of epochs, so it will loop through it across the batch sizes, which is 128 images per. And discriminator is being set as true now because I will be training the discriminator initially. So that is done. Then some real images are generated. Now this looks a little bit tricky, right? So what am I essentially doing over here is I am essentially extracting a batch of real images. You can see, right, into batch, I plus 1 into batch size. So basically extracting just a batch of sample images. And after that is done, I am going to train the discriminator on batch. X is equal to X batch, Y is equal to Y. And what is this formula? It looks a little bit weird, right? This is nothing but I don't want to label it by myself. So little additional efforts which I am taking over here is I'm using soft labels, which means instead of labeling real images strictly as one, I am using this formula. So this is introducing some random noise purposely. So see, now you might be thinking that, but why are we doing it? That's also quite a valid reason that why are we using the soft labels. So the reason why you are using soft label is I don't want the model to overfit. So just to ensure that my model is not becoming overconfident, and obviously generalization is important. So that's another reason. So then after that, fake samples. So what are we essentially now doing? Now it is a time for us to generate fake samples by feeding some random noise. So I'm just creating a random normal function and I'm doing this fake noise generation. And then I'm also going to use the generator's output as input to discriminator. And then finally, I shall be training the discriminator. So you can see over here, predict on this noise and discriminator will be trained on this fake data. And then I'm keeping a loss track of the discriminator, then making the discriminator as false. And I'm asking the GAN to train on the generator and I'm keeping a loss track of the generator for every epoch. And exactly because of this, this process may look a little complicated, Darshan. This is a little new, overwhelming, challenging. No, it's not. Trust me, it is just the same thing and it will never ever change. So I'm training it for now 50 epochs, if you see, and the batch size I'm keeping is at 128. That means in each iteration, the model will process 128 images at a time. So now see, here you'll see some output. Here I would say that if you look at the D loss, now there are two things that can happen. If it is too high, which means that the discriminator is struggling. And if you see it is too low, it means that the discriminator might be too strong, making it harder for the generator to improve. In the same way, you also have the generator loss. Where if you see the generator loss is high, which means that the generator is still in the process of learning, let it learn more. And if you see the loss low, that means it has started generating realistic images. So now $1 million question. How do we know that the GAN is learning? The idea is very simple. At the beginning, it will generate bullshit images. Worst. But as and when the training progresses, the discriminator gets better at classifying the images and the generator improves and starts producing images that look more like it is expected, but it doesn't happen that way, that after 50 epochs, it is expected to generate some good looking images It may or may not happen depending on the training, to be very honest. No, 5 minutes for the book. Right. So here we see now here importing matplotlib. We are generating random noise, as we can see. So why are we generating random noise? Basically, if you see, what am I doing right here? I'm asking it to create 100 across 100 matrix of having any values between the range 0 to 1. And to be very honest, this is the one which is going to serve as an input. So random noise is what is going to be getting transformed into meaningful images. Then that random noise is passed to the generator for predicting, and then generator is generating images with the help of these function, and that is what we are visualizing. So I'm just saying that, hey, I want 10 cross 10 images. So that many images to be printed, and every time I am asking it to show the generated images. So what is this going to do is it is essentially going to extract a single gray scale image. Give me a moment. Okay. And that's it, if it is trained successfully, you should be able to see that. And you see this, what a quality of images. Not good. In fact, this notebook is giving error. Not error, actually, it's not giving error. The RAM is not sufficient, is what I realized. So, in fact, I'll show you when I do this on Collab also. You see the runtime disconnected. There's something wrong with this notebook due to inactivity or reaching the maximum duration. So, basically, the resources required by this are so large that our resources are getting full. So you cannot run this notebook. It's a perfectly running notebook, but you cannot run this notebook on your Collab. If you want to run it, you will have to compulsorily go for Collab Pro because this T4 is not capable of doing it. So yes, this is what we can say. I will.
And with that, we have come to the end of our course. If you have any doubts or questions, ask them in the comment section below. Our team of experts will reply to you as soon as possible. Thank you and keep learning with Simplilearn.